Hello my friends and welcome to this new section on the visualization of the results of the deep convolutional Q-learning model. First, I really want to say huge congratulations for having completed this whole implementation of the deep convolutional Q-learning model. And now here we are at the fun part where we're going to visualize the results of the AI we created. And as I said at the end of the previous tutorial, the last tutorial of the implementation, I said that I had a surprise for you, and well, the surprise is exactly this. We're going to visualize the results on Google Colab. And why is that a good surprise? That's a good surprise because basically you will have absolutely no trouble running the code, running the code and visualizing the results. Indeed, this is a new feature of the course. Before this, we actually used to run the code on Spider in Python, but it was extremely difficult to, install all the packages, PyTorch, the Gym dependencies and all the different dependencies. A lot of students actually had tons of issues installing everything, and at the end, most of them couldn't run the whole code, and mostly they couldn't see the final results. So I absolutely wanted to fix this, and really the best solution that I've come up with was to include the whole code, so you will have exactly the same code as what we've implemented in this part, but I've included the whole code on a Google Colab notebook, where the only thing you will have to do to run the code and visualize the results will be to click these play buttons here. That's the only thing you have to do, because the beauty of Google Colab is that most of the libraries and packages are already installed. For example, TensorFlow is already installed, PyTorch is already installed, and all the Torch modules, functions, and classes are already installed, so you don't have to install them. However, we still have some little dependencies to install to make sure everything is connected well, but we won't have to install them through a terminal or, through the Anaconda prompt like we did in the self-driving car. We will just have to click this play button here in this first cell, installing system dependencies for Visdoom. Now, I know what some of you might be thinking. Why didn't we do the same for the self-driving car? Well, unfortunately, we couldn't do the same because in the self-driving car module, we had the user interactions, when we plot some sands on the map to, design the roads and put some obstacles. Well, unfortunately, Google Colab doesn't have that feature yet of allowing to have some user interactions with some maps. So I couldn't do it for the self-driving car. My apologies for that. But that's why I gave you the whole chapter of my book on the AI crash course, which contains all the instructions on the self-driving car. I hope you could install everything properly. Anyway, there was not much to install compared to Doom. So I hope everything went well for the self-driving car. But for Doom here, now you're covered. You won't have any trouble running the code and visualizing the results. So that's the surprise. I hope you like it. And now I'm going to walk you through this whole implementation to show you that indeed we have exactly the same code as what we implemented in this part 2. The only thing is that I merged the three codes. This is the code we had in the folder, composed of the image preprocessing.py file, then the experience replay.py file, and then the AI.py file with the two parts, part 1 building the AI and part 2 training the AI. Well, what I simply did is I merged the three of them by putting first the image preprocessing.py file. I'll show you that in the workbook. Then second, the experience replay.py file, and third, the AI.py file. They're just one below the other in that order. Okay, so I'll show you this to you, and then I just had to change 2 or 3 things in this whole code, and I'll show you exactly the changes so that you can make sure to catch the difference. Basically, in that file, everything is the same. In that file, everything is the same as well. Absolutely no change. However, in that file, here, when we import the packages for OpenAI and Doom, we don't use the ppackage gym doom wrappers action space to import to discrete. We don't use that anymore. We will use something else, you'll see. And also, I changed the dimensions of the frames here, 80 by 80. I changed that to 256 by 256 so that you can have better visualization results indeed, because you will have bigger videos to watch. Okay, that's just what I changed. I'll show you now. Let's start with image preprocessing, because indeed, as I told you, I just merged the three files together. So we start with, indeed, image preprocessing.py, and as you can see, this is exactly the same. We start by importing the libraries, the exact same ones here. Then we pre-process the images with the preprocess image class composed of the init method and the observation method. And as you can see, this is exactly the same. Preprocess image class, init method, and observation method. All right. Then we move on to experience replay, where we have exactly the same indeed. We first import the two libraries here, NumPy, nametuple, and the ke, right? Then we define one step, exactly the same as what we have here. And then we make the AI progress on several end-step steps with the end-step progress class, which is exactly the same as in the workbook, right? I just did some copy-paste here. We have exactly the same, the init method, the iter method, and the reward steps method, all right? Then, of course, we implement experience replay with the replay memory class. And as you can see, we have exactly the same in the Google Colab. Plus, you will maybe better appreciate the structure because I added some text cells so that it can be even nicer to visualize on this workbook. All right. So replay memory class, init method, sample batch, run steps, basically exactly the same code. All right. And then we move on to the third file, AI for Doom, ai.py, containing the two parts, part 1 building the AI and part 2 training the AI. So let me show you that we have exactly the same on this workbook. So AI for Doom, ai.py, first we import the libraries, the exact same ones, right, as you can see. Then here, that's the difference I already highlighted. When importing the packages for OpenAI and Doom, well, instead of importing gym wrappers and then skip wrapper and ppacket to import two discrete, well, what we do is we only have to actually import gym, that's the same, then import this Doom gym, which are the new Doom environments, basically, which were really well improved, and finally the wrappers by the gym library. All right, so just this difference here, which will make the thing work on Google Colab and also on Python if you want to run it. And then here, of course, I didn't have to include that code within Google Colab simply because here we import the other files here, because they're separated. And since I merged the three files on Google Colab, well, I don't need to do this import. So here we move on directly to part 1, building the AI. And here, as I told you, we have the exact same code except for the dimensions here, right? If we look at part 1 here, part 1, building the AI, we start by making the brain with the CNN class. And as you can see, we have the exact same code except for the dimensions of the input frames here, which were, when we implemented the code, 80 by 80. But I changed that in Google Colab to 256 by 256 so that you can have better frames and therefore better videos to watch. Okay, but all the rest is exactly the same. So here we make the brain with the CNN class, then we make the body with the softmax body class, so exactly the same as what we have here. And finally, we put the whole thing together with the AI class containing the brain and the body and also some methods to perform the actions, right? Exactly the same AI class composed of the brain and the body and then the same method to perform the actions. All right, so exactly the same, just the dimensions of the input frames changed. And now let's move on to part 2, which will be also exactly the same. First, we get the Doom environment, right? Let me show you part 2 here as well. We get first the Doom environment. And here, remember that since we no longer use ppacket to import the environment, but instead visdoom, well, the only thing that changed in that code is indeed this. Here, indeed, we get visdoom corridor, but this is exactly the same environment. All right, and then, of course, I changed these new dimensions so that you can have bigger videos here. So we no longer have 80 by 80, but this time 256 by 256. And then we have exactly the same. We get the Doom env and the number of actions, which you will see will be 7. Then we build the AI by creating the brain object, CNN, then the body object, softmax body, and then the whole AI composed of the brain and the body, exactly the same as what we implemented together. All right, then we set up experience replay, so that's exactly the same here. And then we implement eligibility trace, still exactly the same. And then what do? Well, we make the moving average on 100 steps, exactly the same here. So that's the exact same code, basically only the dimensions of frames and the way to import the environment changed, okay? And finally, we train the AI with exactly the same code, okay? So until here, we have the whole code that you saw in the folder when you downloaded the dataset and code, okay? And basically, you also have the whole code that we implemented together. However, then to make the visualization work on Google Colab, well, I added this extra code. But since it is really only specific to this Colab notebook and also only specific to visualize the AI in action in the Doom environment, well, please, you don't have to worry about understanding all the codes that is here, because you will only see that once in your life when you want to build and train some AI to play in the Doom environment. What I mean is that you won't have to use this code for the other applications you'll be working on when building and training an AI. So don't worry too much about this code. I just added that to make it work on Google Colab. But let's see what I do. I first import the libraries, of course. Then I added some practical codes here so that you can very quickly see the number of actions you have in the environment, as well as a display of the frame of the environment, just to see how it is like. And the reason I added that is because I'm also going to show you how to play with other Doom environments, because you actually have many of them. And so what you will simply have to do is replace the VisDoom corridor by the name of the other environments, which are here. I'm going to give you the link of that page right after this tutorial. But here, as you can see, you have many Doom environments that you can play with. VisDoom Basics, VisDoom Corridor, which is the one we're going to play with right now, VisDoom Defense Center, and other. And you even have some indoor mazes. And just follow the instructions here. You will find them all in this folder. In this init method, you can just find the name here, VisDoom Basics, VisDoom Corridor, VisDoom Defense Center, and you have many of them, you see. So if you want to play with other Doom environments, feel free to do that. You will just have to change the name of the environment. Anytime you see VisDoom Corridor here on this workbook, you just replace that by the name. And thanks to this code and this one, well, you will be quickly able to see what is the number of actions, the dimensions of the input shape, and also a display of the frame to see how the environment looks like. So this will be pretty practical. Then I just made this helper function for the visualization. Then I run the AI on one episode, of course, after it is trained. So we will first train it here, as you can see. By the way, I forgot to tell you that I also changed the number of epochs from 100 to 20. And that's simply because, I increased the dimensions of the frame. And since I increased the dimensions of the frame, well, the training will take much longer because, of course, it's harder to train. And therefore, I reduced the number of 100 epochs down to 20. Okay, and don't worry, with that we will already get well positive rewards. But of course, if you want to improve the performance and improve the results in the end, feel free to increase that number of epochs. You will get even better results. But you'll see that already with 20 epochs, the training will take quite some time. Okay, all right, so where was I? Yes, that helper function for the visualization. Then I run the AI on one episode, of course, after it is trained. And finally, this last cell of code will output the video of the gameplay, over this one episode. And you will see how the AI will perform over this one episode on a video, which will be output and which you will be able to download in files here, when we execute this code. Okay? All right. So now, time to the execution, time to really sit comfortably in our chair. I hope you have a good coffee or a good tea. Now we're just gonna press the different play buttons in each of the cells to run the final result. So let's do this. But first, and that's very important to understand in Google Colab, so this is the link of a Google Colab workbook which you all have access to, and therefore, of course, you can't modify anything in it, because if one of you modifies, well, the others will see the modification. So this is in read-only mode, and therefore what you have to do in order to make some modifications, in case you want to change the name of the environment or increase the number of epochs or even tune your AI, well, you will have to create a copy of this workbook which will be in your own Google Drive. And that's why, in order to do that, you will need a Gmail address in order for you to have a Google Drive, okay? So make sure to have one, and once that's the case, well, you just need to click File here and then Save a Copy in Drive. And this will create a copy of this workbook in your own Google Drive, on which you will be able to do some modifications. All right, and now here we are at the beginning of this execution. So now we're just going to play all the cells and we're going to get closer and closer to the final result. Are you ready? Let's do this. Let's start by installing all the system dependencies for VisDoom. Let's click this play button, and now it will install all the dependencies, as you can see, like Pillow or SciPy, and also some other dependencies that are going to be needed to run this successfully. But all the rest, like PyTorch, the gym modules, are already installed. So that's really awesome. That's really the beauty of Google Colab, and that is thanks to which none of you will have any issue executing the code and visualizing the final result. All right, so this is going to take actually 1 or 2 minutes, so I'm just going to fast forward here, and I'll see you very soon for the rest of the execution of the code. All right, we seem to be at the end of the installation of the system dependencies. As you can see, it is downloading them, installing them, well, collecting them with all the right requirements, and in a matter of seconds, it should be done, right? And let's see, 3, 2, there we go. Successfully installed everything. Don't worry about these errors here. They won't impact the execution of the code, but everything is successfully installed just as we want. All right. So now next step, very important. Look at this important note. It says that after installing all dependencies, basically after executing this first cell here, you have to restart your runtime. Otherwise, you will get some execution errors here. So let's do it quickly. It's very simple. You just need to click runtime here and then restart runtime and then yes. All right, this will restart your runtime. And now you can just execute all these cells by just clicking the play button. So let's do this. Starting with this first file, image preprocessing. All right, so let's first import the libraries, then preprocess the images with the preprocess image class. And now we already moved to the experience replay implementation, meaning this one. All right, so let's do this. We first import the libraries, then we define one step of the environment, then we make the AI progress on several end-step steps with the end-step progress class, exactly the same as what we have in the folder, and then we implement the experience replay by building this replay memory class. All right, all good. And now we move on to the third file, this one, AI for Doom, ai.py, and we first import the libraries, then, all right, so it takes a little time here because we import all the torch modules. Then we import the packages for OpenAI and Doom, so with the Gym and Wisdom Gym and the wrappers. Okay, so all good. And then we move on to part 1 here, building the AI, where we're going to make the brain, then the body, and then assembling everything. So let's first make the brain, all right, with the CNN class. Then let's make the body with the softmax body class. And then let's make the AI with the AI class. All right, so all good. And now we already move on to part 2, where we're going to train the AI with, of course, deep convolutional Q-learning. All right, so exactly the same as what we have here. We first get the Doom environment with our new modules, VisDoom. Don't worry about this. This is not an error. Then we are going to build the AI by, creating the different objects, the brain, CNN, the body, softmax body, and the whole AI containing the brain and the body. All right, did I execute this? Yes. Then we set up experience replay with end steps and the memory as an object of replay memory. And then we implement eligibility trace, all right, to improve the performance. Then we make the moving average on 100 steps with the MA class. And finally, my friends, are you ready? Well, this is now time for, the very exciting part where we're going to train the AI over 20 epochs. All right, so you will see that this will be already a bit long. It will take like maybe 1 or 2 hours because I increased the dimensions. Feel free to reduce the dimensions back to 80 by 80 if you find this too long, but trust me, you will have much better videos with these dimensions, okay? So, are you ready? Let's do this in 3, 2, 1, go. All right, so this will execute the code of the training, and in a few seconds we should be able to see the first epoch, which will have, of course, a negative reward, but you will see that, over the epochs, the reward will increase little by little until reaching positive rewards, and then until reaching hundreds of reward. Well, let's aim for that, actually. Let's hope that with 20 epochs, we will have some final rewards at some hundreds, like 100 or 200 or 300. Because with these rewards, I experimented with them. Actually, yes, first epoch, negative rewards, minus 98. So I was saying that with rewards at around 100, 200, 300, we will get already some great results. We will see the AI managing to either kill some monsters or avoiding them or, moving towards the vest, okay? So that's the first epoch 1, minus 98. And then, we will see epoch number 2 with maybe already a better reward. But at the beginning, of course, the AI is not trained. It is exploring the environment, right? Remember this trade-off in reinforcement learning, exploration versus exploitation. Well, at the beginning, the AI is purely exploring, and then it's going to train, and then it's going to become smarter and smarter, and that's when it's going to reach some high rewards. So it's totally fine to have negative rewards at the beginning. Maybe we'll get that over the 3 first epochs, but then you will see that after epoch number 4, 5, or 6, well, we will start reaching maybe positive rewards, and then hopefully rewards at around 100, 200, or 300. Okay? So it's going to take a little while, as I said, so we're not going to stay here for 2 hours. Otherwise, I will run out of things to say. So what I'm going to do is I'm going to put a fun or cool music now. And there we go, epoch number 2, minus 62. So there's already some improvement, that's good, but you will see that there will be some even better improvements the more we progress in the epochs, okay? So what was I saying? Yes, I'm gonna put some cool music now and play the training in accelerated mode. And of course, I'll see you at the end of the training to see the final results. All right, so there we go, 3, 2, 1, go. All right, and here we are at the end of the training. Congratulations, you trained the deep convolutional Q-learning model on a very challenging application, which is to play the game of Doom. So, what to say first? Well, as we hoped for, we reached some average reward at more than 100. Then, what is important to say is, of course, that with more epochs, you will get higher rewards. So if you're ready to, for example, train this model for more epochs, like 100 epochs or even more, in order to reach rewards more about 300, 400, 500, or even 1000, well, feel free to do it. For example, you can let this run for the night while you sleep, and when you wake up in the morning, you get your better results. Note that you can also use in the runtime a GPU, right? If you change the runtime type, which I shouldn't do because otherwise it will restart the notebook, but in the hardware accelerator here, you can choose GPU or even TPU. But that's only if you want to, optimize the performance and do some super hard training. But here I just use the classic thing because I just want to show you how to execute all this. And there we go. Now we're going to execute the rest of the workbook with this extra code only specific to this Colab notebook, where of course we're going to visualize the AI in action. All right, so let's do this. Let's first import the libraries, right? All good. Then we're going to print the input shape and the number of possible actions. All right, so here we're going to get indeed that we have 7 possible actions, in the Doom corridor environment. So these are move forward, move backward, go left, go right, shoot, and then maybe protect yourself or whatever. I don't know what the last action is, but something like that. Then these are the dimensions of the input frame. This corresponds to the height of the frame. It has 240 pixels height. This corresponds to the width of the frame, right? It is 320 large, and this corresponds to, the fact that we work with colored images, and the 3 here correspond to the 3 elements of RGB channels. All right, then let's execute the next cell, displaying a frame of the environment just to see how it is like. And indeed, remember that's useful to see the environment you're working with, right? So here we see that we are in Doom Corridor, but if you want to experiment with some more environments here, actually, remember they are also in the main page. Here, right here, yes, you have all the list of the environments, that I recommend experimenting with. So, if you want to have a look at another one, well, I can show you actually. Let's get this one, and then I'll go back to this Doom Corridor, right? So if I replace that by this one, right, and I re-execute this, well, we will get 3 actions this time. Of course, it is a more simple one. And if we execute this cell, well, we'll see this environment, right? So it's just a way to quickly see what you're working with and to get a preview basically of what the AI will do in the environment. All right, so let's go back to Wisdom Corridor. Let's re-execute this, in case we need it for the next cells. All right, perfect. Doom Corridor. Now let's move on to the final cell. So this is a helper function that will be used for the visualization. So let's execute this cell. And now let's run the AI on one episode. And here you will be able to understand the code because, basically it is the process of, running the AI on a full episode where at each step it is in a specific state. It's going to play an action within the state. Then it's going to get the reward and then reach the next state, right? So this is the classic MDP process, right? Markov decision process. And so there we go, that's done for one episode. And finally, we're gonna get the video of the gameplay of our AI who was trained for 20 epochs, was able to reach more than 100 reward, which will get us some pretty good results, but maybe not reaching the vest, but it's okay, you'll experiment that by yourself. And now I would like you to click this folder button here because I will want to show you how the video is populated. So these are some folders containing, some elements like the frames, the frames of the results or some JSON files. But really what we'll be interested in is the final video. And to get it, we just need to click the play button here and you will see that it will be populated in the main folder here. Don't miss it. And it's okay, it looks like the cell was already executed, which is the case, but you will see that in a few seconds, we will see an AVI file, which is a video file, being populated here. It will appear in like 10 seconds. I can even do a countdown if you want. So let's do this. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go. And now it should really appear in a few seconds. Yeah, there we go. All right, so agent gameplay.avi, that's your video. So let's download it and it will be downloaded on your computer, which I will find right here, right? So that's the video, agent gameplay.avi. Make sure to open it with a video player that has codecs like VLC, right? It won't work with QuickTime Player if you're on a Mac, but it will definitely work with VLC. So let's have a look. And here is the video. All right, so let me just press pause here. All right, so here's the video. And as you can see, so this is the 256 by 256 dimensions of the frame. So as you can see, it's not very large, right? So that's why I really wanted to work with these dimensions instead of 80 by 80. So now let's have a look at the video. So this is the AI playing Doom on one episode, and it has to avoid the monsters, not be killed. It has to move forward to reach the vest. So let's see how it does. 3, 2, 1, go. All right, so first it gets shot, it moves forward, okay, and then it got killed by the monsters. But that's still quite good, It understood that it had to move forward towards the vest because the highest rewards is got by reaching the vest. And of course, if you really want to see the video of your AI reaching the vest and winning at this game, basically, you will have to train your AI for more epochs and maybe do some even other kind of improvement like tuning your brain of the AI or doing some parameter tuning like tuning the learning rate. Well, you have many options. If any of you get an amazing video or, the video of an AI having reached a reward of more than 1,000, for example, well, feel free to share it in the Q&A. I'm sure other students will be super happy to get it. All right, so I hope you liked implementing the deep convolutional Q-learning model. Now we're going to move on to the next part, which will be about implementing the A3C model, an even better and more powerful model, which we will implement to play the game of Breakout. So I'll see you in the next part, and until then, enjoy AI.
Hello everyone and welcome back. In this video we are going to talk about ChatGPT and how to use it to implement the same algorithm for Doom that we are going to use in the course, Convolutional Deep Q Learning. So in the next couple of minutes we are going to walk through the way that I actually went and asked ChatGPT for us to get our model. So let me help you understand how I did it and why I did certain prompts in the way I did. So the initial prompt was pretty well crafted from my end. I said, you are a senior machine learning expert with years of experience working on projects applying machine learning to simulations and robotics. This is the first part, setting the stage, giving them a role. So basically the vector space of the whole ChatGPT will be prompted more on a machine learning topics. Now I want to bring him to my context, Doom. And actually how to reach that point, I said, okay, I hired you to help me with implementing a convolutional deep Q learning algorithm for the Doom environment. The goal is to have a fully functional reinforcement learning algorithm that can play Doom, a game environment. I have implemented classes for experience replay and memory and image processing. I will provide you that so you can incorporate that into the final code. This is a really important, which most people misses. You need to have some way of telling him or telling ChatGPT that you already have something and you want to do that, to use that code in the final implementation. So if I didn't provide this as a context, it will generate some code, some implementation of convolutional deep Q learning that will not consider using experience replay and our image processing function. But we want that. So then I continue and saying your goal is to implement the full solution using Python, Torch, and model and optimize the code to be executed in Google Colab so that students going through the code can execute those with not so strong computers. This is basically telling the ChatGPT what is the format of the final solution that you like to have. And then finally, ask clarifying questions if needed. We'll provide it with more context and if you don't know, if you don't have enough context, please ask me. And finally, ask got it. I want it to confirm that it got. This is a clever way of allowing it to reflect on this and not strictly go to generate next prompts, next answers. If you don't do this, if you don't ask got it or clear or did you understand or something like that, it will completely ignore some of the parts and start generating. Since you have the limit of how many tokens you have in your questions and in the answer, you would like to break it so you can get a refresh on the amount of tokens that you can generate. So the first answer is, I understood the task. I'm going to do exactly what I'm going to ask. But before I proceed, I have a few questions. And this is where if you have any questions, ask me. It asked me pretty good questions. First off, do you have a custom environment or do you use something that is already there? So OpenAI, VS Doom and stuff like that. Then we move to more like, are there any specific performance metrics that you'd like me to follow? Are there requirements on the model itself? What versions of Python and PyTorch? And finally, are there any specific constraints on the deadline? This is from mostly business plans that it was trained on, but for it, like, it doesn't really, like this, it's not relevant for it, but okay. I provided, yes, I will use OpenAI Gym, and here is how to load it. This is from the course. I said, okay, follow average reward. No specific requirements, be creative, as long as it works. Use latest models or versions of the libraries. And what is the deadline? I just wrote ASAP. Additionally, here are these classes I mentioned. So I just pasted the classes that we have in the course. So experience replay, everything. And finally, replay memory, image processing, and that's it. And with this, I built the context. And now it started generating. So it generated the code. It basically started by pre-processing the image, then created the deep Q network, which is pretty similar to what we have. Then it started by initializing that, and then training code. everything so far worked, and then it breaks here. If you want to continue to generate something longer, I just wrote continue. And it said continue. Yeah, certainly. It continues generating. And bam, we have the full code. Amazing. It stated how to use it, frequency, what to change, and stuff like that. Help me with this as well. And let me bring you to my Google Colab. So I started by pasting the code here, pasted our pre-processing function. I'll jump to changes in this pre-processing function in a second. Then I'll paste this experience replay, some of the installation from my end. We'll explain this in a second. I played with his DeepQ network and training code. So there are definitely ways to improve this, especially if you have local environment, it will work. If you are using this in a Google Colab, it might break. So let me bring you to that. So I did it and I got an error. I said, hey, my initial code that I provided did not work. I just pasted the code, this error message, and saying I can't resize any images. And if you take a look at our code from the course, it requires to resize the image with this. But the newer version of SciPy is actually removing this. So it said, oh yeah, it appears that it's been removed. Here is the new version with pillow. And it actually, I didn't require that. It basically rewrote the whole pre-processing image class with pillow instead of SciPy. So I use it. And it's working actually. And then I said, okay, I have a problem with environment using Google Colab. How to solve it? This is the error. And it said, oh yeah, apologies. It seems that this particular environment is not working. Here's what you do. You basically install and do this. I got an error, another error. And this error actually indicated that rendering is not found in this particular version. And it said, okay, install this version. I did. Another error. And it said, oh yeah, Google Colab does not support rendering OpenGL libraries, which means for us that we need to do, instead of Google Colab, something else for visualization purposes. And it basically gave me step-by-step leading on what to do, how to change that, and stuff like that. And if you do this locally, you will solve the problem. But this is basically now teaching you how to use properly ChatGPT. Like right here, you saw that I got some errors, I prompted with those errors, and so on. And now you have, like if you scroll back, you have full functioning code with a DeepQ network, with a training code, and you can go and ask it to generate a test code, and it will. Amazing, right? So that's it. This is how to use ChatGPT to solve the DeepQ or convolutional DeepQ network for Doom. Thanks. Enjoy the course.
Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to discuss the plan of attack for this amazing section on the most powerful algorithm in artificial intelligence, which is A3C at the moment. So let's have a look. Today we'll talk about the following things. We'll start with the 3 A's of A3C. So we'll talk about what the abbreviation stands for and how we're going to deal with the 3 A's. And also we'll look at the actual article or the actual research paper that gave birth to A3C, the Google DeepMind research paper. And we'll have a quick look at it so that you're more comfortable navigating it in your free time. Plus, we will see exactly why the A3C is the cutting edge, most advanced algorithm on the planet for artificial intelligence at the moment, and why it's so important to have this in your arsenal. Next, we're going to talk about the first A of A3C, which is actor critic. Well, A3C actually stands for Asynchronous Advantage Actor Critic algorithm. And so we're going through the A's not in order, but we're going through them in an order that makes sense for us, that will help us in our intuitive understanding. Then we'll talk about the asynchronous element in the A3C algorithm. And then we'll talk about the advantage. And that's the tutorial where we'll put everything together and it all start making sense. So a quick word of caution that as you're going through these, you might notice that after the actor critic and even after the synchronous tutorial, you will still not exactly have the full picture or full understanding of how this all ties in together. And that's totally okay, because all these three elements, they indeed work together, and they require each other to function. So just power through it and get to the third tutorial. And in the third tutorial, the advantage tutorial, that's when it'll all come together. And if at that point you still don't quite understand something, then you can just revise that specific tutorial, whether it's actor critic or asynchronous or the advantage tutorial, to put all together. But basically, just don't get thrown off if after one of those two tutorials you still feel that you need some more information. That's because they all work together to come to one functioning A3C algorithm. That's in the advantage tutorial that all ties in together very nicely. And finally, we'll talk about some additions that you can add, or some additional modules and elements that you can add to the A3C algorithm. The thing is that there's different versions of the A3C algorithms, different modifications, and already through the first 4 tutorials in this section, we will see some modifications, and at the end we will add an extra one, the long short term memory, LSTM. Now here we won't go into a lot of detail on LSTMs. That's a topic for another course, but nevertheless, you will get a overview of what LSTM is and how those structures or how those layers in neural networks work, so that you have a better understanding in preparation for the practical tutorials. But very important also, this will showcase how the A3C algorithm can be modified to suit certain purposes. So there we go. That's the plan for this section. Definitely it's going to be an exciting algorithm to look at, because it's the top algorithm at the moment in the world, and we're going to be developing an intuitive understanding, and then together with Adlan after this, you're going to be coding it, which is very, very exciting. And I can't wait to see you on the first tutorial, and until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're taking our first step into the world of A3C. And as a first step, we're going to find out what this abbreviation stands for. So A3C stands for Asynchronous Advantage Actor Critic Algorithm. This is an algorithm which was developed at Google DeepMind in 2016 by a group of researchers, and it's the cutting-edge algorithm for artificial intelligence to date. Now, it has multiple modifications, and we'll discuss that more in the course, especially in the practical tutorials, but nevertheless, this algorithm blows everything else, including deep convolutional Q-learning networks, out of the water, completely out of the water, and it is faster, it takes less time for training, and gets better results. So throughout this part of the course, we'll be referencing, and we have already referenced, but we'll be referencing even more, a paper, or the paper that was published that first introduced A3C. It's called Asynchronous Methods of Deep Reinforcement Learning by Vladimir Mnych and others from Google DeepMind. So I'm going to show you this paper now so that you have an introduction to it. So here is this paper. I wanted to show it to you so that you can get a feel for it and already get introduced to it a little bit. And of course, it is highly recommended to read through the paper and understand what exactly they're talking about. And you'll see that throughout the practical tutorials, Adlan will be taking you through certain parts of the paper, through certain paragraphs or sections which will be relevant to what we'll be programming at that point in time. And what I wanted to point out here is, like, as you can see, a lot of research went into this, and there's a lot of references as well. But like a part that I really like is that at the end, the very end, they compare the different algorithms, compare the results. And this is what I wanted to point out here. So let's zoom in a little bit. So here, as you can see, even in Google DeepMind, they're training, or they're evaluating the algorithms on games, just as we're doing in this course. So exactly the same principle, because games are a simulated environment or a small environment, a confined environment with certain rules, and they want to understand how well this artificial intelligence is doing in those games. And here we've got exactly all those games which you can find. A lot of them you can find on OpenAI Gym, and the games that we've been working with. So for instance, in this section, we're working with Breakout, so it's also here. And so you can see that for Breakout, they've got in bold, they've got the best algorithm highlighted. So DQN, that's the algorithm we've been working with. Then some other algorithms, and then here you've got A3C with an LSTM, long short-term memory. So that's the one we'll be implementing in this part of the course. We'll have A3C with an LSTM, which makes it even stronger. So as you can see, Breakout is the best result is achieved by A3C with LSTM. So that's the score, 766.8 compared to the others. And also you can see that for the most of them, so if we now take like a bigger picture view, you can see that most of the bold ones are actually in this last column. So yes, indeed, there are some games where other algorithms are performing better, but as you can see, DQN is actually not performing better in any of the games. But you can see that there are other algorithms perform better sometimes, but A3C LSTM performs the best in most cases. So you can see that this is bold, this one, these ones, this one, and so on. So you can see that A3C LSTM is a really powerful algorithm. It is indeed at the forefront of artificial intelligence, and that's exactly what we'll be implementing. So very exciting section ahead. Highly encourage you to go through this paper and get a feel for what we're going to be talking about, and then throughout this section and throughout especially the practical side of the things, practical side of tutorials, we're going to be going through this in detail. We're actually going to be working with their pseudocode here, which is available, and so Adlan will show you how to implement that and how we're going to be working with that. And on that note, I hope you're going to enjoy this paper, and I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the first part of A3C, the actor-critic part. So here we've got asynchronous advantage actor-critic algorithm, and we're going to be talking about that underlined actor-critic part. That's where we're going to start. You could technically start anywhere, but it just makes a lot more sense to start from actor-critic, because that way we'll have like a very consecutive explanation of or intuitive understanding of what's going on. It's going to facilitate us better if we start surprisingly at the end of this abbreviation. All right, so far in this course, we've come up with deep convolutional Q-learning, which is illustrated over here. So we've got the computer seeing the pixels, so the actual image in pixels, not just a vector. So it's not cheating. It's actually seeing exactly what a human sees. It sees the monsters, it sees the health, it sees the parameters at the bottom, it sees the corridor, it sees the gun. It sees exactly the same thing as a human would see when playing this game. Then that image is passed through a convolutional layer. Then it's passed through a pooling layer. Then it's flattened and goes into a neural network. And then at the output, we've got actions. As you remember, we've got those Q values. Then we apply a action selection policy to them. So for instance, we apply a softmax and we find out which action we want to take. And so there's some exploration plus exploitation going on there, a combination of the two. So that is how deep convolutional Q-learning works. But now let's see what we're going to do with this. So for simplicity's sake, just so that it's easier for us to operate with this, because we're going to be adjusting this image and moving it around, we're going to replace the circles with squares, with these rectangular boxes. And we're also going to get rid of those lines in between, just change them to arrows. So this doesn't change the essence. This is just the representation on this chart. This is still, even this representation is still deep convolutional Q-learning. It's just going to be easier for us to modify it and show exactly what A3C is. So that's just how we're going to represent things from here. And what A3C does, or this specific part, so we're starting, remember, we're starting like step by step. We're starting with the actor-critic part. So we're going to see how we go from deep convolutional Q-learning to A3C step by step. And first step, we're going to introduce this actor-critic part over here. So we're going to talk about that. So the first thing that happens is this last bit, the output is actually, we're just going to redraw it like this. So it's exactly the same output, exactly the same Q values, or exactly the same actions. So if you had 8 possible actions, you still have 8 possible actions. We're just going to put them at the top so they take up less space. So nothing has changed. So far this and this are exactly the same. But now this is where the actor critic part comes in. We're going to have a second output. We're going to have, so the first one is a set of outputs, and here we're going to have a separate individual output. So technically we're going to be using our neural network. So once, and now, well, the image and everything, like the values go through the network from left to right. Over here, they don't just spit out one set of values, they spit up actually 2 sets. And so the top set, we already know what it is. It's the possible actions, but here we're actually going to have another extra value. So let's have a look at that. What is that value? So here we go. That's the top. So we just kind of like reduce the size of this illustration. The top output are the Q values, as we discussed previously, for the actions. So there, same thing, everything is same. But then now this bottom part, and the top part is actually called the actor. We're going to give it a name. That's the actor because that's the part where the agent chooses what it wants to do. So that it's like it's acting, it's as if it's performing on stage. And it'll make more sense once we have the second name up on the screen as well. And then the second output is just like one value, and that is V of S. So that is the value of the state. So if Q of S and A is the Q value of a certain action, and as you can see, that's why there's action 1, action 2, action 3, up to action 6, or however many actions there possibly are in that state. So in a given state S, what is the Q value of taking action A, action 2, action 1, action 2, and so on. Then here we're also using the neural network to predict what is the value of the state we're actually in. And this part is called the critic. And so that's the intuitive, or the kind of not even full intuitive. That's just like the start of the intuition behind actor critic, that there's 2 outputs now from the neural network, not just one. Before we just had that one output, which we now call the actor, but now we have 2 outputs, actor and critic. And there's going to be a dynamic between them, which we'll explore further. But for now, it's important to understand that we're predicting not just the Q values of the actions that the agent can take from this certain state, but we're also predicting the value of being in this current state using that same neural network. So that's the core of the first step into the actor critic. And now we're going to need to talk about asynchronous, which we'll do in the next tutorial, in order to understand exactly what's going on between the actor critic. And the final thing for today is that all of these Q values, as we know, that's also called policy. So in some literature, in some blogs, in some discussions you might find in the actor critic, you might find the author talking about Q values on this side of the actor. In other literature and blog posts and discussions, you will find the author talking about the policy. So, and usually it's they use a Greek letter P for representing the policy, or it might just say policy of state S. So altogether, these are the policy of state. It's because, as we remember, the policy is if you put all the actions together, the possible actions, and then it's deciding which action to take. So these are going to be like the probabilities of taking each action. So that's the policy. So don't be thrown off if you see one or the other. They basically mean the same thing. So on one hand here, you've got the policy or the Q values. On the other hand, you've got the actual value of the state, and they're being predicted from the neural network. So that's the start of the actor critic. We'll continue with this in the next tutorial when we're talking about asynchronous. And I look forward to seeing you there. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're continuing our journey into the world of A3C, and we're talking about the asynchronous side of A3C. So there we have our abbreviation, Asynchronous Advantage Actor Critic, and today we're going to find out what asynchronous here stands for, what it means. And let's go back a step. Let's look at what we started this whole course with. We started with reinforcement learning and what it's all about, that the agent is in a certain state. They observe the state, they make certain decisions, they take actions in that state, and then the state is changed, so they get into a new state, plus they get a reward. So they get a reward for taking that action, or some sort of reward, which could be a penalty as well, and they end up in a new state. And based on that, now they take another action. Again, they get a reward, and end up in a new state, and they take another action, and so on. And so that is the basis behind all of reinforcement learning, and that's what we've been using in Q-learning, in deep Q-learning, in deep convolutional Q-learning, and that has allowed our agents to beat gradually more complex and more complex environments. But now we're going to introduce a even better concept and even further take this even to a further level. What A3C introduces through this asynchronous element is, instead of having one agent attack the environment, they have 3 agents or whatever number of agents. So several agents attacking the same environment. And the key here is that why it's called asynchronous is because they're initialized differently. So their starting points are different. So for instance, as you'll see from practical tutorials, you set a random seed and you set it differently for each of the agents. And that way, because their starting points are different, they're going to first go through environments in different ways, and then they're going to explore in different ways. And then in the next iterations, they're also going to explore in different ways. And so, for instance, if you have 3 agents, you're all of a sudden you're getting triple the amount of experience. Instead of just one agent going through and exploring the environment and trying to understand how to operate in that environment, you now have 3 or however many of them going through that, getting this experience. And so so that each one of them is learning through this bigger experience. And apart from being just giving a broader range of experience, it also reduces the chances of one agent getting stuck in a local maximum. So for instance, if one agent finds like a way to beat the environment, which is not the most optimal, because if it deviates to the left or to the right from that solution that it found, it always gets more penalized. It might get stuck in that local maximum. It might just keep doing that, thinking that that's the optimal solution where it's actually not. Well, the likelihood of several agents getting stuck in that same local maximum decreases with the number of agents. So the probability of one agent getting stuck in a certain local maximum might be high, or might be a certain value. But the probability when you have 3 of them, of all 3 of them getting stuck in that local maximum, is much lower. And as long as they share experience between each other, they can help each other out. So if one of them gets stuck, for instance, it's stuck in a local maximum, just simply think that's the best one, that's the best solution all the time, and keeps doing that. Well, as long as it interacts with the other agents, so let's say this guy gets stuck in a local maximum, as long as it interacts with the other agents through the way we build our whole algorithm, A3C algorithm, they will help him out. They will give him knowledge that actually, no, hey, you should explore this, or he will be more likely to get out of that. And also overall, the environment will know that, hey, even though this is a great maximum, these other agents have seen better options, and we should keep exploring because they looks like they're better options. So in a very short, kind of rough, intuitive understanding, those are some of the advantages of having these asynchronous agents. First of all, you have more experience to choose from and to learn from. You could get to the solution faster, and generally speaking, there's a lesser chance of getting stuck in a certain local maximum. So let's see how this all plays out in this model that we've built so far. So as you remember, this is what we've gotten so far through the actor critic. And this is like where it all ties in. This is, so far, as you remember from the previous tutorial, we did introduce this, we had this already, even in deep convolutional Q learning, so we just named it actor now. But now we've introduced critic, but so far it doesn't really make sense. What's the point of having this critic and measuring the value of the state, or predicting the value of the state using the same neural networks, the same approach? But now this is the part where it's going to start making more sense. What we're going to do is we're going to replicate this, because now we have multiple agents. So with multiple agents, this is what it would look like. So the first way of imagining it is now we have these 3 things. Well, remember what we said about them sharing the experience between each other. So this is actually right now they're all independent. You have one playing the game, another one playing the game, another one playing the game. It's like launching your agent on 3 different computers. You put 3 different computers next to each other and you launch them, and that's great. Like, indeed, you'll get more experience, you'll get like more variety, especially if they're initialized different. So we're gonna assume from here that they're always initialized different. Even though we have the same picture here, we're going to know that they're actually initialized differently. So it's not going to be like identical training, identical learning from this game. And so even if you put 3 computers side by side and you launch them, yes, you're going to have more experience because you're going to have 3 agents playing. And also you're going to have a bigger variety of possible solutions. So that's true. But the problem is that they're not sharing that experience among each other. They're not learning from each other. So they don't have that synergy. They don't have the advantage or the extra power that they would get if they were cooperating. You know, like how if you have a team of people, they work better together than each one of them separately. So like in a team, here you got 1 + 1 + 1, it's 3. But in a team, 1 + 1 + 1 is not 3, it's like 33 because they leverage each other's strengths and mitigate each other's weaknesses. And same thing here. So if you put these 3 computers side by side, yes, you'll have more experience, more variety, and possibly someone will get to a better solution than the other one. That's great. But it'll be even better if they start sharing that experience. And how do they do that? Well, it's through this V that we calculated. So this V value that's the output of our network is actually like that. So they have this same V. So every time all these agents, they're contributing to the same critic. They don't have separate critics, they have a common critic. And that's the key of how the actor critic ties in with the synchronous. So there's one critic that's watching as they get experience. So how do we calculate the V? We calculate the V through, as you remember, we calculate the V through the values that we get. So the rewards that we get through the environment. And so as the agents explore their environment, they are calculating, they're predicting the V, plus they have the V that they can calculate. This is all ties back into what we've already discussed in the previous sections of this course. So they already have a V that they can predict, like expect through the rewards that they know that exist in this maze, and that they've already explored. And as they explore them, of course, that value can change. But also they have the V this V is the output of the neural network. So as they're going through this, they're going to be adjusting their neural networks in order to better match that expected V. So basically, this is shared. The critic part is shared between the agents. And that is how they share the information between each other. That's how they are able to kind of see what's going on in the environment, shared with each other, and then use that, as we'll see further in the next part, in the advantage, use that in order to optimize how they're behaving in that environment. And the other thing to note here is, so this was A3C. This is like the core of A3C up to here. This is a version of A3C. But there's an actually even better implementation of this A3C, which you'll actually hear Adlan talk about in one of the first tutorials in the practical side of things. And what he'll be talking about is how the creator of PyTorch actually made an adjustment to one of the codes that was shared on GitHub, where he took all of these. As you can see right now, they have separate neural networks and only they share the V. That adjustment that was made was actually to take all of these neural networks and put them into one, take them and put them together. So ultimately, there's only one neural network here shared among the agents. So before each one of them had one neural network, which was shared for the actor and for the critic, one neural network shared for the actor, for the critic, one neural network shared for the actor, for the critic. Now they all have one neural network, which is shared for the actor, critic, actor, critic, actor, critic. And then the critic is here in common. So let's see. Let's move these pictures to the left over here. So make some space. And this is basically the architecture or the structure that we're going to be using in the practical tutorials. I know that like this may sound a bit overwhelming at this stage, but we've got one more A to talk about, which is the advantage, and there we'll see a bit better in action how this is going. So we'll talk about the intuition in action there. But generally speaking, this is what it is. There's one network which each of the agents use. So they share, basically what that means is that they share the weights. The weights of the network are shared between the agents. And when they update the whole network, not just their own network. And then they have outputs. They have like these actions for each agent, and then they have the critic that is shared, which is going to be monitoring. So I know all of this is kind of like there's a lot of stuff right now, but hopefully it's slowly coming together. At least the main takeaway from here is that the critic, because it's shared, that's how the agents are able to make sure that they're cooperating together in order to get to the result much faster. And then in the next tutorial, we'll see even further how all of this adds up, how all of this comes together. And for now, there's I would like to recommend, or we would like to recommend you an additional reading. So this is a blog by Jaromir Janisch. It's called Let's Make an A3C Implementation. There's actually two parts, implementation and theory. There's the link, and it's very similar to what Adlan will be implementing in the practical side of the tutorial. So it's not specifically for this tutorial, not specifically just for this tutorial, but it's for this whole section. Encouragement there, some additional information, some additional insights there. And so that's why we're bringing it up here. But nevertheless, in the next tutorial, we're going to start pulling all of this together, everything we've discussed so far. And I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're talking about the final A in A3C. We're talking about advantage. So there it is. We've already spoken about actor, critic, and asynchronous previously, and slowly built our way to what we're going to be looking at today. And with advantage, we're going to put everything together. So this is what we have so far. We've got a neural network which is shared between the agents, the asynchronous agents, and then we've got the critic, which is also shared between the agents. So how does this all play out, and why is this critic shared between the agents? Let's have a look at that. Well, understand this better, we're going to look at an example. We're going to look at this agent, for instance, and see what happens when he's in a certain state and he needs to make a decision what action to play. So this agent is in a state, he sees this image, and then what happens is this information goes into the neural network, it goes to the convolutional layer, then it goes into the pooling layer, then it goes into the flattening layer, and then from there it goes into the hidden layers of the neural network. And then as an output, he gets all of these policy values, the Q values of the policy, and also he gets the V value, the critic value. And so, as we know, neural networks, in order to operate, they need to propagate certain errors or losses back through the network, so this way, in order to update the weights. So what losses are we going to be dealing with here? Well, we've got two losses. We've got the value loss and the policy loss. So the value loss is linked to the V value, policy loss is linked to policy. And so value loss, we've already dealt with it before. We know that we have rewards, and we know that we have a discount factor. So basically, this is very similar to what we were talking about in the deep Q-learning tutorials. Basically, the network predicts a certain value V, and at the same time, we can estimate what should be, based on what we know about the environment so far, we can estimate what should the value V be in the state. And by comparing the two, we can calculate the value loss and then backpropagate the network, update the weights. So that's pretty straightforward. The new thing here is the policy loss. And so what is this policy loss and how does it work? Well, this is the part where this whole situation where the critic is shared between the actors or between the agents is going to finally emerge. So to understand policy loss, we need to introduce a value called advantage, hence the name of this part of this tutorial and this whole part of the A3C algorithm, the advantage. And the advantage is calculated as Q of S and A minus V of S. So basically, the Q value that you chose to play of the action that you chose to play in the state that you were in, state S, minus the value of that state. So this is the difference between the two, and that is called advantage. And the advantage is used in the calculation of the policy loss. Now, we won't go into the formula of the policy loss calculation because it's quite complex. It uses entropy, or it can use entropy, doesn't have to. We're not going to dissect that formula, but we're going to understand this on an intuitive level. Why are we doing this? Why are we calculating this advantage, and how is it going to help us? Well, let's look at this for a second. The Q value here comes from what the neural network predicted for this agent. So it predicted in this specific action, in this specific state for the action that it can play. So it's got these actions and it can select one of them, and it can play it. Well, whereas the V value is the value that is dictated by the critic. It is the value that we have here in this shared part. And that's the key here, that this part is shared. So the critic, because this is how the critic comes into play, because we've got a value that we choose, or the action that we choose to play for this agent in that state, but then the critic can tell us what is the known value of that state. What is overall the known value for this whole group of agents that are performing together, because they're sharing, not necessarily because they're sharing the network, but because they're sharing the critic, they're all contributing to these V values that are being calculated for a different state. So the whole A3C algorithm says, okay, so the critic knows a V value. How much better is your Q value that you're selecting compared to the known V value? That's what it's saying. So that's basically it. So that, okay, I'm going to select a Q value here based on my policy, based on whatever we use, like a softmax function or a epsilon greedy policy or something like that. And of course, there'll be exploration plus exploitation combined in there. But we select a Q value, and now the question is, what is the advantage? Hence, it's called advantage. What is the advantage that your selected action brings compared to the known value of that state? And that is the essence of the advantage. And basically, then that is used to calculate the policy loss. And then the policy loss is then backpropagated back through the network. So they're both backpropagated through the network, and the weights are adjusted in order for the network to better represent the value of the critic. And also, so that's this top part. But then this also part, the key here is that the weights are when this policy loss is backpropagated, the weights are adjusted in such a way so that this advantage is maximized. So like that's the intuitive side of the intuitive understanding of it, that we are backpropagating this policy loss through the network in order to help maximize this advantage. And what that means is basically that when an agent comes across bad actions, like actions where the Q value is less than the known value for this state. So basically the whole A3C algorithm knows that the value for this state is something X. And then all of a sudden you came across a very bad action, and you chose a bad action. And what that means for the A3C algorithm means that, well, why would we do something like that when it's worse than what we already know about this whole environment and what we could have done? So we shouldn't do more of that. And therefore the weights are adjusted in a way so that happens rarer, so that happens less rare. So that's a less frequent occurrence that we choose that bad action. On the other hand, if you choose a very good action where Q value is greater than V or much greater, then during this backpropagation of the policy loss through the network, the weights are going to be updated in such a way to reinforce that, to reassure that to happen again, so that the weights will be adjusted in such a way so the A3C algorithm will think, oh wow, that was really cool, the advantage was very high there, I should do more of that. And therefore it will update the weights in such a way that will be more likely to occur in the future, that action. So, and therefore that is that's how the network is slowly going to adapt and slowly going to construct itself into something that on one hand calculates the value correctly, and then on the other hand, or as correctly as possible, and on the other hand it encourages, or it has actions which have a high advantage. So there we go, that's this part. And now let's have a look at another one just to kind of reinforce what we just discussed. So let's look at the top one. So same thing here. The top agent sees a situation, a state is in a state, and then needs to decide what to do. So sends this information to the network. So this image goes into network, goes to convolutional layer, pooling layer, flattening layer, goes into the hidden layers. And then from here we get an output. We get the Q values of the policy. We get the V values. Again, same thing. We've got two losses. We've got the value loss, which is here, the policy loss, which is here. Value loss, we already know how it's calculated. We discussed this in the deep Q learning and just discussed this just now as well. So that's how the value loss calculated. And then the policy loss, again, in order to calculate that, which we're not going to go into formula, but on an intuitive level, we're calculating the advantage, which is, okay, so we took a certain action, we chose a certain action based on our selection policy, whether it's softmax or epsilon greedy or whatever other selection policy that we're using. And then what's the action we took? Now let's compare it to the known value of the state, which comes from the shared critic. So this critic is kind of like, if you think about it, he's kind of observing all of these agents at the same time. He's looking at this one, looking at this one, this one. They're all contributing towards the critic to get the critic more up to speed with the environment, to make sure that the critic is representative of what's going on in the actual environment, so that the weights, that's where the value loss comes in, so that the weights of the actual neural network, that they reflect very well the actual situation of things in the environment, so that they can then rely on this value and then use it here. And so basically, so all of these agents, agents are contributing to this critic, but then at the same time, through this value loss, but at the same time, the critic is observing the decisions or the policies of these agents. It's like looking back at like I'm trying to draw like an arrow to the policy, an arrow. It's looking back at them, at the decisions that they're making. It's criticizing these decisions through the advantage. It's saying, okay, you made a decision, you chose this action. That's great. Now let's calculate the advantage. What is the advantage? The advantage is A equals, the Q value of the decision I made, or the choice I made, the action I chose to take, minus the known value to the critic, So calculate the difference. If it's a low difference, when your policy loss is backpropagated through the network, the weights are going to be adjusted. It's going to encourage the weights to be adjusted in such a way that doesn't happen again. That Q value, or that Q value is going to be lower, so that because our policy selects the actions based on the Q values. The higher the Q value, the more likely it's going to be selected. So if we were using like an argmax policy, then we'd just always select the one with the highest. As you remember, we discussed this. Then we'd always select the one with the highest Q value. But we're using a probabilistic approach, whereas either using like softmax or epsilon greedy policy. And then, so we're basically selecting, we can select any one of them, but the higher the Q value, the better. So if we selected something and then the advantage was very low, then bam, the network is going to be updated in such a way that next time this Q value of that certain action is going to be less, and maybe something else will be more. So that's how that is played out. And on the other hand, if we select something where the advantage is going to be high, then this is going to go into the policy loss, and then the network is going to be updated. So that is a more commonly observed scenario. And so basically, this whole policy loss helps the network adapt or morph in such a way that we do more of the good stuff, good actions and good things, and do less of the bad things. And that's how these two losses come into play, and that's how they backpropagate. So hopefully that clears up in a very intuitive way. Of course, we didn't go into the formulas, into the complex mathematics behind all of this, and like into the very intricate details. But at the same time, hopefully in an intuitive way, all of this clears up why we have the actor and the critic and how they interact together. That you have these agents asynchronous. So this is the synchronous side of things. Then this is your actor and your critic, and this is your advantage, and how that all comes into play. So these asynchronous agents, they're playing this or exploring the environment and working through the environment, and they're all together contributing to a critic, which is then observing their policies, observing the actors, which is what this is called, and through the advantage, and therefore coming up with this policy loss, and then policy and value loss, they're backpropagated to adjust the network in order to, on one hand, represent the true way of things in the environment, on the other hand, to improve the actors' performances. So there we go. That's a quick recap of the intuition we discussed. And once again, hopefully this is all coming together on an intuitive level. And of course, in the practical tutorials, we'll talk more about how all of this works, and Adlan will walk you through the process of building this. But having this image in your mind, and this kind of like a roadmap of everything, how it comes together, should be, I hope it will be very helpful for you to better navigate the practical side of things. And in terms of additional reading for today, we've got two elements. So first one is on the advantage. So here we've got high dimensional continuous controlling using generalized advantage estimation by John Schulman. And this is an image of a stick figure getting up, like standing up. And here you can find even more about advantage, and you'll find out the different types of advantages. So you've got the generalized advantage estimation, You've got advantages that you use actually in the formulas in the calculation. So if you want to find out more about advantage and exactly how it works, the formulas behind it, and some of the top elements or formulas and know-hows in the space of this advantage that we discussed, then this is the article to go to. And one other element that or piece of work that we wanted to remind you about is a series of blog posts by Arthur Giuliani, which we've mentioned a couple of times already. This is part 8, which is specifically about A3C. So here you can get another explanation, so with a bit more mathematics about what's going on, and maybe you can pick up some additional things from here. Just 2 things to keep in mind. First of all, as always, this blog is in TensorFlow, whereas we're using PyTorch, so keep that in mind. And the second thing is that the way we structured our approach is we talked about actor-critic first, then we talked about asynchronous, and then we talked about advantage. Whereas in his blog, Arthur first talks about asynchronous, then actor-critic, then advantage. So keep that in mind. So hopefully that doesn't throw you off. But other than that, of course, it's a great piece of content, and we do highly recommend checking it out for some additional information. So there you go. Hopefully you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to talk about an add-on that we're going to be implementing for our A3C algorithm. It's called the long short-term memory, or the LSTM for short. So let's have a look at what we have so far, and then we'll discuss why we need the LSTM and what an LSTM is. So far we've discussed the A3C algorithm. We've talked about all 3 letter A's in the A3C, and of course we've seen that it's actually a bit more complex, much more complex than what we have on this image. We actually have 3 or more multiple agents going through the environment, and they're communicating between each other and so on. But for simplicity's sake, for today's tutorial, we're going to just illustrate everything with this one agent. At the end we have this actor part, the critic part. So basically, once we have a state, that state of this image goes through a convolutional layer, then it goes through a pooling layer, goes through a flattening layer, and at this point we have values or numbers which are then propagated through the network, and they go into the hidden layers, and then as the output we get the policy or the actor part, and we get the value of the state, or we get the critic part. And what we're going to do today is we're going to talk about this hidden part. So in the hidden layers, we can actually take it to the next level, and we can add a modification. And we've already seen that multiple modifications exist for the A3C algorithm. We've seen one of them. We've seen that in some cases you can have this main part of the network which is individual to every agent, or you can have this main part of the network which is shared. And that's what we saw, that in our previous intuition tutorials we had a shared part of the network. This network was shared between the agents, and as Adlan will tell you more in the practical tutorials, that really helps with the challenge of breakout. And there are lots and lots of other ways you can modify the A3C algorithm, lots of other additions that can be implemented. And one of them we're going to discuss, because we're actually going to have it in the practical side of tutorials. Here, before your hidden layers, which you can add, is an LSTM layer, a neural network layer, which allows your A3C algorithm, which allows your algorithm to have memory, which allows your algorithm to remember what happened before. And we'll talk about LSTM just now in more detail, but basically you can add an extra layer here, which is the LSTM layer, and enhance your algorithm with some additional memory, with another feature. And what you'll actually see in the practical tutorials is that we didn't even need any hidden layers after the LSTM layer. So you'll see that in Adlan's implementation, he's got the flattening layer. Right away after that, he's got the LSTM layer. So basically this box represents the LSTM layer. And then after that, right away, you've got the output. So you didn't even need any other hidden layers after that, simply because that's how much power the LSTM layer adds to the algorithm. And again, the algorithm, or the architecture of your neural network, it's a very individual thing. It's a personal preference. It's a very creative thing. So you might want to have 2 LSTM layers. You might have an LSTM layer, and then several, like 5 hidden layers after the LSTM. That's totally up to you and for you to experiment and explore. But this is what we came up with in the practical tutorials. So you'll see that we have a flattened layer, and after that, we've got an LSTM layer and then the output. So now that we've talked about the LSTM layer so much, what is this LSTM layer? Well, the LSTM layer adds memory, gives a feature like allows the neural network to have memory about what happened in the previous iterations. And it is often symbolized or shown with a symbol which looks like this. This is us just getting started into it. And I'm just putting here, I know it looks very crooked, but I'm putting it here so you can see when we further discuss this image, you can see what's going on. So the output of this layer goes into here, and that is our so this is a whole layer going in here. So it's a vector of values. X is a vector of values, goes into the LSTM, which we'll just discuss just now. And then as an output, you get another vector, which is, the concatenation of these two, or somehow it ties in with network. In our case, as an output, you get this and you get this. So let's have a look at this in more detail. So we're just going to focus on this part. In fact, we're going to, as you probably noticed by the letters being on this side, we're going to turn it to the side. So like that. And this whole like jumble around was just to reiterate the fact that even though it looks like this, what is actually happening is a layer of values, a whole vector of values is going in here. Something is happening, which we'll discuss just now, and then a whole vector of values is going on here. So this is the layer. It's not just one element of the layer. This is the layer itself. So let's go back again, just to reiterate. Layer goes into this layer. Something happens, layer comes out. So that's the LSTM. It's just on its side. So it's just easier to discuss this way. And that's the common representation. All right, now that we agree why this image was on its side and how we're going to proceed with this, let's start digging into this LSTM situation a bit more. So what happens inside the LSTM layer? So this is what it looks like. And of course, this looks very complex. And we're definitely not going to go through all of this right now. Simply because there's quite a lot to discuss. These are point-wise operations, these are layer-wise operations, and there's just a lot going on, or a lot of intricate details which we're not going to go into because otherwise it would blow out this course. And the purpose is not to talk about LSTMs here. We're just going to utilize LSTMs. And if you'd like to learn more about LSTMs, you can either go to over here, Christopher Ola's blog. He's got a good description of LSTMs, or we also talk about LSTMs in our Deep Learning A to Z course. You can check it out there. We've got a whole section on recurrent neural networks and LSTMs as well. So basically, this is the internal part of the LSTM, and what happens is like the layer goes in. So we're going to talk about this on an intuitive level, on a very basic intuitive level, just what is going to be enough for us to understand what happens, why there's memory, and so that you can also better understand what Adlan is talking about when he's implementing this. So a layer goes in, all of this, something basically goes on here, a layer goes out. What we need to actually see is that these parts, there's actually additional inputs into this layer. So remember this, usually you have like an input from a previous layer, then this layer, and then you have an output. If you think of that image we had previously, the normal network, which is not on its side, which is like from left to right, not from bottom to top. But with an LSTM, you actually have more inputs. So I know it's getting even more complex. But these things, at least we can understand them. So this is your memory cell. This is the key, and this is what you'll hear Adlan talk about. So the memory cell is something that is saved in the LSTM. So these inputs and these outputs, they're actually, here what you're looking at is the time axis. So this is unraveled in time. So in one specific iteration, this happens. But then this value is taken from the past, and this value is passed into, these values are taken from the past, and these values are passed on to the future. And how they pass? Well, through the way the LSTM works. So without worrying about too much what's going on here, all we need to understand is that the layer goes in, and here we already have a value which came from the past, which is stored inside the LSTM, inside the long short-term memory. We've got this memory cell, and whatever value was here before, it just stays here. As you can see, it just goes through. It flows through freely, except for these point-wise operations where it can be either closed off or something can be added to it. But regardless of that, it's just some value that flows through freely. So it's basically it's passed on to the next point in time. So you can just think of it as like some memory that, like a flash drive or something like that this cell has. And so it just remembers the previous value that was in here. And then it can use that to either add to it or read from that value and so on. And this value is the hidden state. So hence the H. And the hidden state is basically another value that comes from the past and then is used inside the LSTM. And as you can see at the end, after all of this happens, what you get is you get a layer that comes out, and so you get this value that comes out, and it is the same value that's passed forward. So basically, the LSTM remembers two things. There's a constant value that is just like stays in the LSTM that can be changed. Like there's a flash drive for like a constant value, so the memory cell. And so you have the luxury of storing something in that space, in that memory, and it will be passed on to the future. So whenever in the next iteration, so like the algorithm was in an environment, it saw something, did something, and so on, and then in the LSTM you can store a certain value, and then it will remember this value even when it's in the next state. And also the other value that it will remember its previous output. It automatically will remember its previous output. So the output goes here and goes here. So that's basically the very, very, very high level of what happens in an LSTM. Once again, if you'd like more details, there's lots of resources where you can find. And at this stage, we just don't need to go into that much detail on all of these things. We just need to understand, what a memory cell is, what a hidden, memory cell is, what a hidden state is, and how they facilitate memory for the LSTM. And the question is, so now that we kind of have a general overview of all of this, to reinforce or to solidify this knowledge, or kind of like give a reason for this knowledge, let's ask the question, why do we need memory? Why do we need memory in our A3C or other algorithms? Well, let's look at our example, the challenge that we're taking on in this section. So the challenge is breakout. And what happens in breakout? Well, in breakout, you've got this environment, these little blocks that you need to destroy with this little ball, and you need to make sure that this is your kind of like racket or platform that's moving around, and it must, wherever the ball is flying, it must catch the ball, and it'll bounce off the platform and go back and hit. It'll bounce off the walls as well and go back, hit a block, and come back. And so that's the essence of what you need to accomplish. But now let's look at this ball. Like, imagine you're an A3C algorithm, or an agent inside one of those agents inside A3C. You see this picture. What do you extract from here? What would your actions be here from here? So you can see the ball is flying, right? So, well, it's flying, right? So it's going somewhere, and maybe it's flying towards you, right? Could you make this conclusion? Could you like anticipate that it's coming towards you? You probably could, and maybe you're in the right spot to catch the ball. But what if the ball is actually not flying that way? What if it's flying that way? The thing is, you cannot tell from this one image which way it's flying, because you don't know where it was in the previous moment of time. So if it was here, then it's flying this way. So if you knew the previous moment in time, if you knew that it was here, then now you know here, as a human, you just draw a line from these two and you'd be like, oh, cool, so it's going this way. But if you knew it was here, you draw a line from these two and it's going this way. Moreover, look at this. It could have actually been somewhere like over here. Maybe it's going up. Maybe it's actually going that way. So maybe it was here and now it's going up way. So just from that one image is very hard. It's actually impossible. It's just like geometrically impossible to tell which way the ball is flying. And so that's why the LSTM, the memory, actually really, really helps algorithm. Without the memory, you can still do a good job. It could probably like guess or, find other ways of understanding where to go. But with the LSTM, with just even that one memory, so if we go back, even with that one value, well, that was kind of like the output of the previous value, or maybe you can store it here, or based on this value, like based on the information that it gets from the previous point in time. So let's say from what happened here. So that's where your ball was before. So you can pass on information about the environment from the previous point in time through here. Then now you have it. Now you don't not only have your information from the image. If we go back even further, you'll remember that information from the image, well, this is Doom, but we're actually working with Breakout. information from the image came here, 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 turned into these flattened values. And so that's information from the image coming into the LSTM. And now all of a sudden, as you remember, coming from not from somewhere, but from the previous point in time. So that's why you can't actually demonstrate it's coming from the top or from the bottom, from the left, right. It just stays in the LSTM layer. You have that information just through the architecture of the LSTM. You have the information about what happened previously. And so we go back. That information here helps you now make a decision on what to do, helps the algorithm make a decision. And now all of a sudden it knows that, okay, so the ball is actually flying in either direction. Let's say it's flying in this direction or in this direction, so I'm in the right place. So I should stick around here. The ball is coming in my direction. Or if it realizes the ball is flying there, it should start moving to the left, because if it waits a bit longer, it'll be too late and it'll miss the ball. So basically, that's how the LSTM layer really helps in this algorithm, and that's exactly what we will see when you're doing the practical tutorials with Adlan. So there we go. That's how LSTMs work. And just one additional note, as we mentioned at the start, LSTMs are not 100% necessary. They're not a complete, like they're not completely attached to the A3C algorithm. You might want to have them in the A3C algorithm. You might not want to have them depending on the situation, depending on the architecture you choose. There are lots of additions, and we've already discussed the addition or the modification where the neural network is shared between actors or is not shared between the agents or not. Now the LSTM. There's another one that you will see in the practical tutorials where we add entropy, which is calculated through a policy loss, and Adlan will walk you through that. So basically, there's lots of different modifications that can happen in an A3C algorithm. Just remember that it depends on what you want to achieve, and it's also something that we'd encourage you to explore if you're going to be implementing lots of these and trying out different algorithms. We've already discussed a couple, and maybe you can find some additional modifications that might be of interest to you. Or maybe when you're watching these tutorials, maybe by then more modifications have come out which are very interesting. So definitely that's something that you could look into, and that could further enhance your knowledge of artificial intelligence and how to create these algorithms. And on that note, I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI.
Hello and welcome to the third module of this course, the A3C, Asynchronous Actor-Critic Agent. And so now I can really say, welcome to the state-of-the-art machine learning. Well, at the time I'm saying this, because maybe some of you will take the course in 1 or 2 years, but at the time I'm saying this, in 2017, well, you are about to work on one of the most powerful models in artificial intelligence. But there is more. That is not the only special thing about this module. Not only we're about to work with the most powerful AI model, but we are going to implement the most powerful version of this algorithm. That is the most optimized version, implemented version of the A3C model. Because you can imagine that there's the heart of the A3C algorithm, but then there are a lot of tools that we can use to optimize the whole model. And so not only you're going to have the heart of the A3C algorithm, but we're also going to implement all these tools around it to make the model super powerful. And why did I want to do that? Well, that's for 2 reasons. The first reason is that we're approaching the end of this course. This course is the highest level course between the 3 courses, ML, DL, and AI A to Z. So now I think you're ready to take it to the next level. And the second reason is that solving breakout is actually super challenging. Remember in the promo video, we wanted to put breakout as the first module because we thought it would be the easiest challenge. But not at all. It was actually the most difficult challenge. An easy way of explaining this is that, well, in Doom, the monsters are big and therefore easier to detect and therefore easier to kill or avoid. But in Breakout, we have this tiny ball that the AI has to detect as well because the AI will still have eyes here. We're still going to do deep reinforcement learning. So it's actually super challenging, and that's why we don't really have a choice to implement the most powerful version of the A3C. Now, why do I say this is the most powerful version? That's for a particular reason. It's not like I'm saying that I'm going to implement the most powerful version of the A3C. No, it's not this. The reason I'm saying this is that the version we're about to implement, and this is something very special we're going to do, is actually a version of the A3C that was implemented by somebody, but corrected by one of the most influential people in machine learning today, who happens to be the creator of PyTorch. His name is Adam Pashka. So now what we're going to do, we're going to go on GitHub, on the PyTorch main page, and if you scroll down to the end, down to the bottom, you will see the team of PyTorch creators and contributors. And you can see here that PyTorch is currently maintained by Adam Paske. That's the person who we should really be grateful for, because there are very few versions of the A3C that work well for Breakout, and he corrected one of the code for the A3C to make Breakout work perfectly well. So Adam Paske is not only maintaining PyTorch, but also he is one of the creators of PyTorch. And as I said today, he's in the top 10 most influential people in machine learning. So we can feel confident that the version we're about to implement is probably the most powerful version of the A3C today. And so what is this implementation? Well, originally it comes from a developer called Ilya Kostrikov. And so as you can see, he did a PyTorch implementation of the A3C, which originally didn't work well for Breakout. But then somebody made a pull request. If we go to the pull request here, we can see in the close one that there we go, we have this one, a cleaner solution to grad sharing problem. And guess who this pull request was made from? It was made from Adam Paske, the creator of PyTorch. And that solved the problem. That made the A3C work very well on Breakout without waiting for days and days. And therefore, if we go back to this implementation, we can see the 4 contributors of this most powerful implementation. And here are the contributors. So thank you very much to all of them. And we can say a huge and special thank you to Adam Paske for fixing the gradient sharing problem. He started by doing a fork, which is a sub-branch of the code. And then he did a pull request to the developer to fix this problem there was in the code, which is a gradient sharing problem. And that's how he became a major contributor of this implementation, making the whole thing work perfectly well. And trust me, I did a lot of experimentation on the A3C model. I actually implemented 5 models. I was even desperate that it didn't work well, so I made my own breakout on KV to have a bigger ball and therefore an easier pre-processing of the images. Then I went back to OpenAI and made my own implementation of the A3C, but that took ages to run and train on a pretty powerful computer. So I wanted to find a better way, and that's the way it is. This very powerful implementation of the A3C model, of which one of the major contributors is the creator of PyTorch. So what we're going to do in this module, I think you're ready for that, is implement this highest level code for the implementation of the A3C. So we're basically going to re-implement all these files, and we will mostly insist on the files that are directly related to the A3C. For all the parts that are directly related to the A3C, we will implement the code line by line. For the others, I will just explain the code. So we should be able to tackle this without finding it too overwhelming. So there we go, quite a special module. Not only we work on a state-of-the-art model of AI, but also, at the time I'm speaking, I'm highly confident we're implementing the most powerful version of the A3C. So let's do it, let's go back to Python, and let's start all this. Before we start, we're going to do the most simple thing we're going to do in this module, setting the working directory folder. So let's go to our AI A to Z template folder, module 3, breakout, the most challenging one. And there we go, that's all our files. So let's see which ones are directly related to A3C. And so let's see which ones we're going to implement line by line and focus our energy on. So there are actually 2 files. The first one is model.py, which is this one. So we will re-implement it line by line because that's the most important. That's where we make the A3C brains. And the most important thing to understand here is that we will have a shared model which will have the same update of the weights for the actor and the critic. So that's a part of this special version of the A3C, the shared model with the shared update of the weights. And then the other most important file that we will implement line by line is the train.py file. Of course, right after we made the brains of the A3C, well, we have to train them, and we train them in this train.py file. So this is quite a long code, but this is what contains the heart of the A3C model, which will have 2 losses to reduce: the value loss, which is the loss related to the predictions of the critic, and the policy loss, which is the loss related to the predictions of the actor. So this is quite new, but that's because in the A3C we're basically working with several agents, each one having their own copy of the environment, but we also have this fully connected layer that outputs a value of the v function, and that basically is a common vision of what's happening in the game. So this will be quite challenging, so make sure to be in good shape. And for the rest of the files, well, I will just explain them in details, but not by spending too much time on them. Believe me, you want to keep your energy for this. This will be already a lot. So these files are env.py, which is an improvement of the gym environment thanks to Universe. So basically that file just improves the gym environment with Universe, and that allows to have an optimal preprocessing of the images and also to normalize all the values of the environment, like the colors intensities or the rewards intensities, well, all the values of the environment. This file normalizes all these values and also makes sure we have an optimal preprocessing of the images. And as you can see, this is taken from this OpenAI GitHub page with a Universe starter agent. So we will not spend too much time on this. We will actually stop here. You just need to understand that we improve the gym environment with Universe to get an optimal preprocessing of the images. The rest is not that important, especially for the A3C. Then we have main.py, which is the code that will execute the whole thing. So you know the code that will run the whole thing, create the brain, train the brain, and output the videos. And that's because it will run all these codes here. So model, we saw what it was. Then myoptim.py is a special optimizer. So that's basically the Atom optimizer, but adapted to this shared model that we're implementing. So we will explain all this code in one tutorial. Then we have test.py, that's actually the last one. So test.py is basically the file that will implement a test agent. So that is an agent that will play breakout without updating the model. So that's totally independent from the training. And we will also explain this code in details. Besides, the good news is that you will have two codes. One code, which will be the code we implement in the tutorials, but without any comment. And one other code, that is one other code folder, with all the codes commented. So with all these 6 files, all well commented. So that if you miss something in any tutorial, well, you will be able to look at the commented code to understand what's going on. So there we go. I hope you're excited to implement this. You're really at the top of the mountain now, or just below the top because you need to understand this first. But you're getting there, so take a good breath of oxygen, and there we go for this super exciting journey. Until then, enjoy AI. Hello and welcome to this tutorial. Alright, so we're going to start with the first file of our model and the most important file, that's model.py. And this is in this file that we will implement the brain of the whole model. You know, the brain at the heart of the A3C model. So that's in this file that we will make the neural network, which will of course contain some convolutional neural networks because of course we're still doing some deep reinforcement learning, so our AI will still have eyes. And inside this neural network we will integrate everything that is related to the actor-critic model. And there's a bonus. As I told you, we are implementing one of the most powerful A3C models, and what makes it that powerful is that it will contain a recurrent neural network, and more precisely an LSTM, long short-term memory, so that we can learn the temporal properties of what's going on in the game, that is actually the temporal properties of the input, so that the predictions can be even better. So there we go, we are implementing a very powerful model that combines basically all the neural networks that we saw in the deep learning course, that is an artificial neural network, a convolutional neural network, and a recurrent neural network. And at the heart of all these networks, there is of course the A3C model that will make the AI very powerful. So let's do this, let's attack this model and implement it. So we're going to start by making 2 functions. There are just some functions that will take care of how we can initialize the weights, because you know we're going to have some neural networks and therefore we're going to have weights. And we just want to make these 2 functions first so that we already have a tool to integrate very easily inside the whole model, the neural network. So these 2 functions are going to be normalized columns initializer. That is basically a function that can not only initialize some weights, but set a specific variance of a tensor of weights. So that's exactly what we're about to implement right now. And then we will implement a second function, which will be the weights init function. And that will basically initialize the weights in an optimal way for the learning. All right, and then once we're done with these 2 functions, we will start implementing the neural network. So let's do it. Let's quickly make these 2 functions. So I'm starting with the def here. Then I'm going to give the name of this function, which is normalized underscore columns underscore initializer. There we go. And this function is going to take just two inputs. First is going to be the weights we want to initialize and the standard deviation. Because as I just said, we want to set a specific variance for our tensor of weights. And if you want to understand why we have to do this, it's because, you know, when we make the neural network, there will be the actor and the critic, according to the A3C model. And we will make two separate fully connected layers, one for the actor and one for the critic. And these two fully connected layers will have weights. And we will set a standard deviation for each of these two groups of weights. And so what we'll do is we will set a small standard deviation for the actor. It will be around 0.01 and a big standard deviation for the critic, which will be around 1, I think. So that's why we're making this function, so that we can very easily set the standard deviation for the weights we will initialize later for the actor and the critic. That's why we're doing this. So now we're just going to set a default value, but this will change afterwards when we initialize the weights. So let's choose so far 1.0. All right, and now we're ready to define what's inside this function. So what we'll first prepare is the output that we're going to call out. So this out variable is what will be returned by this function. And so out, first what we're going to do is initialize it. So as you understood, this output will be a tensor of weights that will have a specific standard deviation. But before we take care of setting the standard deviation, we just want to initialize it, and then we will set the standard deviation here, which is the argument, which is the input of this function. So out, and to initialize a tensor of weights, you might know how to do it. We already did it. We're going to use our torch library. And from this torch library, we will take the rand n function, which will initialize a torch tensor with random weights that follow a normal distribution. So that's why it is called rand n. N is for normal. And so now what we simply need to input is the number of elements that this tensor will contain. And this number of elements is of course the number of weights, because we're actually initializing a tensor for these weights here. And so to get this number of elements, we can simply take our weights and add dot to get size with parentheses. And this will give the number of elements in weights, so that it will create a torch tensor of the same number of elements of our weights. And it will be initialized with random weights following a normal distribution. All right, and now it is time to set the standard deviation we want to have. That is this standard deviation here. So what we're going to do now is a simple normalization. We have a torch tensor of weights, and now we want to normalize it. And so to normalize it, we will simply write the explicit computation. And so what we simply need to do here is take our output, then update it by multiplying it by the standard deviation we want to have, divided by this sum I've just mentioned. And so to get this sum, we're going to use the square root function by torch. And so that's why I'm taking here torch.sqrt. That's the square root function. And inside, we are going to input the squared sum of the weights of our vector. And so we take our output, then we use the pow function to which we input 2, because we want to take the square of the sum. And then we take, therefore, the sum, and inside we are going to specify the index of the column that contains the weight we want to sum. And then to get these weights separately, because we want to sum them, well, we use the expand underscore as function of our output, out. All right, so this will get the weights of out, which so far was initialized as a torch tensor of weights. So that gets all these weights. We take the sum of squared, and then we take the square root to apply the normalization. And the fact that we have this standard deviation at the numerator will make sure that, I can write it here, variance of out will be equal to the square of the standard deviation. This formula here will make sure that this tensor of weights that we initialized will have a variance that will be equal to the square of the standard deviation that we input as argument. And that is how we can set a specific standard deviation for the future actor and critic that we will make soon. And we will choose a small standard deviation for the actor and a large one for the critic. And we will do this very easily thanks to this function. Alright, and so now we have only one thing to do left. It's of course to return the output that is now normalized with this specific standard deviation. Alright, so perfect. That's the first function we had to make. That's the first tool we will be very happy to use to make the A3C brain. We have one more function to make now. It's going to be the weights init function, and that's just a function that will, I remind, initialize the weights to make the learning optimal. So let's do this in the next tutorial, and until then, enjoy AI. Hello and welcome to this tutorial. Now we're going to make this second function to initialize the weights, and this one will be used to get an optimal learning of actually these weights. So the second function, we're going to call it weight underscore init, and it will take as argument the object m, which will represent the neural network. So that's all, and then colon, and now let's get inside the function to define what we want it to do. So basically what we want it to do is initialize the weights of the neural network in such a way that we get an optimal learning. So this will not seem particularly intuitive. This is based on research papers and experiments. We are going to initialize the weights in a specific way that we haven't seen before, but believe me, that will optimize the learning process. So we will just implement it without getting into the details of why we initialize the weights this way. And so we're going to start by using a trick, which will be used later to make the distinction between the convolution and the full connection. Because remember, our AI will have eyes, and therefore it will have some convolutional layers, and of course it will also have some fully connected layers, and we will have a different initialization of the weights for these two types of connections. So we're going to use this trick to separate these two kinds of connections, and then we'll use some if conditions to get a different initialization for each of these connections. So this trick is to create a new variable that we're going to call class name, and that will be equal to m, our object. So m represents the neural network, but it's an object. We will see that later. And we're going to get a special attribute from this object, which will be class name with double underscore first, class, double underscore, dot, double underscore again, name. And almost there, another double underscore. So that's a pretty ugly trick to look for the type of connection of our neural network object, but that will give us exactly what we want. You're going to see it's going to make sense when we start the if conditions. And by the way, speaking of if conditions, we can start them right now. And so what we're going to do now is start a first if condition, which will get us the first case, that is, if the connection is a convolution. And so to write this condition, we write if class name dot find. Here we use a method, the find method, find, and inside we input in quotes conv for convolution. And so if class name dot find conv is, we're going to do different than -1, that is actually if we have a convolution, because -1 means no, well, in that case we will do a special initialization of the weights. So this condition here means if we have a convolution connection. So in that case, what we do is run this specific initialization of the weights we want to do. And so that's where all the non-intuitive things will come. We will start by creating a variable that we're going to call weight underscore shape. So weight underscore shape will be a list that will basically contain the shape of the weights in our neural network M. And so we're going to use the list function to create a list. And inside we're going to input M, the neural network, dot weight, which will be the weight of the neural network, but in the convolution connection. And to get the shape of these weights, we use another attribute, which is dot data, and then size. Size will get us the shape of these weights in the convolution connection. So now weight shape contains in a list the shape of the weights in the convolution connections of our neural network M. Alright, so we have weight shape. Then To initialize the weights of this convolution connection, we're going to need two values. First is the product of the first dimension by the second dimension by the third dimension. So that's what we're going to get right now. And then we will also need to get the zeros dimension times the second dimension times the third dimension. And then we will use these two values in the computation of how we initialize the weights. So let's get these two. This first product, we call it fan in. And that will be equal to the product. And we're going to use the prod function, which is a function by numpy, which has the shortcut np. So np, that's prod. And inside prod, we input what we want to make the product of. And so as we said, that is the dimension 1, 2, and 3 of our weight shape. And so to get this, we can take our weight shape and get the indexes of these three dimensions. And so we said it's dimension 1 up to dimension 3 included, so up to dimension 4 excluded, and that's how we can get it. 4, the upper bound here, is not included. So that's exactly what we want. Then same for fan out. As we said, fan out is going to be the product of the dimension 0 times the dimension 2 times the dimension 3. And so here we can get the index from 2 included to 4 excluded. So that will get us the product of dimension 2 and 3. And then we can multiply it by the dimension 0, which we can access with weight shape 0, of index 0. So to sum up, this is dim1 times dim2 times dim3, and just below we have dim0 times dim2 times dim3 of our weight shape, list of weights. Alright, so now we're going to use these two values, fan in and fan out, to proceed to the initialization, because we're going to compute a new value that we're going to call w bound, and that will be equal to the square root, which we can get with the function np from numpy.sqrt, exactly like before. So the square root of 6 divided by fan in plus fan out. So fan in plus fan out. There we go. So this w bound here represents in some way the size of the tensor of weights. And why did we get this? It's because then what we're just about to do now is we want to generate some random weights that are inversely proportional to the size of the tensor of weights. Because indeed, what we're about to do now is take our neural network M, then get its weight, so by still taking the attribute weight, then access its data, that is the tensor itself, and then from this tensor of weights, we're going to generate some random weights that are inversely proportional to the size of the tensor of weights. And so in this uniform function now, we have to input a lower bound, which will be minus w bound, and the upper bound, which will be plus w bound. Okay, so that's for the weights, and now we need to initialize the bias. And good news, for the bias it's going to be much more simple. We are going to initialize them all with zeros. So to get these bias, we take them from our model, of course, that is our neural network, and then the attribute for the bias is bias. Then same, we access to the data, and then we're going to use a method, which is the fill underscore method, which, as you might have guessed, is used to fill the tensor of bias with zeros. Well, with zeros, we have to specify that we want to fill it with zeros here, and so that's why I'm inputting here 0. Alright, so to summarize, we generate some random weights inversely proportional to the size of the tensor of weights, and we initialize the bias with zeros. Alright, so that was for the initialization of the convolution connections. And now we need to do the same for the full connection. And so we're going to add a new condition, elif. Same, we take this trick we used first, class name, that is this variable that contains the different names of the connections. So if class name dot, same we use the find method, to which we input in quotes, this time a full connection, that is a classic linear connection in a classic artificial neural network. And so the name for that is linear. And same, we're going to use this trick to say that we want it to be different than -1, so that this elif class name find linear different than -1 means if the connection is linear. That is, if we have a classic full connection. So in that case, how are we going to initialize the weights? Well, it's going to be quite the same. We're going to introduce a weight shape variable, which will not erase the first one because we will either be in this case or that case, so it will not be the same, so we can totally reuse that. Then, same, we're going to introduce a fan-in variable, which this time will not be equal to the product of these 3 dimensions, but actually this time it will be equal to simply the dimension 1. And that's because for the full connection, there is less connections than in a convolution connection. You know, you saw this in the intuition lectures, in the ANN and the CNN section. There's less dimension for a full connection than for a convolution. So basically we just take this dimension 1 here, then same, we're going to have a fan out variable which we'll then use to compute W bound, and this fan out dimension is going to be weight shape of index 0, that is the dimension 0. Alright, then to compute W bound it's going to be the same. It's going to be the square root of 6 divided by the sum of fan in and fan out. So there we go. And then the good news is that it's exactly the same as previously. We use the uniform function for the weights and the fill function for the bias to get the same kind of initialization, but this time with a different fan in and fan out, and therefore a different W bound. So that's the same principle, that's the same idea. The only thing that changes here is that we have less dimensions for the full connection, and therefore a more simple computation of this bound of the weights here to generate these random weights. But the good news is that now it's ready. Not only this weights init function is ready, but now we have our 2 tools, and so we are ready to start building the brain. So I can't wait. This will be, of course, the most exciting part. This was just to warm up and get us ready for the big thing. So we'll take care of that in the next tutorial. Well, actually, it's going to take several tutorials, of course. We'll start by making the eyes, and then remember we'll add an LSTM to learn the temporal properties of the input. And then we'll take care of the actor and the critic. And that's where we'll use these 2 functions, normalized columns initializer and weights init. So I can't wait to do that. We're going to make something very powerful now, so get ready for it. Until then, enjoy AI. Hello and welcome to this tutorial. I'm super excited because we're about to make the A3C brain, that is the brain of our AI. And speaking about brains, I would like to highlight something. Remember in the first module we made a simple brain with only fully connected layers. Then in the second module for Doom, we made a brain that not only had fully connected layers, but also eyes, because we added the convolutional layers, which gave eyes to the AI because it could observe the images and understand what's going on inside. And now we're going to take it even at a high level, because we're going to make a brain that not only will have eyes and fully connected layers, but also memory. Because as I said in the previous tutorial, we're going to add a recurrent neural network inside this big brain, and that will give a long memory to our brain so that it can understand the temporal relationships, the temporal properties of the input images. So there we go, an even more powerful brain. I can tell you that the model we're about to implement right now is really, really powerful. And we can see how building AIs and doing deep learning, doing deep reinforcement learning is all about getting closer and closer to how a human brain works. You know, we started with the basic relationships of the brain with the linear full connections, then we added eyes, then we added the memory. Who knows what we're going to add in the future models? You know, in 2018, maybe they will add something that will make the brain look like even more like a human brain. But already with fully connected layers, eyes, and a memory, we have already a really good and functional brain. So let's do it. Let's make this brain. So as usual, we're going to make a class for that because it's going to have a lot of properties with the convolutions and the LSTMs. So we're going to make an init function to initialize all this, create all these connections, and then of course we'll have the forward function that will of course propagate the signal inside the brain so that we can get eventually the output. All right, are you ready? Let's do this. So class, we introduce a new class which we call actor critic, because of course I'm talking about brains here, but let's not forget that we're making the A3C model, which is based on the actor-critic principle with separately the actor and the critic. So we will make actually one linear full connection for the actor and one linear full connection for the critic. You'll see how we will do that. It will be actually quite simple. So actor-critic and this actor-critic class is going to inherit from the nn.module so that we can use all the PyTorch tools. So let's do this. To inherit from the nn.module, well, we need to take first the torch library, then dot, then nn, then dot, and module. All right, so that way we inherit from it. All right, so there we go with our first function, which will be, of course, the init function. So we start with init, double underscore. Then this init function is going to take as argument self for the object. Then the input shape, that is the dimensions of our input images, and we call it num input. And the action space, which is basically the space that contains all the actions. But also, you know, from this action space, we can get the number of actions, that is the number of possible actions, which we will actually get very soon. So that's why we also need it. So that's for the arguments, that's all we need. And then let's go inside the function and let's create all the variables proper to our brain. But before we do that, remember what we have to do to activate in some way the inheritance, so that we can use all the tools from the nn.module. We have to use the super function this way, inside of which we input actor critic, that is our class, and then comma self for the object. All right, then dot, and there we go again with the init function. There we go. That gives us all the tools that we'll need from Torch to build our brain. All right, then, well, it's time to make the eyes of the AI, that is the convolutions. So we're going to do it very quickly because we already explained this in details for Doom, because remember the AI for Doom had eyes. So it's exactly the same. We're going to make some convolutions, and we will use a very simple architecture with 32 feature detectors of size 3 by 3, a stride of 2, and a padding of 1. So that's a pretty classic architecture, but that will actually be enough to, make sure that the AI understands what's going on in the breakout game. All right, so let's make those convolutions. So we start with self, because the convolutions will be variables of the object. So self.conv, we can call it conv, and there's going to be 4 convolutions, so I'm calling this one conv1. And there we go, we take the nn module, dot, and then we take the conv2d class, because actually conv1 will be an object of this class. And then inside, first we input the input shape of the images. So that's exactly what we have here. So we can copy this and enter it as the first input. Then the second argument is the number of feature detectors, or also the number of kernels. So we're going to take 32, as we just said, classic choice. Then we need to choose a size of the kernel, that is the number of cells that will slide over the input image. And so remember, we can either take 3, 4, 5, that's common choices, and here we're going to choose 3. And then we're going to choose a stride of 2 and a padding of 1. There we go. So that's for the first convolution. That goes from the input image to the first convolutional layers composed of 32 convoluted images. So now we're ready to make the second convolution. So it's actually going to be almost the same. So I'm copying this line and pasting that below, but pasting it below again and pasting it one last time, because we're going to have 4 convolutions with almost nothing to change. So we can already replace here conv1 by conv2, conv1 by conv3, and conv1 by conv4. That will be our 4 convolutions. And now, of course, we need to change some things here, but not much, because we're going to keep a stride of 2 for each and a padding of 1. They will all have 32 feature detectors, that is 32 output convoluted images. But then here, remember, this corresponds to the left part of the convolution. So actually that corresponds to what was at the right part of the previous convolution. You know, remember it's like a domino, so it's really easy. And therefore here we have to input 32. And here as well. We're going to see it very easily. 32 and 32. All right, so to sum up, we start with our input images that has num inputs dimensions. With the first convolution, we get 32 convoluted images, each one detecting a specific feature. Then from these 32 convoluted images, we apply the second convolution to get 32 new convoluted images. Then same, from these 32 new convoluted images, we apply the third convolution to get 32 new convoluted images again. And then eventually, from these 32 convoluted images, we apply the fourth convolution to get features. Alright, and this will be enough. With this, our AI will have a supervision. It will detect the ball very well. Alright, so that's it for the convolution. So that's it for the eyes. And now, let's take care of the memory. This new feature of this brain we're implementing, as opposed to before with Doom. Not only it will have a supervision, but also it will have a super memory, a long memory. Because we're going to implement an LSTM, long short-term memory, which is this kind of recurrent neural network that gives to your model some kind of a long memory so that it can learn some long temporal relationships from the past. So same, we're going to create a new variable. So I'm starting with self, and this new variable, we're going to call it simply LSTM, because this will correspond to the LSTM network inside the brain. So LSTM. And now, before we write the code for the LSTM, let's make sure we understand what this LSTM part of the brain will do. So, as we understood, this LSTM is used to learn the temporal properties of the input images. So for example, if the ball hits a brick, the LSTM will encode the bounce. So that's the first thing to understand. It will kind of encode what's happening in the game. Then, the next important thing to understand when we implement an LSTM is that we need to choose an order of the temporal dependencies. And here, since we're going to feed our neural network with a sequence of 4 images, then that means that we can already learn some temporal dependencies of order 4. That is, some temporal dependencies where what happens at time t plus 1 depends on what happens at time t, t minus 1, t minus 2, and t minus 3. So that we can definitely do that. But the good news is that we're going to use an LSTM, and therefore we will be able to learn some even more complex temporal relationships. That is, for example, we can learn some temporal properties where what happens at time t plus 1 will depend on what happens at time t, t minus 1, t minus 2, t minus 3, down to t minus n. And that's the long part in the LSTM, long short-term memory. With this LSTM, we can learn some very complex temporal relationships. Alright, so let's add our LSTM. So to do this, we're going to use the NN module, and then we're going to add the class LSTM cell, which will create this LSTM object, which will represent the LSTM part of the neural network. Because right now, what's also important to understand is that we're making a CRNN, a convolutional recurrent neural network, and the RNN part comes after the CNN part. And therefore, right now what we need to input in this LSTM cell is first the size of the output after the convolution, so that is 32 times 3 times 3. So this 32 times 3 times 3 is actually the output after the 4 convolutions here, but that becomes the input of the RNN, the LSTM network. And now why does the output of the 4 convolutions have this size 32 times 3 times 3? Well, don't worry, it's not that direct. It's actually not a simple formula, but there is a formula to compute this number of output neurons after flattening the pooled and convoluted images of the convolutions. But if we gather the terms of this big formula, well, we get 32 times 3 times 3. I didn't want to spend too much time on this because we have a lot to do more. And besides, we already made a function to compute this number. Remember, it was for Doom when we made this count neurons function. So you can reuse it if you want, if you're not convinced, but that is just what we get after gathering the terms of this big formula computing the number of outputs. So that's for the first argument. And then the second argument is going to be the number of output neurons of the LSTM. And we're going to go for 256. Okay, and so what does that mean now? That means that now we have a vector that encodes each event of the game. Or in other words, we have an encoded state. And so that is now that we can make the separation between the actor and the critic. Because we're going to make actually two separate neural networks, one for the actor and one for the critic, but there will be the same encoding of the images and the temporal relationships for these two neural networks. So this is the common part that we do for these two neural networks. This will be the same beginning for the two neural networks. But now things are going to change for the actor and the critic, because we're going to make one linear full connection for the actor and one different linear full connection for the critic. So let's take a quick break and let's do that in the next tutorial. Until then, enjoy AI. Hello and welcome to this tutorial. Alright, so after we made these 4 convolutions and the LSTM, we now have an encoded state that is going to be the input of these two neural networks that we're going to make for the actor and the critic. And speaking of them, the only thing that we have to do now is just create 2 linear full connections, one for the actor and one for the critic. But before we do that, we need to get the number of possible actions. And so I'm going to call a new variable here that is not going to be a variable of the object. So I'm not going to use self here, but I'm going to create the variable num outputs, which will represent the number of possible actions. And to get it, well, we can get it from the action space. So we take our action space, which will be the input of the init function when we create the object, and then we add dot n to get this number of possible actions. And now the actor and the critic will take separately the same input, that is the output of this whole process here with the convolutions and the LSTM. So it will take the same input, which is an encoded state, but then they will have 2 different linear full connections so that we get eventually actually 2 neural networks, one for the actor and one for the critic. So let's make these 2 separate neural networks, but since we already did the big job with the encoding here, well, what we simply need to do is just create 2 objects, one linear full connection for the actor and one other linear full connection for the critic. And so that's exactly what I'm going to do. I'm going to create 2 objects now. A first object for the linear full connection of the critic, which I'm going to call critic underscore linear. And to create this linear full connection, well, you know how to do it. We simply need to take the NN module and then the linear class, to which we have to input, well, the input neurons, which are the output of all this encoding here with the convolutions and the LSTM, that is 256 neurons. So we input 256 here, and then we're going to have one output, because remember, the output of the neural network for the critic is the value of the V function applied to the input state, to the input encoded state that we made here. So if we call the input state S, that is the output of all this, well, the output of the neural network of the critic will be Vs, and therefore it has one dimension, it's just a value, and so here we input 1. And remember, Vs is what is shared among the actors so that they can get some common information that they can use to play their action in a more relevant way. Okay, so that's for the neural network of the critic. And now let's make the neural network of the actor, and therefore I'm adding here self dot actor linear, and same, we already have the input encoded state, so now we simply need to add a linear full connection, and therefore same, we take the NN module, then the linear class, and now same, this neural network of the actor will take the encoded state that has a size of 256, so 256 here, but then the output is going to be different. Because of course, you know it, the output of the neural network for the actor are the Q values. The Q values of the input state, the one that we encoded here, and the action plate. So again, if we call this encoded state that we made here S and the action plate A, the output of this neural network, actor linear, will be QSA. And since, we have one Q value for each action, then therefore we have num outputs Q values, and therefore the output here is going to be num outputs, because num outputs is actually the number of Q values. Okay, perfect. So if you want, I can write for you output here for the critic is VS, where S is the encoded state, and for the actor, the output is QSA. All right, so that's very important to understand this distinction here, and to understand that we therefore have two separate neural networks, one for the critic and one for the actor. Okay, perfect. So we are almost done with this init function. Now the most important thing is done. The only remaining thing that we have to do is to initialize all the weights of those two neural networks and all the bias. And of course, to do that, we're going to use the two functions that we made earlier. That is the normalized columns initializer and the weights init. So let's do that quickly. It's going to be pretty easy and pretty fast. So first we're going to initialize some random weights. And to do this, we're going to apply the weights init function to our object. So here we have to take self to get our object. And to our object, we apply the weights init function. So therefore, inside, we just need to input the weights init function. And there we go. That will apply this function to our object. And by doing this, we are just initializing some random weights to get a future optimal learning of these weights. And now, what we have to do is make a special normalization for the actor and the critic. But remember, I think I told this in the previous tutorials, we are not going to set a same variance for the actor and the critic. The actor will get a small standard deviation, a small variance, and the critic will get a big one. And why do we do this? What's the purpose of giving a small standard deviation of the weights for the actor and a large standard deviation of the weights for the critic? Well, that allows to manage the deal exploration vs exploitation. That's exactly the purpose of doing this. By giving a small variance to the actor and a large variance to the critic, we will have a good management of exploration vs exploitation. So let's do this. Let's first take care of the actor. So we take self, our object, then we're going to take the neural network of our actor, which is actor linear. Then we are going to access the weights of this neural network of the actor. And remember, to access the data of the weights, we need to add .data. All right. So with this, we get the weights. And now we're going to use our function normalized columns initializer. So I'm copying this, pasting that here. And we're going to enter as argument the standard deviation we want these weights to have. But first, remember this function takes two arguments. First are the weights we want to initialize. So we simply need to take that again and paste that here. And the second argument is this standard deviation we want these weights to have. So as we said, we want a small standard deviation for the actor, and a small one is going to be 0.01. Perfect. So that's for the weights of the neural network of the actor. Now let's take care of the bias of the neural network of the actor. And therefore here we're going to do almost the same thing. We're going to copy this, paste that below, replace weight by bias to access the bias. And after data, we're simply going to add .fill, and remember, inside we input 0 because we want all the bias to be initialized with 0. So actually, I don't think this line is necessary because, as you remember, the bias are already initialized to 0 with this fill function in the weights init function. So, we're doing this just to make sure that the bias are actually initialized to 0, but I think it's already done here. But anyway, now we're 100% sure. All right, and now we're going to do the same for the critic. So let's be efficient and let's copy these two lines. Let's paste them here. And here, we're just going to replace actor by critic. Same here. And now the only thing that we have to change is just the standard deviation we want the weights of the neural network for the critic to have. And as you remember, we want this time a large standard deviation, and instead of 0.01, we will input 1. So there we go, we have a small standard deviation for the weights of the neural network of the actor, and a large standard deviation for the weights of the neural network of the critic. And of course, let's not forget to replace actor here by critic. All right, and now we're good. Cool. So now we have two remaining things to do. first is to initialize also the bias of the LSTM. And to do this, we take our object self, because the LSTM belongs to our object. Then we take our LSTM, then dot, and then we're going to get the two types of bias that are in the LSTM. That's bias underscore IH, and the other one is bias underscore HH. So that's the two types of bias in the LSTM. And same, they're going to be initialized to 0. So first we access to the data, and then we use the fill underscore function to fill all these bias with zeros, initialize them with zeros. All right, and now for the second group of bias, we add here the same, but we replace IH by HH. All right, so that initializes the bias of the LSTM with zeros. And now the last thing we need to do is to use a method that is inherited from the NN.module. That is the train method, and basically that is just a method that puts the module in train mode. So what's the use of it? Well, the use is that it allows to activate, if there is any, the dropouts and the batch normalizations. And so to use it, we just add self.train, and that puts the module in train mode. Perfect. So we're done with the init function. We have our convolutions, we have the LSTM, we have our two separate neural networks for the critic and the actor, and all the weights and bias are well initialized. So that's all good. We are ready to move on to the next step, which is to make the forward function that will of course forward propagate the signal from the very beginning with the original input images throughout all the brain until we get the output. So let's do that in the next tutorial, and until then, enjoy AI. Hello and welcome to this Python tutorial. Now we're going to make the forward function that will forward propagate the signal through all the brain from the very beginning with the input images up to the output, which will contain the Q values for the actor and the V value, that is the value taken by the V function, for the critic. So it's going to be quite similar as what we did for Doom, but this time something is going to change. A main thing is going to change is that now we have an LSTM in the brain. So we will have to do something more to propagate the signal, and be careful with that. And the other thing, less important, but still that changes compared to before, is that we're not going to use a ReLU activation function, as you know, the nonlinear activation function, but we're going to use the ELU, which is kind of a more sophisticated ReLU function. We will see that in the PyTorch documentation. So let's do this. Let's make this function. We start with a def. It's actually the last function of this actor critic class. So we're going to call it forward, like last time. And this forward function is going to take self, the object, because we're going to use the object, and the inputs. So important to understand, what will these inputs be? This will not only be the input images, these inputs will also contain the hidden nodes and the cell nodes of the LSTM. So that's why I wanted to highlight that some things are going to change now. Basically, we're considering in the forward function the hidden nodes and the cell nodes of the LSTM. And speaking of them, now what we're going to do is separate these two inputs of this argument inputs in the forward function. And how can we separate them? Well, we can recall a new variable which will be the inputs images. So that's this time the input images. And we separate them with the tuple hx and cx, which is the tuple of the hidden states and the cell states of the LSTM. So hx are the hidden states and cx are the cell states. Alright, and that will be equal to the input, that is this argument here. So now we make this separation, and therefore we can start to propagate the signal throughout the brain. And to do that, we are going to get successively the different layers from the first one to the last one by using our connections, that is the convolutions, the LSTM connection, and the linear connection here, the full connections. So let's do this. Now it's going to be the same as before. We're going to get our first layer that we're going to call X. And to get this first layer, we need to propagate the signal from the input to this first layer, and therefore we need to use the first convolution, because it is this first convolution that propagates the signal from the input images to the first layer. So what we're going to do now is copy this, because this is the first convolution. We paste that here, and we apply this first convolution to our input images, which are now the right inputs. And there we go. That propagates the signal from the input images to the first layer. But now, remember, we have to use a nonlinear activation function to break the linearity in order to be able to learn the nonlinear relationships inside the images. And to do this, we are going to use, as we said, the elu activation function that we're about to see right now in the PyTorch doc. But before that, let's get it. So to get it, it's like relu. We take the functional module, which has the shortcut f, then dot, and then elu. And then we put all this in parentheses because we want to non-linearly activate the neurons of this first layer here that we obtained by applying the first convolution on the inputs. So now let's go to the PyTorch doc to understand what elu is. Here it is. So you can access it to pytorch.org/doc/nn.html, and then you have to find nonlinear activations. And in the nonlinear activation functions, you will find, well, relu. That's the classic one we know. So it's just a max of 0 and x. You have the graph in mind. Then you have relu 6, which is this one, so a little more sophisticated. And there we go, we have elu. And as you can see, elu is a relu plus an additional element. So it's like a more sophisticated relu. And so that's the one we use to non-linearly activate the neurons in the different layers. And by the way, this elu activation function is called the exponential linear unit. So there we go, we applied the elu on the first convolutional layer, and now things are going to be easy. We're going to proceed to the next forward propagation of the signal, which is from the first convolutional layer to the second convolutional layer, which we are going to call x, because basically we're just updating x. Now x is the first convolutional layer, and by propagating the signal from the first convolutional layer to the next one, x will become the next convolutional layer. And so to propagate the signal from the first convolutional layer to the second one, we can simply copy this and paste that here and replace conv1 by conv2. And now, of course, the second convolution is not applied to the input images, but to x, that is the first convolutional layer, which is right here. All right, perfect. Now we get our second convolutional layer. And now let's propagate the signal again from the second convolutional layer to the third one. And therefore we can directly copy this and paste that here and replace conv2 by conv3. There we go. And last one, now to propagate the signal from the third convolutional layer to the fourth one and last one, we can just copy this again, paste that here and replace conv3 by conv4. There we go. So let's recap. We start with our inputs. We apply the first convolution to get the first convolutional layer. Then we apply the second convolution to the first convolutional layer to obtain the second convolutional layer. Then we apply the third convolution to the second convolutional layer to obtain the third convolutional layer. And finally, we apply the fourth convolution to the third convolutional layer to obtain the fourth convolutional layer. And that's how the signal is propagated throughout the eyes of the AI. So there we go, we have now the output signal after the 4 convolutions. And now you know what to do. We need to expand this whole output signal in one dimensional vector. That's the flattening step. So we're going to update x again. X now will become this flattened one-dimensional vector. And to do this, that's the same. We need to take x, which is so far the 4th convolutional layer, x dot, then we use the view function, and we first input -1 to say that we want a one-dimensional vector. And then as a second argument, we need to input the number of elements in this vector. And that is, remember, 32 times 3 times 3. And therefore, we input here 32 times 3 times 3. There we go. Now we have our flattened vector, and the flattening step is done. Perfect. Now let's take care of the LSTM part. So as you understood, the LSTM takes as input the flattened vector, this one-dimensional vector of 32 times 3 times 3 elements. So it's already ready and well prepared for the LSTM. The LSTM is now ready to take this flattened vector as input. And therefore, we can take our LSTM and input as argument first x, our ready flattened vector, that is this x right here that we just expanded. But also, and that's where this tuple comes into play, we need to input hx and cx. And we can use hx and cx here because we made that separations from the original input argument of the forward function. So LSTM_x, the flattened output vector after the 4 convolutions, and this tuple of the hidden and the cell nodes. So there we go. Then we must not forget the self, because LSTM is a variable of our init function, so a variable attached to the object. So self.lstm, and this will actually return 2 outputs, a tuple of 2 outputs, which will be the output hidden node and the output cell node. So it's actually a tuple, and therefore we can update hx, the hidden node, and cx, the cell node, because that's exactly the output of this LSTM here. Great, so we're almost done. Now that we have the outputs of the LSTM, we need to get the useful output, because actually only the hidden nodes are useful, and therefore we're going to get it by updating x again, and x will now be equal to hx. It's the first element of the output tuple of the LSTM. X equals hx, and we're almost done. Remember that we have 2 brains, one brain for the actor and one brain for the critic, and therefore we have 2 output signals to return. The output signal of the actor and the output signal of the critic. And therefore, now what we're going to do is return these 2 output signals. And how can we do that? Well, that's very easy. We simply need to take our linear full connections, but separately, that is the linear full connection of the critic and the linear full connection of the actor. And we apply each of these full connections to the output x, that is the useful output of the LSTM. And that will be all. That will be the output signal. So there we go, let's do it. We first take self, our object, then we get the linear full connection of the critic, which is critic underscore linear, which we apply to x, the output signal of the LSTM, and then same, we take self again, then dot, and then we take the linear full connection of the actor, which is actor underscore linear, which same we apply to x. There we go. So that's the main thing we need, but then we're also going to return the tuple of hx, the hidden nodes, and cx, the cell nodes, because we will be using them later in the retro loop of the LSTM. Alright, perfect. So now we're done with the brain, or should I say the brains, because we actually made 2 brains, one for the actor and one for the critic. So congratulations for making the A3C brains. I hope that wasn't too overwhelming to combine a CNN and an LSTM, but at least the good news is that we're really working with the best and most powerful model. So there we go. We're actually done with this first file model.py. And so in the next tutorial, we'll take care of the optimizer, because we're going to make a separate optimizer. We're not going to code each line of code because a lot of it comes from the research papers, and this is actually pretty specific. And if we go into the deep details of what's going on with this optimizer, this might be a little too overwhelming for what's going to happen next, because we still have the train function to make, which will be a huge function, and that contains the algorithm of the A3C. So trust me, you want to keep some energy for that, and therefore we will not spend too much time on this, but still I will explain the code and you will understand the whole idea behind this optimizer. So congrats again for making this actor-critic class, and I'll see you in the next tutorial to make the optimizer. Until then, enjoy AI! Hello and welcome to this tutorial. Alright, so in the previous tutorials we made the brain, or if you want the brains for the A3C. Now we need to train this brain, but in order to train these brains we need an optimizer. That's this tool we'll use in stochastic gradient descent to update the weights according to how much they contribute to the error between the predictions and the targets. And what we did up until now in the first and second module, we used the Atom Optimizer by Torch in the training. But as I told you, we are dealing with a very challenging problem, that is breakout, and the A3C algorithm by itself is not enough to solve this problem. We need some customized optimizers and a lot of different tricks to solve this problem without waiting for ages. So that's the purpose of doing this, and that is why we have a separate custom optimizer based on the Atom Optimizer, and that is contained in this shared Atom class. And why shared Atom? It's because it is actually the Atom Optimizer, but that will work on shared states. So we're going to explain how it works in this tutorial. So we're going to go through the different functions here without coding them, because we want to keep some energy for the next implementation, that is the train.py file, which will take more than 100 lines of code. So be ready for that. And therefore, we will try to explain what's going on here in one tutorial, this tutorial, and let's start right now. Alright, so first we introduce this class shared atom that will contain three functions: the init function, the shared memory function, and the step function. So what we do first is that we inherit from optim.atom, which is of course the atom optimizer, and that we get from the optim module from the torch library. So here we apply inheritance to get the tools all related to the atom optimizer. And then we start with the init function. So what happens here? First, we use the super function to inherit from all the tools and all the basic parameters from the optim.atom class. And these basic parameters are here: params, learning rate, betas, epsilon, and weight decay. And then we start a for loop. This first for loop for group in self.param groups. So first, what is param groups? Self.param groups contains all the attributes of the optimizer. And among these attributes, we have the parameters that we have to optimize. These parameters that we want to optimize are the weights of the network that are contained in self.param groups params. So there we go, group belongs to self.param groups, and here we have this second for loop, which will get these parameters that we want to optimize and that are exactly contained in self.param groups params. So basically, we go through self.param groups that contains all the parameters, and for each group of parameters in self.param groups, we are going to go through the parameters that we want to optimize. Therefore, for P in group params here means for each tensor of weights that we want to optimize. So for each tensor of weights that we want to optimize, and then what happens inside this loop with these 4 lines of code, basically what happens is that the update made by the atom optimizer is based on an exponential moving average of the gradient. So that's this line of code here. That's the exponential moving average of the gradient of moment 1, that is of order 1. But the update made by atom is not only based on that, it is also based on an exponential moving average of the square of the gradient. That is an exponential moving average of the gradient of moment 2, or order 2. So here is the exponential moving average of order 1, and here is the exponential moving average of order 2. For each of them, the EMA of the gradient. So that's what happens here. And now, if you want to get more in depth of how the exponential moving average works, well, I highly encourage you to have a look at this research paper, Atom, a Method for Stochastic Optimization, because basically, the atom optimizer that we're implementing right now is based on the algorithm 1 here. So if you want to have more details on how the algorithm works, well, this paper will be definitely helpful. And then you have some further explanations on the algorithm with the atoms update rules. And so you know that's only if you want to attack this before attacking the big train function that we'll make afterwards. Okay, so let's go back to Python. And now let's move on to the second function, share memory. So now I'm just going to say a few words. The idea of this share memory function is kind of like tensor.cuda. You know, CUDA is an accelerator based on the GPU. And so basically what happens here is that we have these tensors of the states dot share memory, here, here, and here, that behave a little bit like tensor.cuda. So, you know, accelerate the computations. But the difference is that here, the tensors.share memory send the computations to a part of the GPU or the CPU that is accessible to all the parallelized threads. So that's basically what is done here. That's a little bit like tensor.cuda, but it's only sent to a part of the GPU or CPU accessible to the parallelized threads. All right, and then we have the last function, step. So you know this function, it's like the step method of the atom optimizer that we already used in this course. And so again, this is based on the algorithm 1 of the same paper that we saw before. So this algorithm. So again, if you want to understand in details the following lines of code, well, again, I encourage you to have a look at this algorithm 1 by this paper. And besides, what is done here is not totally compulsory, because this is actually a copy-paste of the step method of the optim.atom class. So basically what is done here, we could have done it by using our inheritance, because here we inherit from optim.atom. And so to use our inheritance, well, what we can do instead of doing all this is just, I'm going to write here as comment, is just use the super function that we apply to our shared Atom class, then our object self, and here we just add step with parentheses. Step is the method of the optim.atom class. And that's exactly the same. That's why I was just saying that here is just a copy paste of the step method of the optim.atom class. So I think that if you replace all this by this super function applied to share atom and the step method, well, we might get exactly the same thing. Alright, so that was interesting to have a quick look at it. Basically, you can see this as the atom optimizer. It's like we had a deeper look at it. But again, if you want to go in more details of all this, and if you want to understand what happens behind the scene, well, I encourage you to have a look at this research paper. I'll put the link in the comments here. Remember you will have all the code commented in great details, so it's really good if you can have a look at it. And now, I hope you have some great energy because we are going to move on to the train file, which will contain this huge train function, and that will basically train our brains, which now we can do because we have our optimizer. So have a good break now, have a good sleep, and whenever you feel in great shape, let's move on to the next step. Until then, enjoy AI. Hello and welcome to this tutorial. Now we have the brain of the model, we also have the optimizer, so basically we're ready to train our different agents, that is, our different brains. So that's from now that we will make this big train function, which will contain all the A3C algorithm, and therefore, what we're about to implement in this train.py file is just this huge train function. There will just be this big train function, nothing else, no class, but we will use this train function in the last step of this module with the main code. So there we go. But before we start, you can notice that, well, first we import some libraries. So that's the classic libraries with the torch module, the torch library. Then the ends library to create the Atari environment, which will be breakout. Then we will, of course, import our actor critic class from our model file, this one. And finally, we will use variable from torch.autograd to run highly performant computations of the gradient thanks to the dynamic graphs. And then we have this ensure shared grads function, which I didn't want to spend too much time on this because, well, first, this is just a function that will make sure everything works correctly if the model used by the agent doesn't have any shared gradient. So that's why it's called ensure shared grads. And the other reason is that I don't think this function is necessary, but we never know. And at least with this, we'll be 100% sure that the code will execute properly. But that's not really important. What we must focus on is this train function that we will start making right now. So here we go, def and train. We will simply call it train. And this train function will take several arguments. The first one is rank. I'm going to explain what it is in a second. The second one is params, so that's all the parameters of the environment. Then the third parameter is going to be shared model. So the shared model is what the agent will get to run its little exploration on a certain number of steps. And then finally, the last argument is going to be the optimizer, that is the one we made earlier. So perfect, that's our 4 arguments, and now we are ready to start implementing this train function. So the first thing we'll do is, you remember what A3C stands for? It stands for asynchronous actor-critic agents. So in A3C there is asynchronous. So as you understood, we have to desynchronize each training agent. And to desynchronize them, we're going to use the rank to shift each seed with this rank. So this rank parameter here is just to shift the seed so that each training agent is desynchronized. So for example, if there is n training agents, then the ranks will go from 1 to n, and there will be 1 integer per agent from 1 to n. So when we shift the seed by 1 thread, all the pseudo-random numbers created by the thread will be totally independent from the other threads. However, the seeds are fixed numbers, so when we reproduce the experience, we will find exactly the same events. And that's because it's deterministic with respect to the seed. So it's important to understand that, and that's why the first thing we need to do is to desynchronize each training agent by using the rank here to shift the seed with the rank. So let's do this. To do that, we're going to take our torch library. Then we're going to get the seed with manual underscore seed, parenthesis. This is a function. And now we're going to take the seeds of all the agents, which we can access with params.seed. And to shift them by the rank, to desynchronize each of these agents, we will just add here plus rank. And that will shift the seed with the rank to desynchronize each training agent because there is one seed for each training agent. All right, first thing done. And now next step. The next step is to get the environment. So we're going to create a new variable that we're going to call env. And now we will use the create Atari env function from the env module to create the environment for breakout. That is to get the environment of breakout. So we take this function, create Atari env, and now we have to input just one argument, which are the parameters of the environment. And we have them because this is one of the input of the train function. This is this params here, which will be the parameters of the environment of breakout. And therefore, to get the breakout environment, we take this params argument, then dot, and then we get env name, which in the future, that is in the next code with the main function that will execute the whole code, will be breakout v0. All right, so that gets us the environment, perfect. And now, next step is to align the seed of the environment on the one of the agents. And why do we do that? It's because, remember, each agent of the A3C model has its own vision of the environment, like its own copy of the environment, and therefore we need to align each of the agents on one specific version of the environment. And to do that, we're going to use the seed, because each seed determines a specific environment. So by associating a different seed to each agent, well, we'll get exactly what we want, that is, that each agent will have its own environment. And so how can we do that? We can take our environment, then add dot, then use the seed function to choose the seed we want to get for the environment. And so now to align the seed of the environment to the seed of the agent, well, we simply need to get this, because this corresponds to the seed of the agent that was shifted thanks to rank to get desynchronized training agent, because they're all on a different seed. So we just need to paste that here, and this will align the seed of the environment on the one of the agent. Okay, now we are going to get our model, that is our A3C brains, and so that is now that we're going to use the actor critic class from our model file. So we are basically going to create an object of this actor critic class, and we're going to call this object model, or brain if you like. But basically this object will contain all the convolutions, the LSTM, the linear full connection, and the forward function to propagate the signal. So it will basically contain the brains of the actor and the critic with the ability to propagate the signal throughout the brain to get the final output. So let's do this. Let's create our model. So as we said, we want to call this object model. And so we create an object of the actor critic class. And therefore we take our class, actor critic. And now remember what arguments we need to input. That's actually the arguments of the init function. So self, we don't have to input it. That's what we have to do to use the object in the init method. But then the arguments we have to input are num inputs, which is the input shape, that is the dimensions of our input images, and the action space that contains, the set of actions. So let's input these arguments in the train function. So the first one, we can get it with our environment and dot, and then we use observation space. So that's the space of observations, then dot, and then to get the number of inputs, we get shape bracket 0. All right, so that's for num inputs. And now for action space, well, that's almost the same, but we need to get it from our environment that we already imported, then dot, and then action space. All right, and that gives us the arguments we need to input when creating an object, the model of the actor critic class. Okay, so now we have our model, and now the next step is to prepare our input states. So remember, we're still doing deep reinforcement learning, so the input states are the input images, and therefore this will be originally a NumPy array, which will contain one channel because we will work with black and white images, and it will have dimensions of 42 by 42. But it's important to understand and to keep in mind here that the input states are the input images. So first what we have to do is to get the NumPy array. Then we will convert it into a torch tensor, but the first step, as what we did previously, is to get the NumPy array. And to get it, it's actually quite simple. Well, first we need to create a variable for the input state, which we will call state. And this, to get the NumPy array, we simply need to take our environment and then add dot and then use the reset function. And this will initialize state as a NumPy array of dimensions 1 by 42 by 42. 1 means one channel, so black and white image, and 42 by 42 is of course the dimensions of the image, the number of pixels on the width and the number of pixels on the height. So basically that's just the dimensions, and that's the ones we'll work with. And now that we have this actually NumPy array, because this will get us these images of such dimensions in NumPy arrays, now we can convert them into torch tensors. And to do this, well, we're going to update state again because we don't need to keep the NumPy arrays. And that's where we use torch, the torch module. And remember, we already did that for Doom. We use the function from underscore NumPy parenthesis. And inside this function, we need to input the NumPy array to which we want to convert into a torch tensor. And that is the state. The previous version of the state in NumPy array will become, by applying the from NumPy function, a torch tensor. So that just creates a tensor from the state, and now we just need to initialize the done variable. Remember, the done variable is generally the variable that says if an episode is over or if the game is over. While here we just want to introduce this done variable and initialize it to true to specify that this done variable will be equal to true when the game is done. So that will be useful for later, so that the AI doesn't play indefinitely to breakout. Alright, so that was basically the beginning of this train function with some initialization and some things that we have to do. The most important part here was that we have to desynchronize each training agent, so that's one first principle of the A3C model we have to apply. And now in the next tutorial we will proceed to the synchronization with the shared model. Let's not forget that there is the different models, but also the shared model, which is a model that all the agents share. And so we have to synchronize with this shared model so that each agent can get this shared model to proceed to a small exploration of a certain number of steps. So that's what we'll do in the next tutorial, and until then, enjoy AI! Hello and welcome to this tutorial. In today's tutorial, we are going to synchronize with the shared model. So what we're going to do is still saying the function, of course, and then initialize the length of one episode. So we're going to call the length of an episode underscore length. There we go. And we are going to initialize it to 0, but then this episode length will be incremented. And speaking of incrementing it, that's exactly what we'll do. So we're going to use a while loop and use this trick to say while true, colon, to repeat what's going to happen now, what's going to happen inside this while loop. And so the first thing that's going to happen in this while loop is this incrementation of the length of an episode. So the first thing that we're going to do is increment it by 1. And to do so, we can simply take episode length and add here plus equals 1. And now we are going to synchronize with the shared model. That means that it is now that the agent will use the shared model to do its little exploration on a certain number of steps. And how is the model going to get this shared model? Well, we need to take our model, then dot, and then use the load state dict method, because we're going to use it to get the state dictionary of our shared model. So we have to put the shared model first and apply then the stateDict method to get the parameters of this shared model. And that's how our model here will get the shared model to do its little exploration. Okay, and once the model gets this shared model, now we have to distinguish two cases. The first one is if done, meaning if the game is done. So if the game is done, then what happens in that case? Well, we have to reinitialize the hidden states and the cell states of the LSTM in the model. And so that's why now I'm going to take CX, the cell states, and also HX, the hidden state, and I'm going to reinitialize them both. And how are we going to reinitialize them? Well, with only zeros. There will be a vector of 256 zeros, because remember the output of the LSTM has dimensions 1 and 256. So there we go, we're going to initialize them by using the torch library, then the zeros function, and since we want a vector of 256 zeros, we're going to input here the dimensions 1 for the vector and 256 for the number of elements, which will be zeros, and there we go. But then we will convert that into a torch variable, because then some gradients will be computed, so we need to integrate this with a gradient. Alright, and we're going to do the same for the hidden states just below and reinitialize them the same way. There we go. So that's if the game is done. And now the other case, which we can access with else, then what happens in that case? Well, we're going to keep the old cell states and hidden states. And so very easily, we can keep the old ones this way by typing cx equals variable cx.data. And same for the hidden states, we can simply add here hx equals variable hx.data. Alright, good thing done. Now we can get out of the else, because we're basically done with these two cases, whether the game is over or not. But we stay in the while loop, because now we're going to do some more things, which basically are all the training process. And so what we're going to do now is initialize several variables, which are going to be at the heart of the computations in the training. So let's do this. We're going to need the values, which remember is the output of the critic. So that's the v function. And we will initialize them as an empty list this way. Then we're going to need the log probabilities. So log probs, and we will also initialize it as an empty list. Then, of course, we're going to need our rewards that we will also initialize as an empty list. And finally, we're going to need the entropies. Something new, but this is indeed at the heart of the training computations. So empty list as well. So now that we initialize these four variables, we can start a new for loop. And in this new for loop, we will update the values of these four variables. And so this new for loop is going to be a for loop over the exploration steps. And therefore, the looping variable is going to be our steps. So for step, in, range, and inside, we can directly input params.numSteps. Because params.numSteps is exactly the number of steps of the exploration. So for all the steps in the exploration, what do? Well, we're going to get the predictions of the model. You know what is returned by the model. And to get these predictions, we can simply take the model and apply it to the input. So that's the input signal. It goes through the brains in the model, and that will get us the outputs. But it will get us several outputs, you know. It will get us the values of the v function, which is the output of the critic, then the q values, QSA, which is the output of the actor. But also don't forget that it will also output the tuple of the hidden states and cell states, because remember, if we go back to our model, well, in the forward function, we can see that indeed it returns the output of the critic, that is the value of the v function, vs, then the output of the actor, which are the q values QSA, and also the output of the LSTM, which is this tuple hx and cx, the hidden states and the cell states. So we must be careful with that. This is quite different than what happened before. And therefore, we're now going to apply the model to the input, which is the state, but now there are several things to do, which are related to torch, but that gives, of course, power to what we're doing. The first thing we need to do is to unsqueeze the state to add this fake dimension that must have the index 0. So that's because the model can only accept a batch of inputs and not an input by itself in a vector or a tensor. So that's the first thing we must do, the unsqueeze. But then that's not all. We need to convert our input state into a torch variable. So I'm adding here the variable So now we're okay with the state, the input state, but remember that the inputs of the forward functions are actually the input image, so that's what we just took care of, but also this tuple of hx, the hidden states, and cx, the cell states, and therefore we need to add here this second part of the input with the tuple of hx and cx. Alright, and we must take care of the parenthesis. There we go, we have our two inputs. The first one is the input state, that is the input images, all converted into a torch variable and unsqueezed to add this fake dimension of the batch, and this tuple of the hidden states and the cell states. So we're all good to go, we are ready to get our predictions. And now, since this return, well, our three predictions, the output of the critic, the output of the actor, and the tuple of the hidden states and the cell states by the LSTM, well, we're going to introduce some three new variables now, which will be these three outputs. So there we go. The first output is the value of the v function, which is the output of the critic. So we're going to call it value. So there we go. That's the first output. Then the second output is going to be the output of the actor, and that's the Q values, QSA. But since the Q values are associated to the actions, we can also call them the action values. All right. And then final output returned by the model, that's the tuple of the hidden state, hx, and the cell state, cx. And there we go, we have our three outputs returned by the model. Perfect. So now that we have the predictions, we need to use a softmax to play the right action. And so now that's going to be exactly the same as what we did before. The next step is to get our probabilities, so we can call them prob. And that's where we use the softmax method, which we take from the functional module that has the shortcut f. So f dot softmax, and that will generate a distribution of probabilities of the input that we're about to input right now, and which are of course the action values, that is the Q values, that is the output of the actor in the model. Okay, so now we have our probabilities, but as you noticed, we're going to work with the entropy. And to get the entropy, we not only need the probabilities, but also the log probabilities, because the entropy is the sum of the product log prob times prob, all this multiplied by -1. And so we also need to get our log prob, which same are going to be generated from log softmax. So instead of taking a distribution of the probabilities, we take a distribution of the log probabilities, and that we do it with log softmax, the log softmax function, to same we apply to the Q values, which we call the action values. All right, so now we have the prob and the log prob, and so we're ready to get the entropy. And the entropy, what is the formula for that? Well, as I just mentioned, we take the log prob, we multiply it by the prob, then we're going to take the sum of all this, and to do that we can add here dot sum 1. We actually use this trick many times now. And as we said, we multiply all this by -1. So it's the minus of the sum of the product log prob times prob. Perfect. And now we are going to store this entropy that was just computed in our list of entropies. Because there we go, we have the last computation of the entropy, and so we need to store it in the entropies list. And to do this, nothing more simple, we're going to use the append function, of course, because entropies is a list. So we take our entropies list, then dot, and we use the append function to add the entropy that was just computed. Alright, so we're going to take a break now. We're going to do this step by step. In the next tutorial, we will play the action by taking a random draw of this generated distribution of probabilities. And after we play the action, we will get the value of the state. And we will eventually store our new transition, state, reward, and done. So that will be a new big step done, and we will complete that in the next tutorial. Until then, enjoy AI. Hello and welcome to this tutorial. Okay, so we just computed the entropy and added it to the entropies list. And now what we're going to do is take a random draw of an action according to the distribution of probabilities of the softmax. So let's do this. That's the next step. We are still in the loop because we're still running on the steps here. And so you now know how to play the action. We will first introduce a variable for the action called action. And then we take our distribution of probabilities, and we're going to use the multinomial function to take a random draw from this distribution of probabilities. And then we add .data. So it's important to note that the action will actually be a tensor with only one value, but you should not see this as a simple value. You should see this as a tensor of dimensions 1 by 1 that contains this value for the action, and that's because it is unsqueezed. And now, still in the same for loop, we are going to get the log probability associated to the action that was just played. And so I'm updating my log probability here by taking the previous one, the previous log prob that we computed here. And then I'm going to use the gather method, to which I'm going to input 1 and the action that was just played, because we want to get the log probability that is associated to this action. And so as a second argument here, I'm going to input my action, but that has to be as a torch variable as required by the gather function, and the gather function just indexes with a tensor of integer. Alright, so now we just got the log prob associated to the action that was just played, and now the next step is to append what we got to the list here. So we got the value, that's what we got here as the output of the model. Then we also got the log prob, so we're going to add the log prob to the log probs list. We already appended the entropy to the entropies list, so we're good. And the rewards, we will get it afterwards. So we will now append the value and the log prob to the values list and the log probs list. Let's do this. We take our values list, we add dot, we use the append function, and we add the value that was just returned by the model. Perfect. Then same for the log probs. We just got our new log probs, and we are going to append it to the log probs list. And so in this append function, we input log prob, our log prob that was just computed here. All right, so our lists are now well updated. So now what we're going to do is play the action, because actually right here we selected the action by taking a random draw from this distribution of probabilities here, but we actually haven't played it yet. And we're going to play it now so that we can reach the new state and therefore get the new transition. And to play it, we're going to take our environment, because we play the action in our environment. Then we're going to use the step method, and inside we specify the action that was selected to play it. And to do this, we take our action and we add .numpy, because that's what is expected by the step function. Okay, but this returns actually the new state and also the new reward, because by reaching a new state, we get a new reward, and also we get a new value for done to know if the game is done or not. Alright, so with this, we play the action, we reach the new state, and we get the new reward, and we know if we are done with the game. And speaking of being done with the game, well, we're just going to add something here that will make sure that an agent is not stuck in some state. And to do that, we're going to update the done variable the following way. Well, it's going to be equal to done, or we're going to add a condition saying that the episode of the game should not last too much time. And you will see in the main function that there will be a max episode length parameter, which will be equal to 10,000, and we don't want an episode to last more than 10,000 units. So we're going to add here episode length, which is the length of an episode, and we're going to write the condition larger than max episode length. There we go, and actually max episode length, we are getting it from our parameters. Therefore I'm adding here params dot max episode length. So this means that if the game is done or the length of the episode is larger than the maximum length of episode set, which will be equal to 10,000, well, the game will be done and we will start a new game. Okay, so that's just a precaution. And speaking of precaution, we're going to add another precaution. It's to clamp the reward between -1 and +1. We already got the reward here, but we want to make sure that the reward is between -1 and +1. And to do this, we simply need to update the reward by doing this, taking the max, then taking the min of reward and 1. And here we take the max of the minimum of reward and 1 and -1. And that will make sure the reward is between -1 and +1. Alright, so another precaution. And now we just want to check if the game is done, in which case we will restart the environment. And why do we need to check that now? It's because we just reached a new state. We just passed a new transition, so we need to check that after passing this new transition, well, the game is not done. So if done again, if done, then in that case, we will restart the environment by setting the episode length to 0. And also the state will be reinitialized. And to reinitialize it, we take our environment and we use the reset function. Okay, now we get out of this if condition. That was just a checking. And now what we're going to do is, since we reached a new state, well, this new state is right now a NumPy array, because remember, the states are the input images, which originally are NumPy arrays. And so now what we have to do is to convert the new state into a torch tensor. So we're going to update our state, and we're going to use the torch library, and of course, the from NumPy function to convert this NumPy array state, the input images, into a torch tensor. Perfect. And now the last thing we need to do before getting out of this for loop, that is the loop on our steps, well, it's to, of course, append the reward to the rewards list. That's the last thing that needs to be updated. We updated all the lists here except for the reward. So we're going to do that right now. We take our rewards and we use the append function to append the last reward that was just received. Perfect. And just before we get out of the for loop, we just need to do one last check to check that if it's done, then we want to stop the exploration. And so we're simply going to add here a break, meaning that if it's done, we stop the exploration and we directly move on to the next step, which will be the update of the shared model. And now we are done with this for loop. Now that the agent has done its exploration, it will update the shared model. And we will take care of that in the next tutorial. Until then, enjoy AI! Hello and welcome to this tutorial. So now the agent has done its exploration, and then what he's about to do is to update the shared network. So the first thing we're going to do is initialize the cumulative reward. We're going to call it R, capital R, and we will initialize it as a torch tensor, but that will have dimensions 1 by 1 because it's just a value, but we want it to be a tensor. And so I'm using here dot zeros and then 1, 1. So basically the cumulative reward is initialized to 0. Okay, then same if we're not done, that is if the game is not over. What we want right now is the cumulative reward to be equal to the value of the last state reached by the shared network. So we're going to get the value output, the value of the v function output of our model, and this is the value we will give to the cumulative reward. So let's first get this value. We can get it this way. Value, then, since we only want the value, we can add here underscore and then underscore again. And then we get our model, because it will output this value, but only the first output of the model, thanks to this double underscores here. And here we can just copy paste what we have here, that is the input of the model with the input images and the tuple of the hidden states and the self states. So I'm just pasting that, and there we go, we will get the value. And so now what we're going to do is give to R this value. So R will be equal to value, and to access to the value, we add this dot data here. All right, now the if condition is done. And now what we're going to do, since we just got a new value by, getting the output of the model, the first output of the model, well, let's already append this new value to the values lists. Therefore, we can take directly our values list, then dot append, and we input variable R, because R contains this last value. So great, that is done. Now, we are going to initialize the losses. And remember, in the intuition lectures, you have two losses. You have the loss of the policy, that is the loss related to the predictions of the agent, and then you have the loss of the value, which is the loss related to the predictions of the critic. So we are going to introduce these two variables and initialize them to 0, and therefore I'm going to take here policy, first variable, policy loss, initialize it to 0, and then value loss, the loss of the value, and same, initialize it to 0. Then let's not forget to set the cumulative reward as a torch variable, because we will need it to be a torch variable, because we will be computing a gradient with respect to it, because the cumulative reward is going to be a term of the value loss. So with this variable, it is now attached to the dynamic graphs with the gradient. And now, finally, the last thing we need to do before starting the big training loop, when we apply stochastic gradient descent to reduce this loss between the predictions and the targets, well, we need to initialize the GAE, the generalized advantage estimation, and not gated autoencoder. Be careful with that. GAE, the variable that we're about to initialize right now, is generalized advantage estimation. So as a reminder, generalized advantage estimation is by definition the advantage of playing the action A by observing the state S. So it's a function of the action A and the state S, and it is equal to the difference between the Q values QAS and the value of the V function. So actually, I can write it here. The generalized advantage estimation is a function A of the action and the state S, and that is equal to the Q values of the action A and the state S minus the value of the V function applied to the state S. That's the generalized advantage estimation, and that's what we want to initialize right now, and we will initialize it to 0. But it has to be a torch tensor, so we're going to use the same trick as what we just did right here. We are going to take the torch library and apply the zeros function to set it as a tensor of only one value, which is 0. And we are going to introduce this new variable GAE, and that will be equal to that, torch.zeros11 as initialized to 0. So this will be initialized to 0, and therefore the Q values of the action A and the state S will be equal to the value of the V function of the state S. Alright, and now we're ready to start the for loop. So we're going to have some adventure here, so take a good break, and I'll see you in the next tutorial to attack that. Until then, enjoy AI! Hello and welcome to this tutorial. Now we're going to make the for loop that will compute the policy loss and the value loss. And once we have these two losses, we will be able to use our optimizer to apply stochastic gradient descent to reduce the losses. Alright, so there we go. We start here. By the way, in the previous tutorial, we implemented this section and I forgot to remove the indent. Sorry about that. So starting from R here is not in the for loop. And now we're starting a new for loop. So I'm starting here with for. And now what we're going to do is we're going to start from the last step that was done during the exploration, and we're going to move backward in time. So that's why here I'm doing for I in reversed range len rewards, because rewards is the list, and since each step of the exploration is associated to a reward, because at each step we get a reward, when len rewards is this number of steps. And this reverse here is used so that we can move back in time. So there we go. And now what we're going to do is update the cumulative reward, that is R. And we're going to update it this way. That's actually the same as what we did for Doom. It will be equal to gamma, which we get from our parameters. So I'm taking params first. Params.gamma times R plus the reward of the step, which we can get by taking the list rewards and taking the index I. So first this will be the reward of the last step, then it will be the reward of the previous step, and etc. And each time we update R by multiplying it by gamma and then adding this reward at the step. And so by doing this, remember, we will get in the end, so I'm going to write it as a comment, we will get R, the cumulative reward, that will be equal at the end of the loop to R0, the reward of step 0, plus gamma times R1, the reward of the first step, plus gamma squared times R2, the reward of the second step, plus ... plus gamma at the power of n minus 1 times the reward obtained at step n minus 1, where n is the number of steps. But then, be careful, at the end we will have gamma at the power of number of steps times the value of the v function applied to the last state. This what we should get at the end. And this, we will get that because, remember here we got this value of the last step because this was done at the end of this for loop here. And so we got the value and we set r to be equal to that value. So right now, r at the beginning of this second for loop here will be equal to this value of the last state. But then, by doing this, this is what we'll get in the end. R equal R0 plus gamma R1 plus gamma squared R2 plus gamma at the power of n minus 1 times the reward at step n minus 1 plus gamma at the power of number of steps times this value of the last state. So that's the main thing to understand in this computation of the cumulative reward, and that's why it is important to start from it by initializing r with the value here and doing this reversed for loop to get this final equation. Perfect, and now that we have the right value for the cumulative reward, well, we will compute the advantage. And the advantage here is just the advantage of getting this reward compared to the value. So I'm going to introduce a new variable advantage, and therefore it will be equal to this cumulative reward minus the value of the v function obtained at the step I. So therefore that is r minus values I. Perfect, and now that we have the cumulative reward and the advantage, then we can get the value loss. This is the first loss we can get now, so we're going to get our value loss variable, and this will be updated the following way. Remember so far that the value loss was initialized to 0, and so we're going to take the value loss again and add 0.5 times the square root of the advantage. So we can get it this way, advantage dot pow 2, so that just means the square root of the advantage at the power of 2, and that is exactly the value loss, the loss generated by the predictions of the value of the v function output by the critic. And so it makes sense that this is the value loss because remember, the advantage a of the action a and the state s is the difference between the q value and the value of the v function, and so when we play the optimal action, well, we get the stationary state with q optimal of the optimal action a star played in the state s equals the optimal value v star of the state s. So it's quite intuitive to understand that when the advantage is not equal to 0, then there will be a difference between these two, and therefore that's how the loss is measured. Okay, so value loss computed. One loss down, we have now one more to go. It is the policy loss, and that's exactly what we're going to compute right now. And to compute it, we need to consider again the generalized advantage estimation, because to compute the policy loss, we need the generalized advantage estimation. And to get the generalized advantage estimation, we need first the temporal difference of the state values. So we have multiple things to compute here, and we're going to start with this temporal difference. Once we get the temporal difference, we will get the generalized advantage estimation, and once we get the generalized advantage estimation, we will get the policy loss. Alright, so let's start with the temporal difference, TD. So TD is equal to the reward of the step I plus gamma, which we get thanks to our params list, so params.gamma, times the value of the step I plus 1, and we add dot data to access it, minus the value of the step I, and same, we add dot data. Alright, so that's the formula of the temporal difference of the state values, and now we can update the generalized advantage estimation. And how is it updated? Well, we take our GAE and we multiply it by gamma, params.gamma, times tau, which we access with our parameters as well. So we take params tau and we add this temporal difference of the state values. So be careful, we are in a for loop, and each time we multiply the GAE by gamma and by tau, and we add the temporal difference. So it's important to understand that at the end of this loop, well, this generalized advantage estimation will be equal to the sum on all the steps of gamma times tau at the power of I times the temporal difference at the step I. Alright, so important to keep that in mind. And now that we have the generalized advantage estimation and the temporal difference, we can finally compute the policy loss. So let's do this. We are going to update our policy loss the following way by taking the old policy loss and we subtract the log probabilities obtained at the step I that we multiply by this generalized advantage estimation that we have to put in a variable, because then we will compute the gradients. So it has to be attached to a gradient in the dynamic graph. And then we add minus 0.01 times the entropy obtained at the step I in the for loop. And again, now be careful, this is the computation inside the for loop, which means that at the end of the for loop, what we will get is policy loss equals minus sum over the steps of the product log of the policy at the step I times the generalized advantage estimation plus this 0.01 times the entropy at the step I. So there we go. And now what is the policy at the step I? Well, that's the softmax probabilities of the actions. And the entropy at the step I, well, you know what it is. It's what we computed earlier and what we appended to the list. So we already have that. But this PII here is the softmax probability of the actions. And why do we put a minus here? That's because the log of the probability and the entropy are negative values. And since we want to minimize their absolute value, we must see this loss as a log likelihood as opposed to a distance. You know, we want to maximize the probability of playing the action that will maximize the advantage. That's the whole idea behind it. We want to maximize the probability of playing the action that will maximize the advantage. And for those of you who might be wondering what is the purpose of this entropy coefficient, that is this factor 0.01 here, well, the purpose of it is just to prevent from falling too quickly into a trap where we have a distribution of probabilities with zeros for all the actions except one, which has a probability of 1. And if that happens, that would minimize the entropy. So that's why we're adding this small coefficient 0.01 here that will make the entropy increase in the gradient descent. Okay, so now the good news is that the most difficult part is done. We have the two losses, and therefore what we only need to do now, and we already know how to do it, is to perform the stochastic gradient descent to reduce these two losses. And so what we're going to do now is get out of this loop, and we're going to take our optimizer, the one we made separately. Then remember, the first thing we have to do is to initialize all the gradient parameters to 0. And to do this, we add dot, then the 0 underscore grad method. All right, so that's done. Then now we're going to perform backward propagation, but we're going to give twice as much as importance to the policy loss than the value loss because the policy loss is smaller. So to do this, we're going to put in parentheses policy underscore loss plus 0.5 value loss. So 0.5 times the value loss. And we're going to add here dot, and we apply the backward method to perform backward propagation. And thanks to this trick here with the policy loss plus half of the value loss, we give twice as much importance to the policy loss than the value loss. Okay, then we're going to use another trick, which is to prevent the gradient from taking extremely large values and therefore degenerate the algorithm. And the trick to do that is to get first our torch library, then the NN module from the torch library, then the utils submodule, and now we're going to use the function clip underscore grad underscore norm. And we're going to input our model parameters with a second input, which will be 40. And that trick will basically make sure that the gradient won't take extremely large values and degenerate the algorithm. And for those of you who might be wondering what this 40 is exactly, well, that just means that we're using this value so that the norm of the gradient stays between 0 and 40. And therefore, that's how we prevent the gradient from taking too large values. Okay, so now we're almost done. Remember, we made this ensure shared grad function at the beginning of the file, which is to ensure that the agent and the shared model share the same gradient. And to do this, to make sure of it, we can apply this function here. And so we are going to add ensure shared grad to make sure that the model and the shared model share the same gradient. All right, so that's just a precaution. I'm not sure that's totally necessary, but at least we won't get any issue here. Okay, and finally, last line of code, we are of course going to perform the optimization step to reduce the losses. And you know how to do it. Of course, we take our optimizer and we add dot step with parentheses. And there we go, the training of our brains is over. So congratulations, I hope this wasn't too overwhelming. Don't worry, I will provide the code with all the comments. So if you missed any detail, you can have a look at the comments. And don't worry if you haven't understood anything. This is very advanced, but rest assured, this is also the most powerful. Remember, who is it made from? The creator of PyTorch. So we are really working with the best here, the state of the art. So it's totally normal if you didn't get everything the first time. But by working on it many times, you will definitely get more and more comfortable. So now we're done with the training. So basically we made all the most important things. We made the brains by building the architectures of the neural networks with the convolutions, the LSTM and the fully connected layers. We trained this brain by making this train code here. So basically the heart of the algorithm is done. You made the A3C, congratulations. Now we have a few more things to do, but that is just to get the fun part. We need to make this test.py file, which will test the agent and provide the videos of the AI playing Breakout. So this will be very fun to watch. We will not code all the lines of this test.py file because, as we said, we did the most important thing, all related to A3C, but I will of course explain the code, and eventually we have this main.py file which will execute the code, and from the moment we execute this code, all the codes will be generated, so the brains will be made, the training will happen, and the AI will play new games of Breakout, and we will get all the videos. So I can't wait to eventually watch them. We are going to see if the AI is smart enough to catch the balls. So now I'm going to see you in the next tutorial for this test.py so that we can test the AI on some new games. And until then, enjoy AI. Hello and welcome to this tutorial. Congratulations again for being done with the A3C. We made it, we made the brains and we trained them. But now we still have to make a test agent which will not update the model at all, but it will just use the shared model to make its own explorations. And of course, in this code, we will record some videos, and these will be the videos of this test agent playing Breakout with a certain score. So let's go through this code. The most important is done, so as I told you, we're not going to code it line by line, but I think it's important that you understand what's going on here. So there we go with this code. In the first section, as you noticed, we import the libraries, and then we define this test function, which will make this test agent do its own exploration and play the Breakout game. So there we go. This test function takes 3 arguments. The first one is rank, and that is still to desynchronize the test agent, as we did for the training agents. Then we have our parameters, of course, because we will need some. And of course, we have the shared model, because this test agent will use the shared model to do its own exploration. All right, then there we go inside the function. In this line of code, we desynchronize the test agent, exactly as we did before. Then we import the environment. So I remind that in the main code, which will be in the next tutorial, well, env name here will be replaced by breakout v0 so that we can go into the breakout v0 environment and play the game. And video equals true means that we will get the videos of our AI playing breakout. So basically, this line of code in total means that we run one environment with a video. Then at the next line of code, we desynchronize this environment. So exact same principle as in the train function. Then we get our model. And to do this, we create an object of the ActorCritic class and we input the input shape with our environment, observation space, and shape 0, so exactly like for the train function, and our outputs, which are the actions, with env action space. So exactly like before. Then something new here. Since we're done with the training, we don't want to put the model in train mode because simply we don't want it to train. We want to put it in eval mode. And that's what we do here with model.eval. So that's just basically to put the test agent in a mode that will basically test its performance, evaluate it. Then here we get our input states, which are the input images from the game, which at this point are NumPy arrays. Then here we convert them into torch tensors. Here we initialize the sum of the rewards. Here we initialize done to true, so still just like last time. Then something new again, we introduce this start time variable with time.time function to measure the time of computations, and that's because we want to get the starting point. Then here for the actions we use a very practical type of queue that allows to add an element to the queue from the right or from the left, so that's very practical, and I'll give you the reference link in the commented version of the code. So you'll have a look at what this dequeue is, and that's what allows to do that. Then we initialize the length of an episode with 0, of course, and then we will increment the size in this while loop. So we use the same trick here, while true, and in the loop we increment the length of the episode by 1. When the game is done, when the game is over, we reload the last state of the shared model that was updated by the other models. Remember that here this shared model is no longer updated. Then, still, if the game is over, if the game is done, we reinitialize the cell states, Cx, and the hidden states, Hx. And else, if the game is not over, well, we keep the same cell states and hidden states, but we make sure they are in a torch variable so that they can be attached to a gradient. Okay, so that's something we already did in the train function. And then, still in the while loop, and after having updated the cell states and the hidden states the right way, depending on the two cases here, well, what do? We get the predictions of the model. So that's exactly what we do here with this line of code. So we get the value, which is the output of the critic, the action value, which is the output of the actor, and then the tuple of the hidden states, Hx, and the cell states, Cx. Then we generate a distribution of probabilities of the actions, that is of the Q values, action value here, and we do this with the softmax function. And of course, we don't need to get the log probabilities here because this is just for the training. For the test agent, it will just play the action, so it will just use, like Doom, a softmax body to play it, but we're not doing any training here. So we have just the prob, and from this prob, we play the action by taking directly the argmax of these probabilities, that is, it takes the action that has the highest probability, and the reason is that the test agent doesn't do any exploration. Remember that we want to give a chance to pick up some actions that have low probabilities when we want to do some exploration of these other actions, and not taking each time the action that has the highest probability. But here the test agent won't do any exploration, and therefore that's why we directly take the action that has the maximum probability. Okay, and then once we play the action, we reach the next state, and we get the next reward, and done is updated whether or not the game is over. So we get all this with this line of code by playing the action after having selected it with the argmax here. So we play the action here, and we get the state, we get the reward, and done is updated. Okay, and then since we just got a new reward, we're going to update the sum of the reward by simply adding this new reward. And finally, whenever the game is done, so if done means when the game is done, when the AI finishes playing the game, well, we're going to print the results with the time, the episode reward, the length of the episode, that is, how much time did it last playing Breakout, and this is just how we print all these variables using these time tricks. So that's for the time, and then reward sum is just a variable for the sum of the rewards, and episode length is the variable for the length of an episode. Okay, and then once we printed all the results, well, since the game is over and we want to start a new game, we're going to reinitialize everything, that is, the sum of the reward to 0, the length of an episode to 0. We're going to reinit all the actions by using this clear function, reset the input images, by re-putting all the bricks all together, and finally, we use this time.sleep 60 seconds to just do a break of 1 minute to let the other agents practice. And that's if the game is over. Okay, and finally, we have this last line of code, which will get us the new state, and then we can move forward. We can continue in this new game. So there we go, that's the test function, thanks to which we will see the videos in 1 or 2 tutorials. I hope we will be all together like last time to watch the results, that is, with you, Kirill and me. That will be fun, and I'm telling you, expect to see good results. But keep in mind that this breakout game was super challenging. We thought it was the simplest game to play first, but not at all. It actually turned out to be much more difficult than Doom, and that's why we put it in the last module. But anyway, let's make this main function in the next tutorial. Same, this is not the most important here now that the A3C is all implemented. So we will not code it line by line, I will explain the code, and very quickly we will get to the results. Until then, enjoy AI! Hello and welcome to this tutorial. Almost the final tutorial of this module. I'm just going to explain the main code that will execute the whole thing before we get the exciting results and watch the videos. So this is the main code, and as you can see, this is pretty short. We start by importing the libraries and the modules, and also the different classes and functions we made, like ActorCritic from our model file, the train function from the train file, and the test function from the test file. And of course, we import our optimizer. Then we start with the first section where we get into a class all the parameters. And this is this params. Remember, this is this params object that we created from this params class each time we got a parameter like the learning rate, gamma, or tau. So let's go through them quickly. This first one, LR here, is the learning rate. So as you can see, we choose a small learning rate. This second one is the gamma parameter. Again, we take it as 0.99. We take a 1 tau parameter, a seed of 1, 16 processes, 20 steps, a max length of 10,000. Remember, we spoke about that. This is the parameter we set to make sure the agent doesn't get stuck indefinitely into a state of the environment. So this will stop the game if the episode length goes over this maximum episode length. And eventually, of course, we get the name of our environment, Breakout V0. And by the way, you can also play on some other environment just by changing this name of the environment here. So if you want to play to some other Breakout versions or even some other Atari games, well, you can simply replace this Breakout V0 here by some other games. But I can tell you that Breakout V0 is already very challenging. All right, so all the parameters here, and then there is the main code for the main run. And so here, let's see what we do. In this first line, we set 1 thread per core. Then in the second line, we get all our parameters by, creating an object of the params class, which will get and initialize all these parameters here because there are the variables attached to this params object. Then we set the seed. Then we get our environment using the create Atari env function with the name of our environment, which is breakout v0. You see self.envName, and therefore params.envName is breakout v0. So that will get us the environment of breakout. And by the way, this is not the usual way of creating an environment, but to improve the whole process and to improve the performance, well, we use this to actually create an optimized environment. And we do this thanks to Universe. Universe is a package that comes with all the packages you installed on OpenAI Gym. Well, thanks to Universe, we get an optimized environment. This is what is all about here. Then we get our shared model by creating an object of the actor-critic class. And so here it's important to understand that this shared model is the model shared by the different agents. So we have different threads in different cores. And speaking of threads, at the next line here, shared model.shareMemory, what we do is we store the model in the shared memory of the computer so that all the threads can get access to it, even if they are in different cores. So that's what we do here. This is to enable this. Then we get our optimizer linked to the parameters of our shared model and with a learning rate of 0.0001. And again, it's important to understand that the optimizer is also shared because it's going to act on the shared model. And same at the next line, optimizer.shareMemory, we store the optimizer in the shared memory so that all the agents can get access to it to optimize the model. Then we initialize our processes. So the test process doesn't update the shared model, but it just uses it to try it on one part and print the score and record the videos. So that's exactly what is done here with target equals test. That's the test process. And this process here is got from torch.multipreprocessing, so here. And what it does is that it basically runs a function on an independent thread. So then when we do p-start, we start a new process, which was the one initialized here at this line. And then with this process.appendp, we add the process in the list of the processes. And finally, in this loop here, we just do a loop to run all the other processes that will be trained by updating the shared model. And that's basically what happens in the last lines of code here. So if you don't want to get into the details of it, the important thing to understand is that this will run the processes in an optimal way, and therefore we should all be good to execute this code and to have a trained model and eventually watch the results. So I can't wait to do that. This is going to be pretty exciting. I will try to find Kirill now so that we can all watch it together. And so until next time, enjoy AI. Hi guys, welcome to the final tutorial for Breakout.
Hey guys, super excited to have you here.
And super happy to be all together again after Doom.
Yeah.
So this time we're gonna watch the result for Breakout, which I remind was much more challenging than Doom. So let's hope we get some good results.
Okay.
Yeah.
So what are we doing?
So here is the main code. So you know we have several codes. All the codes are here, and here is the main code. I mean the code that will execute all the other codes. So build a neural network and train the agents and the critic. Okay. So basically, what we're gonna do is just execute, just to see how it's going, but we will not wait for the results because actually it takes several hours.
Yeah.
So we prepared the results in this test folder. We already have the video. And we will show you right after that.
Okay.
Okay? So to execute, basically we just select the whole code here, and here we go.
Yeah. All right.
And as you can see, the videos are populated.
Okay.
All right? So right now, we already have 2 videos, and then the agents are training, but it's going to take a long time. So now what we're going to do is watch the results.
Okay.
Okay.
Which I haven't seen yet.
You haven't seen yet, yeah.
All right.
Right. So, in the template folder that you will find on the SDS website, you will find 2 folders, code no comments and code with comments. So that's even if you missed any detail, you can still have a look at this code. You have all the comments well explained, so each line is well commented so that you can understand. And then in this folder you will find this test folder, and that's the folder that will be populated with the videos.
Okay.
So that's where the videos are. So these are the videos of our previous training. You know, we trained the model for a couple of hours and we obtained these videos. So we're going to watch them one by one, starting with the first one. And we're going to see if, you know, we see some artificial intelligence playing Breakout and if we manage to solve Breakout. Okay?
Let's have a look.
So let's have a look at the first video. So this first video is, you know, actually what we're going to do, what we're going to do is stop the training because it's slowing down my computer right now. So, okay, so interrupted, but all good.
Yeah.
So let's watch the first video. It's gonna be really bad because it's really the first one. The paddle might not even move. There we go, yeah, it doesn't move.
Why doesn't he move at all?
Because, you know, it's the very beginning, the AI doesn't know what to do.
Yeah.
And it's still pre-processing the images, so yeah, nothing.
Gotcha.
And it might even be the case for the second video. If we look at the second one, the paddle might still not move.
Okay.
So, what do you think of this artificial
A3C
intelligence so
sucks.
far? Yeah. So that was worth spending so much energy on the A3C, right?
Yeah.
Okay, so next video we might have something.
All right. So
Maybe a little something, a little bit of artificial intelligence. let's
okay,
see.
you're giving away too much.
Not even.
Not even.
Not
Oh,
even.
useless.
Are we gonna break breakout or
No.
no?
All right, come on. Let's do something. Let's
Okay.
see something cool.
Let's hope that we get something for the next one. Yeah, I think we get something because now that's 11 seconds.
Okay.
There we go.
Up.
Better. Okay. So now the AI has eyes. It can see,
Yeah.
can sense what it's doing.
Yeah.
But it's not very quick yet.
Yeah.
It's not a smart AI.
Okay.
Okay.
Gotcha.
But better.
Yep.
Okay, so 4.
4.
Okay. So next video now.
Mm-hmm.
Ooh, it looks much better now.
Yeah. More time.
Yeah. You ready?
Yep. Let's have a look.
Yeah.
Okay. Got it.
There we
Oh,
go.
you got another one. No, you lost that.
Yeah. Still not perfect, but definitely it's like a human playing.
Yeah.
Not very good at breakout, but still it's like a
Like yeah,
human playing.
like a 5-year-old, 2-year-old human playing.
Yeah.
Okay. Wow, it's actually getting them.
Yeah. A good 2-year-old now.
Yeah.
But it's like it's doing, trying to catch the ball with some weird tactic.
Yeah.
It's
Okay.
not like a perfect prediction of where the ball is going to be.
Gotcha. Okay. Let's
Okay.
hope it gets
So
gets
much better. 27.
Uh huh.
Okay. Next one. 37 again.
Ooh, okay.
Okay.
No,
Let's
that
see.
was 27. This is 37.
Okay. No, I mean the time.
Okay. Oh, okay.
Yeah. Now I would say it's a 5-year-old playing.
Okay.
Pretty good, huh?
Yeah.
And now the ball is going faster,
Mhm.
so it's of course much more difficult, but still it's doing great. So let's see if we can beat 27 this time. 23, 24, 28. Okay, here we go. See, it's getting better and better.
Yeah.
That's a good sign.
Mhm.
Okay,
Cool.
lost its 3 lives. Next one. Whoa, 1 minute 10 seconds.
Oh, okay.
Let's see.
Straight there. That's really cool.
Yeah, that's definitely a pro now,
Mm.
isn't it?
Yeah, and you can tell it's not a human playing because it's like it's moving sporadically, like super fast,
Yes.
and it's doing a lot of, I'd say even unnecessary movements, but it's still getting there.
Yeah, let's see how it does when the ball is going really fast.
What does the ball speed depend on?
I don't know. I think it's
Does it depend on the color of the block it destroys,
maybe.
or is it just like random?
It looks like random, but we should check out the breakout rules.
Yeah.
But it's really doing great now.
Yeah.
34 score.
Nice.
Wow. It's really doing great. So yeah, we definitely have some A3C playing breakout now.
Nice. With an LSTM, yeah.
Yeah, this was an LSTM, so it's like we have a brain with a memory.
Yeah.
Not only with eyes,
Mm-hmm.
it has good eyes, you know, it's
Yeah.
pretty quick
Yeah.
to catch the ball. But also it's got some memory, but I don't know, would you use your memory to play breakout yourself?
Of course. Yeah.
Okay, so well done to the A3C,
Okay.
the AI.
What's the last one?
The last one, 55 seconds, so a little less.
Yeah.
You remember what the score was
No.
on the previous one? Let's check it out to see if we get some improvement. We might not get some improvement every video.
Yeah. Exploration.
Okay, so that was 78.
Okay.
Yeah, that's due to exploration, as you say. Okay, there we go.
Okay. I think we should have like some music playing while we watch.
Yes.
It's like hypnotizing. You can do it. He's like on steroids. Just Clicking left and right all the time.
But it's doing good.
Yeah.
But we might not solve the whole game of Breakout, but
Yeah.
we just need to have it trained more.
Yeah. That's already really good.
It's really good, yeah. Oh,
Whoa,
whoa.
at that speed.
Oh,
Nice.
yeah. That was a little bit too fast.
60. So it beat the score again.
That was 78,
Oh, no.
wasn't it?
Yeah.
Yeah.
That's it.
Okay, so we did it,
Good
didn't we?
stuff. Yeah.
Definitely some AI playing Breakouts.
Yeah. Nice. Very nice. Very nice. Awesome.
So I hope you liked it, and mostly I hope you liked this powerful implementation of the A3C. And
Yeah, you can see what how it can do really well with the LSTM. Yeah,
that's right.
like at the end of the A3C paper, they have like the comparison of different algorithms, and this one is the best one by far.
Not only they have the best the comparison of these models, but also I experienced several of them, and so I experienced the one without an LSTM and the one with, and definitely the LSTM improves the algorithm.
How
a lot.
much better is it within LSTM?
Much better. Like I barely had some artificial intelligence before playing Breakout. It lasts like 15 seconds
Okay.
or 20 seconds, but definitely not more than 1 minute, as we saw here.
Yeah, that's good. That's good. Okay, cool.
Cool.
Thanks a lot, guys.
Thanks a lot. That was the end of the third module and therefore the end of the course. So congratulations for having completed the 3 modules and mostly the A3C, which was pretty big. Pretty big.
Yeah. And for sure, explore the different modifications that exist for the A3C.
Yes.
And maybe at the time you're watching this, there's some really cool new advancements in A3C, and you can add those on.
Probably. Or even a new model, even better than the A3C.
Yeah, for sure.
Let's see what 2018 says.
Okay. All right. Thanks, all guys.
Thanks. Bye.
Hello everyone and welcome back. In this video we'll talk about how to use ChatGPT to solve breakout using ChatGPT to implement A3C. So I already prompted it with a lot of crazy prompts. We got amazing results. We'll see them in a second. So this video will be basically walking you through my thought process on how I actually got the results and how you can actually use ChatGPT to create A3C algorithm as well. Okay, so I started similarly to what we had for Doom. I stated, okay, you are basically a machine learning expert with years of experience in robotics. I hire you to do A3C algorithm for breakout. The goal is to have a fully functional SOTA A3C algorithm that can play the breakout game. I have implemented classes, the testing code, environment, and custom versions of Adam Optimizer that is used as a shared weights optimizer for the A3C model. So this is giving it more context, what I did. I will provide these 3 things to you. So as a reference before generating the rest of the code. Your goal is to implement the full solution using Python, Torch, similar to what we had, and optimize the code to be executed in Google Colab, same what we had before. Additionally, comment every single line of the code so the students can understand what you did in the code. Ask clarifying questions if needed. Got it. So we have some overlapping what we did for convolutional deep Q for Doom, but I added a lot of context that I already have things implemented and I'd like them to be used. So that's what I started, and it confirmed. Yes, I understand, and I'll ask any questions, please provide the rest of the code. Then I stated, this is Adam Optimizer, pasted the code for Adam Optimizer, for the resources we have, and I gave this instruction. I said, wait for the rest of the code before implementing. Just before I got any good results, I actually just pasted and it immediately jumped to implementing A3C without waiting for the rest. So I added this as a kind of a systemic code, systemic prompt, and it said, okay, please provide the environment and test the code. So it's actually referring to what we gave in the first prompt. I said, cool. Here is the implementation of Gym environment. I pasted that, main code. I added context here, if you take a look. And this is the main file running everything. And then I said, okay, cool, wait for the testing code. And it said, yeah, however, I still need to see the testing code before I implement A4C. I said, cool, here is the testing code. And you see, this is how, if you have a bigger project, you can use that to kind of sway it to use that piece of a code or as a reference in the style, so you can actually generate something in your style of code. Cool. And when I done that, it said, great, go for it. And it said, basically, I'm going to use this main code and testing and implement this. And then it said created model.py, which actually we did in the course as well. And it said, here is the actor critic model. And I compared to ours. This is the newer version of PyTorch. So much of the weights in the initialization and stuff like that can be done in a more elegant way. So it did it. And it actually used this pretty well. Then generated train code. And basically actor critic. And if you take a look, it's a pretty simplistic, so it definitely needs to be improved. So what you can do, you can say, okay, I said continue, and it continues writing it down. It created this as a kind of a loss, but there is, yeah, basically everything that we needed. It optimized everything, and you can see that optimized step at the end. So it basically used everything that we defined so far, as well as the proper loss and optimizer, everything. So that's it. In a couple of simple steps, we managed to implement the whole code for one of the state-of-the-art models that happened to be like one of the best in 2017, 2018. To this day, it actually holds a lot of capacity to solve complex environments such as breakout. So you saw now that we have ChatGPT, for example, you can guide it to implement certain parts of the code. And if you don't know what certain parts of the code actually does, you can go and ask it. For example, cool. Can you explain training part, and where is the custom? Oh, Adam. So I'm urging it to actually explain itself. So that's another way to basically prompt it out to give you more reasoning behind its generation. And you can see that it's actually going to explain step by step. So yeah, we can wait for this. You can do the same prompts and you will get really similar results to mine. But generally now what it's going to do, it's going to take the train function that it defined right at the top, right here, and it will basically go through every single step and implement it. So yeah, that would be it. I definitely encourage you to try out this code in Google Colab. It can be done. It will be a bit too tricky to make it work because of the visualization and the limitations of the Google Colab environment. However, you can definitely go and paste the errors here, and you can go and get some pretty decent results for that to debug the process. And yeah, with that, I'll let you be, and now you have the way to use ChatGPT on how to get value for A4C. And yeah, hope you enjoyed the course so far. Bye.
Well, Allison should know.
What
do you
is
say to that,
internet
Allison?
anyway?
Internet is that
Massive computer
right,
network.
the one that's becoming really big now.
What do you mean? That's big. How does one? What do you write to it like mail?
No, a lot of people use it and communicate. I guess they can communicate with NBC writers and producers. Allison, can you explain what internet is?
How amazing is that? Just over 20 years ago, people didn't even know what the internet was, and today we can't even imagine our lives without it. Welcome to the Deep Learning A to Z course. My name is Kirill Romenko, and along with the co-instructor Hadelan de Ponteves, we're super excited to have you on board. And today we're going to give you a quick overview of what deep learning it is and why it's picking up right now. So let's get started. Why did we have a look at that clip? And what is this photo over here? Well, that clip was from 1994. This is a photo of a computer from 1980. And the reason why we're kind of delving into history a little bit is because neural networks, along with deep learning, have been around for quite some time. And they've only started picking up now and impacting the world right now. But if you look back at the 80s, you'll see that even though they were invented in the 60s and 70s, they really caught on to a trend or caught wind in the 80s. So people started talking about them a lot. There was a lot of research in that area, and everybody thought that deep learning or neural networks were this new thing that is going to impact the world, that's going to change everything, it's going to solve all the world problems, and then it kind of slowly died off over the next decade. And so what happened? Why did the neural networks not survive and not change the world? Was it the reason for that they were just not good enough, that they're not that good at predicting things and not that good at modeling and basically just not a good invention? Or is there another reason? Well, actually there is another reason, and the reason is in front of us. It's the fact that technology back then was not up to the right standard to facilitate neural networks. In order for neural networks and deep learning to work properly, you need two things. You need data, and you need a lot of data, and you need processing power. You need strong computers to process that data and facilitate the neural networks. So let's have a look at how data or storage of data has evolved over the years, and then we'll look at how technology has evolved. So here we've got 3 years: 1956, 1980, 2017. How did storage look back in 1956? Well, there's a hard drive, and that hard drive is only a 5, wait for it, megabyte hard drive. That's 5 megabytes right there on the forklift, the size of a small room. That's a hard drive being transported to another location on a plane, and that is what storage looked like in 1956. A company had to pay $2,500 of those days dollars to rent that hard drive, to rent it, not buy it, to rent it for 1 month. In 1980, the situation improved a little bit. So here we've got a 10 megabyte hard drive for $3,500. It's still very expensive and only 10 megabytes. So that's like one photo these days. And today in 2017, we've got a 256 gigabyte SSD card for $150, which can fit on your finger. And if you're watching this video a year later, or like in 2019 or 2025, you're probably laughing to yourself because by then you have even stronger storage capacity. But nevertheless, the point stands. So if we compare these across the board, and without even taking price and size into consideration, just the capacity of whatever was trending at the time. So from 1956 to 1980, capacity increased about double, and then it increased about 25,600 times. And the the length of the period is not that different. So from 1956 to 1980, 24 years. From 1980 to 2017, 37 years. So not that much of an increase in time, but a huge jump in technological progress. And that stands to show that this is not a linear trend. This is an exponential growth in technology. And if we take into account price and size, it'll be in the millions of increase. And here we actually have a chart on a logarithmic scale. So if we plot the hard drive cost per gigabyte, you'll see that looks something like this. We're very quickly approaching zero. Right now you can get storage on Dropbox and Google Drive, which doesn't cost you anything, cloud storage, and that's going to continue. And in fact, over the years, this is going to go even further. Right now, scientists are already looking into using DNA for storage. And right now, it's quite expensive. It costs $7,000 to synthesize 2 megabytes of data, and then another $2,000 to read it. But that kind of reminds you of this whole situation of the hard drive and the plane, that this is going to be mitigated very, very quickly with this exponential curve. 10 years from now, 20 years from now, everybody's going to be using DNA storage if we go down this direction. And here's some stats around that. So you can explore this further. Maybe pause the video if you want to read a bit more about this. This is from nature.com. And basically, you can store all of the world's data in just 1 kilogram of DNA storage. Or you can store about 1 billion terabytes of data in 1 gram of DNA storage. So that's just something to show how quickly we're progressing, and that this is why deep learning is picking up now, that we are finally at the stage where we have enough data to train super cool, super sophisticated models. Back then in the 80s when it was first initially invented, it just wasn't the case. And the second thing we talked about is processing capacity. So here we've got an exponential curve, again, on a log scale. It's not ideally portrayed here, but on the right you can see it's a log scale. And this is how computers have been evolving. So again, feel free to pause the slide. This is called Moore's Law. You've probably heard of it, how quickly the processing capacity of computers has been evolving. Right now we're somewhere over here where an average computer you can buy for $1,000 thinks at the speed of the brain of a rat. And by 2025 it will be the speed of a human, or 2023, and then by 2050 or 2045 it will surpass all of the humans combined. So basically we're entering the era of computers that are extremely powerful, that can process things way faster than we can imagine, and that is what is facilitating deep learning. So all of this brings us to the question: what is deep learning? What is this whole neural network situation? What is going on? What are we even talking about here? And you've probably seen a picture something like this. So let's dive into it. What is deep learning? This gentleman over here, Geoffrey Hinton, is known as the godfather of deep learning. And he did research on deep learning in the 80s, and he's done lots and lots of work, lots of research papers that he's published in deep learning. Right now he works at Google. So a lot of the things that we're going to be talking about actually come from Geoffrey Hinton. And you can see a lot. He's got quite a few YouTube videos. He explains things really well. So highly recommend checking them out. And so the idea behind deep learning is to look at the human brain. And there's going to be quite a bit of neuroscience coming up and in these tutorials. And what we're trying to do here is to mimic how the human brain operates. And we don't know that much. We don't know everything about the human brain, but that little amount that we know, we want to mimic it and recreate it. And why is that? Well, because the human brain seems to be one of the most powerful tools on this planet for learning, adapting skills, and then applying them. And if computers could copy that, then we could just leverage what natural selection has already decided for us, all of those kind of algorithms that it has decided are the best. We're just going to leverage that. Why reinvent the bicycle, right? So let's see how this works. So here we've got some neurons. So these are neurons which have been smeared onto glass and then have been looked at under a microscope with some coloring. And this is, you can see what they look like. So they have like a body, they have these branches, and they have like tails and so on. So you can see then they have like a nucleus inside in the middle. And that's basically what a neuron looks like. In the human brain, there's approximately 100 billion neurons altogether. So these are individual neurons. These are actually motor neurons because they're bigger, they're easier to see. But nevertheless, there's 100 billion neurons in the human brain. And each neuron is connected to as many as about 1,000 of its neighbors. So to give you a picture, this is what it looks like. This is an actual section of the human brain. And this is the cerebellum, which is this part of your brain at the back. It is responsible for like motorics and for keeping your balance and some language capabilities and stuff like that. So this is just to show how vast, how many neurons there are. They're like billions and billions and billions of neurons all connected in your brain. It's not like when talking about 5 or 500 or 1,000 or a million. There's billions of neurons in there. And yeah, so that's what we're going to be trying to recreate. So how do we recreate this in a computer? Well, we create an artificial structure called an artificial neural net where we have nodes or neurons. And we're going to have some neurons for input values. So these are values that you know about a certain situation. So for instance, you're modeling something, you want to predict something, you're always going to have some input, something to start your predictions off. And then that's called the input layer. Then you have the output. So that's a value that you want to predict, whether it's the price, whether it's is somebody going to leave the bank or stay in the bank? Is this a fraudulent transaction? Is this a real transaction? And so on. So that's going to be your output layer. And in between, we're going to have a hidden layer. So as you could see in your brain, you have so many neurons. So some information is coming in through your eyes, ears, nose, so basically your senses. And then it's not just going right away to the output where you have the result. It's going through all of these billions and billions and billions of neurons before it gets to the output. And this is the whole concept behind it, that we're going to model the brain. So we need these hidden layers that are there before the output. So the input layers, neurons connected to the hidden layer neurons. The hidden layer neurons are connected to the output value. And so this is pretty cool, but what is this all about? Where is the deep learning here? Why is it called deep learning? There's nothing deep in here. Well, this is kind of like an option which one might call shallow learning. There isn't much indeed going on. But why is it called deep learning? Well, because then we take this to the next level. We separate it even further, and we have not just one hidden layer. We have lots and lots and lots of hidden layers. And then we connect everything, just like in the human brain. We connect everything, interconnect everything, and that's how the input values are processed through all these hidden layers, just like in the human brain. Then we have an output value. And now we're talking deep learning. So that's what deep learning is all about on a very abstract level. In the further tutorials, we're going to dissect and dive deep into deep learning. And by the end of it, you will know what deep learning is all about, and you will know how to apply it in your projects. Super excited about this. Can't wait to get started. And I look forward to seeing you on the next tutorial. Until then, enjoy deep learning. Hello and welcome to the Intuition tutorials for the artificial neural networks part of the course. Super excited to get these things started, and today we're going to find out how we're going to tackle this section. So in this section, we will learn the following things. First of all, we'll talk about the neuron. So there'll be a little bit of neuroscience, and we'll find out a bit about how the human brain works and why we're trying to replicate that, and we'll also see what the main building block of a neural network, the neuron, looks like. Then in the next tutorial, we'll talk about the activation function, and we'll look at a couple of examples of activation functions that you could use in your neural networks, and we'll find out which one of them is the most commonly used one in neural networks, and in which layers you would rather use which functions. Then we'll talk about how neural networks work. So in contrast to what you would expect and what is probably conveyed in other courses and tutorials, we're not going to go into the learning. We're actually going to go into the working of the neural networks first, because that way, by seeing a neural network in action, that will allow us to understand what we're aiming towards, what our goal is. So here we'll look at an example of a neural network. We're going to look at a very simplified hypothetical example of a neural network working to predict housing prices, so basically real estate prices. And by looking at that example, we'll understand better exactly what we're aiming towards and what we want to achieve in the end. And then we will move on to understanding how neural networks learn, because that way we'll be more prepared for what's coming. Then we'll talk about gradient descent. This is also part of neural networks learning, and we'll understand how that algorithm is better than just the brute force method that you might be intending or willing to take as a first resort or first method that comes to mind. So we'll find out what the advantage of gradient descent are, and then we'll talk about stochastic gradient descent. It's a continuation of the gradient descent tutorial, but it's an even better and even stronger method, and we'll find out exactly how it works. And finally, we'll wrap things up by mentioning the important things about backpropagation and summarizing everything in a step-by-step set of instructions for running your artificial neural networks. I hope this all sounds very exciting to you, because I am very excited myself and I can't wait to get started. I look forward to seeing you on the first tutorial, and until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about the neuron, which is the basic building block of artificial neural networks. So let's get started. Previously we saw an image which looked like this, and these are actual real-life neurons which have been smeared onto a glass and colored a little bit, and they are observed through a microscope. So this is what they look like. As you can see, quite an interesting structure, a body, and then lots of different tails, kind of branches coming out of them. And this is very interesting, but the question is, how can we recreate that in a machine? Because we really need to recreate it in a machine, since the whole purpose of deep learning is to mimic how the human brain works, in the hope that by doing so, we're going to create something amazing. We're going to create an amazing infrastructure for machines to be able to learn. And why do we hope for that? Well, because the human brain is, just happens to be one of the most powerful learning tools on the planet, or like learning mechanisms on the planet. And we just hope that if we recreate that, we'll have something as awesome as that. So our challenge right now, our very first step to creating artificial neural networks, is to recreate a neuron. So how do we do that? Well, first of all, let's have a closer look at what it actually is. This image was first created by Spanish neuroscientist Santiago Ramon y Cajal in 1899. And what he did was he dyed neurons in actual brain tissue and looked at them under a microscope. And while he was looking at them, he actually drew what he saw. And this is what he saw. He saw two neurons, or two large neurons over there at the top, which had all of these branches coming out of them towards their top parts. And then each one of them had this rod or like thread coming out towards the bottom, very long one. And so that's what he saw. And now, technology has advanced quite a lot, and we have seen neurons much closer in more detail. And now we can actually draw what it looks like diagrammatically. So let's have a look at that. Here's a neuron. This is what it looks like. Very similar to what Santiago Ramon drew over here. And here in this neuron, what we can see is that it's got a body. Well, that's the main part of the neuron. And then it's got some branches at the top, which are called dendrites. And it's also got an axon, which is that long tail of the neuron. And so what are these dendrites for, and what's the axon for? Well, the key point to understand here is that neurons by themselves are pretty much useless. It's like an ant, right? An ant on its own can't do much. Like 5 ants together, maybe they can pick something up. But again, they can't build an anthill. They can't establish a colony. They can't work together as a huge organism. But at the same time, when you have lots and lots of ants, like you have a million ants, they can build a whole colony. They can build an anthill. Same thing with neurons. By itself, it's not that strong, but when you have lots of neurons together, they work together to do magic. And how do they work together? That's the question. Well, that's what the dendrites and the axon are for. So the dendrites are kind of like the receivers of the signal for the neuron, and the axon is the transmitter of the signal for the neuron. And here's an image of how it all works conceptually. So at the top, you've got a neuron, and you can see that its dendrites are connected to axons of other neurons that are like even further away above it. And then the signal from this neuron travels down its axon and connects or passes on to the dendrites of the next neuron. And that's how they're connected. And in that small image over there, you can see that the axon doesn't actually touch the dendrite. A lot of machine learning, or like a few machine learning scientists are very adamant about the fact that it doesn't touch. It doesn't touch. It has been proven that there is no physical connection there. But the point that we're interested in is that connection between them, that the whole concept of the signal being passed, that's called a synapse. You can see over there in that little image, that's figure bracket is a synapse, and that's the term we're going to be using. So instead of calling our artificial neurons, the lines that we're going to have, or the connectors for artificial neurons, we're not going to be calling them axons or dendrites, because then the question is, whose connection is this? Is it that neurons or is it this neurons? We're just going to call them synapses. And that's kind of just answers all questions right away. That's just basically where the signal is passed. Doesn't matter who that element belongs to. That's just a representation of the signal being passed, and we'll see that just now. So basically, that's how a neuron works. And so let's move on to how we're going to represent neurons, or how we're going to create neurons in machines. So we're moving away, now we're moving away from neuroscience and moving into technology. And here we go. So here's our neuron, also sometimes called the node. The neuron gets some input signals, and it has an output signal. So dendrites and axons, remember, but again, we're going to call all these synapses. Then these input signals, we're going to represent them with other neurons as well. So in this specific case, you can see that this neuron, this green neuron, is getting signals from yellow neurons. And in this course, we're going to try and stick to a certain color coding regime where yellow means an input layer. So basically, all of the neurons that are on the outer layer or in the first front of where the signal is coming in. And by signal, it might be like a bit of an overkill to call this a signal. It's just basically input values. So you know how even like in a simple linear regression, you have input values and then you have a predicted value. Same thing here. So you have input values, and there they are, the yellow ones. And then on the right, you'll see just now, it'll be red. It'll be the output value. The thing that I wanted to point out here is that in this specific example, we're looking at a neuron which is getting its signals from the input layer neurons. So they're also neurons, but they're input layer neurons. Sometimes you'll have neurons which get their signal from other hidden layer neurons, so from other green neurons, and the concept is going to be exactly the same. And just in this case, for simplicity's sake, we're portraying this example. And in terms of the input layer, the way to think about it is, in the analogy of the human brain, the input layer is your senses, right? So whatever you can see, hear, feel, touch, or smell. And of course, it's like there's a lot of things you can see. There's a lot of information coming in, but that's what your brain is limited to. It's pretty much it's pretty much lives in a box made out of bones, and it's a mind-blowing concept to think about, that your brain is just locked in a black box, and the only thing, like, it can't see, it can't hear. The only thing it's getting is electrical impulses coming from these organs that you have, which are called your ears, nose, eyes, your sense of touch, and whatever, and your taste, right? So it's just getting signals, but it basically lives in this dark black box, and it's making sense of the world through your senses. It's phenomenal. And so you have these inputs that are coming in. In terms of human brain, those are your 5 senses, and in terms of machine learning or deep learning, that is basically your input values, so your independent variables, and we'll get that to in a second. So your input values, the signal is passed through synapses to your neuron, and then your neuron has an output value that it passes further on down the chain. In this specific case, in terms of color coding, again, yellow means input layer. So we're kind of simplifying everything here. We're saying we're only going to have like the input layer, then we're going to have one hidden layer with the green, which is the hidden layer, and then we're going to have the output layer right away. So just so that we can get used to these colors for now. So there we go. That's the basic structure. So now let's look in a bit more detail at these different elements that we have. So we've got the input layer. And what do we have here? Well, we have these inputs, which are in fact independent variables. So independent variable 1, independent variable 2, independent variable m. And the important thing to remember here is that these independent variables are all for one single observation. So think of it as just one row in your database, one observation. You just take all of the independent variables, maybe it's the age of the person, the amount of money in the bank account, and then how do they drive or walk to work? What method of transportation do they use? So, but that's all descriptors of one specific person that you are either you're training your model on or you're performing some prediction on. The other thing you need to know about these variables is that you need to standardize them. So you need to either standardize them, which means make sure that they have a mean of 0 and a variance of 1, or you can also sometimes, and Hadlan will point out these situations in a bit more detail, perhaps in the practical tutorials you might come across these. Sometimes you might want to not standardize, you might want to normalize them, meaning that instead of making sure the mean is 0 and variance is 1, you just take you subtract the minimum value and then you divide by the maximum minus the minimum, so by the range of your values, and therefore you get values between 0 and 1. And it depends on the scenario. You might want to do one or the other, but basically you want all of these variables to be quite similar in about the same range of values. And why is that? Well, all of these values are going to go into a neural network where, as we'll see just now, they'll be added up and multiplied by weights, added up, and so on. And just going to be easier for the neural network to process them if they're all about the same. And in fact, that's just how it is going to be able to work properly. And if you want to read more about standardization, normalization, and other things that you can do with your input variables, a good additional reading paper is called Efficient Backprop by Jan LeCun, 1998. The link's over there. So Jan LeCun, we're actually going to talk more about this phenomenal person in the space of deep learning in the part of the course where we're talking about convolutional neural networks, and you'll see that this is definitely a person who knows what he's talking about. He's a close friend of Geoffrey Hinton, who we've already seen, who we've already mentioned. So in this paper, you'll learn more about standardization and normalization, but also you can pick up lots of other different tips and tricks, and it'll be a good source for additional reading as you go through this course. So yeah, check it out if you're interested in some additional reading. There we go. So that's what we need to do with the variables. And here we've got the output value. So what can our output value be? Well, we've got a couple of options. Output value can be continuous, like for instance, price. It can be binary, for instance, a person will exit or will stay, or it can be a categorical variable. And if it's a categorical variable, the important thing to remember here is that in that case, your output value won't be just one, it'll be several output values, because these will be your dummy variables, which will be representing your categories. And that's just how it works. And just important to remember that in that case, that's how you're going to be getting your categories out of the artificial neural network. But let's go back to a simple case of one output value. And now let's, one more point, or kind of like the point that we've already made. I just wanted to reiterate this point. On the left, you've got a single observation. So one row from your data set, and on the right, you have a single observation as well. And that is the same observation. So important to remember that, like, whatever inputs you're putting in, that's for one row, and then the output you get, that is for that same exact row. Or if you're training your neural network, then you're putting the inputs in for that one row, you're putting the output in for that one row. So like, if you want to simplify the complexity, think of it as like a simple linear regression or a multivariate linear regression. So you're putting in your values, you have your output. There's no question about it when we're talking about things like regression, because we're so used to it. Same thing here. It's nothing too complex. We're just putting in values, we're getting output, but just remember that every time it's one row you're dealing with, so you don't get confused and start putting in like thinking that these are different rows that you're putting into your artificial neural network or something. This is all just values in that one row. So different observation, different characteristics of or attributes relating to that one observation every single time. Okay, so next thing that we want to talk about here is the synapses. Here we've got synapses, and they all actually get assigned weights. Weights, we're going to talk more about weights further down, but in short, weights are crucial to artificial neural networks functioning, because weights are how neural networks learn. By adjusting the weights, the neural network decides in every single case what signal is important, what signal is not important to a certain neuron, what signal gets passed along and what signal doesn't get passed along, or to what strength, to what extent signals get passed along. So weights are crucial. They are the things that get adjusted through the process of learning. Like when you're training an artificial neural network, you're basically adjusting all of the weights in all of the synapses across this whole neural network. And that's where gradient descent and backpropagation come into play. And those are concepts that we'll also discuss. So basically, those are the weights. That's all we need to know for now. And here we've got the neuron. So signals go into the neuron. And what happens in the neuron? So this is the interesting part. Like, we're talking about the neuron today. What happens inside the neuron? So a few things happen. First thing, and the first step, is that all of these values that it's getting get added up. So it takes the added, so the weighted sum of all of the input values that it's getting. Very simple, right? It's very, very straightforward. Just add up, multiply by the weight, add them up. And then it applies an activation function. Now, we're going to talk more about activation functions further down, but it's basically a function that is assigned to this neuron or to this whole layer. And it is applied to this weighted sum. And then from that, the neuron understands if it needs to pass on a signal. If it, that's the signal that it passes on, that the function applied to the weighted sum. But basically, depending on that function, the neuron will either pass on a signal or it won't pass that signal on. And that's exactly what happened here in step 3. The neuron passes on that signal to the next neuron down the line. And that's what we're going to talk about in the next tutorial, because it is quite an important topic. We want to delve deeper into the activation function. But hopefully for now, everything should be pretty clear. How, you've got input values, you've got weights, you've got the synapses, you've got something, happens in the neuron, you've got the weighted sum, and then an activation function applied, and then that is passed down the line. And that is just repeated throughout the whole neural network, on and on and on and on. Thousands, hundreds of thousands of times, depending on how many neurons you have, how many synapses you have in your neural network. So there we go. Hope you enjoyed today's tutorial. Can't wait to see you next time. And until then, enjoy deep learning. Hello and welcome back to the course on deep learning. All right, today we're talking about the activation function. Let's get straight into it. So this is where we left off previously. We talked about the structure of one neuron. So there it is in the middle. We know that it has some inputs values coming in. It's got some weights. Then it adds up it calculates the weighted sum of those inputs, and then applies the activation function. And on step 3, it passes on the signal to the next neuron. And that's what we're talking about today. We're talking about the value that is going to be passed over. So we're talking about the activation function that's being applied. So what options do we have for the activation function? Well, we're going to look at 4 different types of activation functions that you can choose from. Of course, there are more different types of activation functions, but these are the predominant ones that you'll be hearing about and that we'll be using in this course. So here is the threshold function. This is what it looks like. So on the x-axis, you have the weighted sum of inputs. On the y-axis, you have just the values from 0 to 1. And basically, the threshold function is a very simple type of function where if the value is less than 0, then the threshold function passes on 0. If the value is more than 0 or equal to 0, then threshold function passes on a 1. So it's basically kind of like a yes-no type of function, very, very straightforward, very kind of like rigid type of function, either yes or no, no other options. So there you go, that's how it works. Very simple function. Let's move on to something a bit more complex now. The sigmoid function, very interesting formula that we have here. You'll see just now. There it is, 1 divided by 1 plus e to the power of minus x. Whereas in this case, of course, x is the value of the summed, of the weighted sums. And so this is what the sigmoid looks like. It's a function which is used in the logistic regression, if you recall from the machine learning course. So what is good about this function is that it is smooth. Unlike the threshold function, this one doesn't have those kinks in its curve, and therefore it's just nice and smooth, gradual progression. So anything below 0, it just like drops off. Above 0, it approximates towards 1. And this sigmoid function is very useful in the final layer, in the output layer, especially when you're trying to predict probabilities, and we'll see that throughout this course. And then we've got the rectifier function. Rectifier function, even though it has a kink, is one of the most popular functions for artificial neural networks. So it goes all the way to 0. It is 0, and then from there, it gradually progresses as the input value increases as well. And we'll see that throughout the course. We'll see that in other intuition tutorials, and we'll also see that how we use this function in the practical side of the course. And I will comment on this a bit more in a few slides from now. So just remember that a rectifier function is one of the most used functions in artificial neural networks. And finally, we've got one more function that you will probably hear about. It's the hyperbolic tangent function. It's very similar to the sigmoid function, but here the hyperbolic tangent function goes below 0. So the values go from 0 to 1, or approximate to 1, and go from 0 to -1 on the other side. And that can be useful in some applications. So we're not going to go into too much depth on each one of these functions. I just wanted to acquaint you with them so that you know what they look like and what they're called. If you'd like to get some additional reading, then check out this paper by Javier Glorot, called Deep Sparse Rectifier Neural Networks, 2011 paper. And there you will find out exactly why the rectifier function is such a valuable function, why it's so popularly used. But nevertheless, for now, you don't really need to know all of those things. For now, we're just going to start applying them. We're going to start using them more and more and more. And so when you feel comfortable with the practical side of things, then you can go and refer to this paper, and then you will be able to soak in that knowledge much quicker, and it'll make much more sense. So, but just keep this in mind, that when you're ready, when you feel that you're ready, then you can go and refer to this paper and get some valuable knowledge from there. So just to quickly recap, we have the threshold activation function, which looks like this, the sigmoid activation function, which looks like this, we have the rectifier function, and we have the hyperbolic tangent function. And now to finish off this tutorial, let's quickly do a few exercises. So we'll just do two quick exercises to help that knowledge sink in. So first one is, we've got an example here of a neural network with just one neuron and then right away the output layer. And the question is, assuming that your dependent variable is binary, so it's either 0 or 1, which threshold function would you use? So out of the ones that we've discussed, we have the threshold function, the sigmoid function, the rectifier function, and we've got the hyperbolic tangent function. In their raw forms, which ones would you be able to use for a binary variable? Okay, so the answers here are, there's two options that we can approach this with. So number one is the threshold activation function, because we know that it's between 0 and 1, and it gives you a 0 under certain values, and then otherwise it gives you 1, so it only can give you 2 values. It fits perfectly, fits this requirement perfectly, and therefore you could just say y equals the threshold function of your weighted sum, and that's it. And in the second case, what you could use is the sigmoid activation function. It is actually also between 0 and 1, just what we need, but at the same time, you want it's just 0 or 1, right? So it's not exactly what we need, but in this case, what you could use it as is the probability of y being yes or no. So we want y to be 0 or 1, but instead we'll say that the sigmoid function, sigmoid activation function, tells us whether it tells us the probability of y being equal to 1. So basically, the closer you get to the top, the more likely it is that this is indeed a 1 or a yes rather than a no. And yeah, so that's very similar to the logistic regression approach. And those are just two examples of if you have a binary variable. And now let's have a look at another practical application, let's have a look at how all this would play out if we had a neural network like this. So in the first input layer, we have some inputs. They are sent off to our first hidden layer, and then an activation function is applied. And usually what you would apply here, and what you'll see throughout this course, is we would apply a rectifier activation function. So it would look something like that. We apply the rectifier activation function, and then from there, the signals would be passed on to the output layer, where the sigmoid activation function would be applied, and that would be our final output, and that could predict a probability, for instance. So this combination is going to be quite common, where in the hidden layers, we apply the rectifier function, and then in the output layer, we apply the sigmoid function. So there we go. Hope you enjoyed today's tutorial. Now you are quite well versed in the 4 different types of activation functions, and you will get some hands-on practical experience with them throughout this course. We'll be using them all over the place, so you'll get to know them quite intimately, and you should be quite comfortable with them. But for now, this is the knowledge that you need to progress and understand what is going to be happening further down in this course. And on that note, I will look forward to seeing you next time. Until then, enjoy deep learning. All right, exciting tutorial ahead. Welcome back to the course on deep learning. Today we're talking about how do neural networks work. Now we've laid a lot of groundwork. We've talked about how neural networks are structured, what elements they consist of, and even their functionality. And today we're going to look at a real example of how a neural network can be applied. And we're actually going to work step by step through the process of its application so we know what's going on. So let's have a look. What example we're going to be talking about? We're going to be looking at property valuation. So we're going to look at a neural network that takes in some parameters about a property and values it. And the thing here, there's a small caveat for today's tutorial, and that is we're not actually going to train the network. So a very important part in neural networks is training them up. And we're going to look at that in the next tutorials in this section. For now, we're going to focus on the actual application. So we're going to work with a neural network that we're going to pretend is already trained up, and that will allow us to focus on the application side of things and not get bogged down in the training aspect. And then we'll cover off the training when we already know the end goal we're working towards. Sound good? All right, let's jump straight into it. So let's say we have some input parameters, right? So let's say we have 4 parameters about the property. We have area in squared feet, we have the number of bedrooms, the distance to the city in miles, the nearest city, and the age of the property. And all of those 4 are going to comprise our input layer. Now, of course, there are probably way more parameters that define the price of a property, but for simplicity's sake, we're going to look at just these 4. Now, in its very basic form, a neural network only has an input layer and an output layer, so no hidden layers. And our output layer is the price that we're predicting. So in this form, what these input variables would do is they would just be weighted up by the synapses, and then the output layer would be calculated, or basically the price would be calculated, and we get a price. And for instance, the price could be calculated as simple as the weighted sum of all of the inputs. And again, here you could use pretty much any function. You could use what we're using now. We could use any of the activation functions we had previously. You could use a logistic regression, you could use a squared function, you could use pretty much anything here. But the point is that you get a certain output. And moreover, most of the machine learning algorithms that exist can be represented in this format. This is basically a diagrammatic representation of how you deal with the variable, right? By changing the weights, the formulas, you can accomplish quite a lot of the machine learning algorithms that we've talked about before, and put them into this form. And that just stands to show how powerful neural networks are, that even without the hidden layers, we already have a representation that works for most other machine learning algorithms. But in neural networks, what we do have is an extra advantage that gives us lots of flexibility and power, which is where that increase in accuracy comes from. And that power is the hidden layers. And there we go. That's our hidden layer. We've added it in. And now we're going to understand how that hidden layer gives us that extra power. And in fact, to do that, we're going to walk through an example. So as we agreed, this neural network has already been trained up. And now we're just going to plug in, we're going to imagine that we're plugging in a property, and we're going to walk step by step through how the neural network will deal with the input variables and calculate the hidden layer and then calculate the output layer. So let's go through this. It's going to be exciting. All right. We've got all 4 variables on the left. And we're going to first start with the top neuron on the hidden layer. Now, as we previously saw in the previous tutorials, all of the neurons from the input layer, they have synapses connecting each one of them to the top neuron in the hidden layer. And those synapses have weights. Now, let's agree that some weights will have a non-zero value, some weights will have a 0 value, because basically not all inputs will be valid, or not all inputs will be important for every single neuron. Sometimes inputs will not be important. And here we can see 2 examples, that x1 and x3, the area and the distance to the city in miles, are important for that neuron, whereas bedrooms and age are not. And let's think about this for a second. How would that be the case? Why would a certain neuron be linked to the area and the distance? What could that mean? Well, that could mean that normally the further away you get from the city, the cheaper real estate becomes, and therefore the space in square feet of properties becomes larger, right? So for the same price, you can get a larger property the further away you go from the city. That's normal, right? That makes sense. And probably what this neuron is doing is it is looking specifically, it's like a sniper. It's looking for area properties which are not so far from the city, but have a large area. So for their distance from the city, they have an unfair square foot area, right? So something that's abnormal, it's higher than average. So they're quite close to the city, but they're still large, as opposed to the other ones at the same distance. And so that neuron, again, we're speculating here, but that neuron might be laser picking out those specific properties, and it will activate, and hence the activation function. It'll fire up only when the certain criteria is met, that, the distance and the area of the distance to the city and the area of the property, and it performs its own calculations inside itself, and it combines those two, and as soon as certain criteria is met, it fires up, and that contributes to the price in the output layer. And therefore, this neuron doesn't really care about bedrooms and age of the property, because it's focused on that specific thing. That's where the power of the neural network comes from, because you have many of these neurons, and we'll see just now how the other ones work. But what I wanted to agree here is that let's not even draw these lines for the synapses that are not in play, so that we don't clutter up our image. That's the only reason we're not going to draw them. So let's just get rid of those 2, and that way we will know exactly, okay, so this neuron is focused on area and distance to the city. All right. So as long as we agree on that, let's move on to the next one. Let's take the one in the middle. Here we've got 3 parameters feeding into this neuron. So we've got the area, the bedrooms, and the age of the property. So what could be the reason here? Let's try to understand the intuition, that the thinking of this neuron. How is this neuron thinking? Why is it picking these 3 parameters? What could it be? What could have found in the data, right? So we've already established this is a trained up data set. The training has happened a long time ago, maybe like a day ago, or somebody's already trained up this data. So now we're just applying, and we know that this neuron, through all of the thousands of examples of properties, has found out that the area plus the bedrooms plus the age, combination of those parameters, is important. Why could that be the case? Well, for instance, maybe in that specific city, in those suburbs that this neural network has been trained up in, perhaps there's a lot of families with kids, with 2 or more children, who are looking for large properties with lots of bedrooms, but which are new, right? Which are not old properties, because maybe in that area, most of the properties are kind of like big properties are usually old, but there's lots of modern families, and maybe has been a socio-demographic shift, and or maybe there's been like a lot of some growth in terms of employment and jobs for the younger side of the population. Maybe just the population demographics have changed, and now younger couples or younger families are looking for properties, but they prefer newer properties. So they want the age of the property to be lower. And hence, from the training that this neural network has undergone, it knows that when there's a property with a large area and with lots of bedrooms, with at least three bedrooms for the parents, for the first child, for the second child, for at least three bedrooms, maybe a guest room, when a new property with a high area and lots of bedrooms, that is valued. That in that market, that is valuable. So that neuron has picked that up. It knows that, okay, so this is what I'm going to be looking for. I don't care about the distance to the city in miles, wherever it is, as long as it has high area, lots of bedrooms. As soon as that criteria is met, the neuron fires up. And the combination of these three parameters, and this is where the power of the neural network is coming from, because it combines these three parameters into a brand new parameter, into a brand new attribute that helps with the evaluation, helps with the valuation of the property. It combines them into a new attribute, and therefore it's more precise. So there we go. That's how that neuron works. And let's look at another one. Let's look at the very bottom one. For instance, this neuron could even have picked up just one parameter. It could have just picked up age and not any of the other ones. And how could that be the case? Well, this is a classic example of when age could mean, like, as we all know, the older property is, usually it's less valuable because it's worn out, probably the building is old, probably, things are falling apart, more maintenance is required. So the price drops in terms of the price of the real estate. Whereas a brand new building, it would be more expensive because it's brand new. But perhaps if a property is over a certain age, that could indicate that it's a historic property. For instance, if a property is under 100 years old, then the older it is, the less valuable it is. But as soon as it jumps over 100 years old, all of a sudden it becomes a historic property, because this is a property where people used to live hundreds of years ago. It tells a story. It's got all this history behind it, and some people like that. Some people value that. In fact, quite a lot of people would like that and would be proud to live in a property, and especially in the higher socioeconomic classes, they would show off to their friends or things like that. And therefore, properties that are over 100 years old could be deemed as historic, and therefore this neuron, as soon as it sees a property over 100 years old, it'll fire up and contribute to the overall price. And otherwise, if it's under 100 years old, then it won't even work. And this is a good example of the rectifier function being applied. So here you've got like a zero until a certain point, and then let's say 100 years old, and then after 100 years old, the older it gets, the higher the value, the higher the contribution of this neuron to the overall price. And it's just a wonderful example of, very simple example of this rectifier function in action. So there we go. That could be this neuron. And moreover, the neural network could have even picked up things that we wouldn't have thought of ourselves, right? For instance, bedrooms plus distance to the city. Maybe that's in combination somehow contributes to the price. Maybe it's not as strong as the other neurons and it contributes, but it still contributes. Or maybe it detracts from the price. That could also be the case. Or other things like that. And maybe a neuron picked up a combination of all four of these parameters. And as you can see, that these neurons, this whole hidden layer situation, allows you to increase the flexibility of your neural network and allows you to allows the neural network to look for very specific things. And then in combination, that's where the power comes from. It's like that example of the ants, right? Like an ant by itself cannot build an anthill. But when you have like 1,000 or 100,000 ants, they can build an anthill together, right? And that's the situation here. Each one of these neurons by itself cannot predict the price, but together they have superpowers and they predict the price, and they can do quite an accurate job if trained properly, if set up properly. And that's what this whole course is about, in understanding how to utilize them. There we go. So that is a step-by-step example and walkthrough of how neural networks actually work. I hope you enjoyed today's tutorial, and I can't wait to see you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Now that we've seen neural networks in action, it's time for us to find out how they learn. So let's dive straight into it. There are two fundamentally different approaches to getting a program to do what you want it to do. One is hard-coded coding, where you actually tell the program specific rules and what outcomes you want, and you just guide it throughout the whole way, and you account for all the possible options that the program has to deal with. On the other hand, you have neural networks where you create a facility for the program to be able to understand what it needs to do on its own. So you basically create this neural network where you provided inputs, you tell it what you want as outputs, and then you let it figure everything out on its own. Two fundamentally different approaches, and that is something to keep in mind as we go through these tutorials. Our goal is to create this network which then learns on its own. We're going to avoid trying to put in the rules. And a good example that I can give you right now is, this will come further in the course, but it's just a very visual example. For instance, how do you distinguish between a dog and a cat? For on the left side, on the approach that's depicted on the left, you would program things in like the cat's ears have to be like this, look out for whiskers, look out for this type of nose, look out for this type of shape of face, look out for these colors. You describe all of these things, and you'd have conditions like if the ears are pointy, then cat, if the ears are sloping down, then possibly dog, and so on. On the other hand, for a neural network, you just code the neural network, so you code the architecture, and then you point the neural network at a folder with all these cats and dogs, with images of cats and dogs, which are already categorized, and you tell it, okay, I've got some images of cats and dogs, go and learn what a cat is, go and learn what a dog is, and the neural network will on its own understand everything it needs to understand. And then further down, once it's trained up, when you give it a new image of a cat or a dog, it'll be able to understand what it was. So there they are. Those are the two fundamentally different approaches. And today we're going to slowly start getting into how that second approach works. All right, so let's get straight to it. Here we have a very basic neural network with a one layer. This is called a single layer feed-forward neural network, and it is also called a perceptron. Now, before we proceed, one thing that we do need to adjust is that output value. Right now, you can see that it's just a Y. We need to put a Y hat in there, and the reason for that is usually Y stands for the actual value, and that's what we're going to be using. So Y is going to be the actual value, which we see in reality. Output value is the predicted value by the algorithm, by the neural network. Y hat is the output value. Basically, that's the denomination for the output value. And the perceptron was first invented in 1957 by Frank Rosenblatt. And his whole idea was to create something that can actually learn and adjust itself. And this is what we're going to be looking at now. So we've got our perceptron. Let's see how our perceptron learns. So let's say we have some input values that have been supplied to the perceptron or basically to our neural network. Then the activation function is applied. We have an output. And now we're going to plot the output on a chart. So there it is, our output Y hat. Now, what we need to do is, in order to be able to learn, we need to compare the output value to the actual value that we want the neural network to get, right? And that is the value Y. And so if we plot it here, you'll see that there's a bit of a difference. Now we're going to calculate a function called the cost function. It's calculated as 1/2 of the difference of the squared difference between the actual value and the output value. Now there are many ways you can come up with a cost function. There are many different cost functions that you can use. This is probably the most commonly used cost function, and why it is specifically this function that we use, we'll find out further down when we're talking about gradient descent. But for now, we're just going to agree that this is the cost function. And basically what the cost function is telling us is what is the error that you have in your prediction. And our goal is to minimize the cost function, because the lower the cost function, the closer the Y hat is to Y. Okay, so as long as we agree on that, let's proceed. So basically from here, what happens is there's our cost function. And from here, what happens is now we're going to, once we've compared, now we're going to feed this information back into the neural network. So there we go. There's the information going back into the neural network, and it goes to the weights, and the weights get updated. Basically, the only thing that we have control of in this very simple neural network are the weights, W1, W2, all the way to Wm. And our goal is to minimize the cost function, so all we can do is update the weight. So we update the weights tweak them a little bit, and how exactly we'll find out further down. But for now, we agree that we update the weights, and then we continue. So, but here I've put up this screenshot of the data just to make one point very clear, that right now, throughout this whole experiment, everything we're doing right now, we're dealing with just the one row. So we have a data set of one row where we have, for instance, we're dealing with how long you study, like the variable that we're predicting is what results you're going to get on an exam, and the independent variables that we have is how many hours did you study for, how many hours did you sleep, and what did you get on the quiz in the mid-semester. So in the middle of the semester there's a quiz, what percentage did you get there? So based on those variables, we're trying to predict what score you'll get for the exam. And in exam, the 93%, that's the actual value, so that's y. So we feed these three values into our neural network again for the second time now. And then we're going to be comparing the result to y. So let's see how this works. We feed these values into the neural network, everything gets adjusted, and weights get adjusted. So as you can see, let's do this again. We're going to feed the values. Again, the point here is that we're feeding in these same values. So we only have one row. We're training on one row. This is because this is just a very simple, basic example. Then we'll see what happens when there's more rows. So again, we feed these rows in, our cost functions get adjusted. As you can see, everything happens along those lines again. So as you can see, every time our y hat is changing because we've tweaked the weights, our y hat is changing, our cost function is changing. Let's have a look again. So we feed those in, y hat is changing, cost function is changing. We get information back, feedback to the weights so that the weights get adjusted again. We feed in the same values every time. Everything gets adjusted, goes back to the weights. And one more time, feed in, okay. And another time, so we've adjusted the weights, we feed in the information, and there we go. So now this time the y hat is equal to y, cost function 0. Usually you won't get cost function equal to 0, but this is a very simple example. So hopefully all that made sense. Every time we feed in exactly that same row, because just in this case we're just dealing with that one row, into our neural network, where then the values get multiplied by the weights, the activation function is applied, we get y hat is compared to y, then we see how the cost function has changed, feed that information back into the neural network, and adjust the weights again. And then we repeat the same process again with the same exact row. We're trying to minimize that cost function. So up until now, we've been dealing with just that one row. Let's see what happens when you have multiple rows. So here's the full data set. We have 8 rows of how many hours you slept, or maybe these are different students taking the same exam, how many hours they studied, how many hours they slept before the exam, what they get on the quiz, and their final result on the test. And as you can see here on the left, I've got 8 of these perceptrons. Actually, they are all the same perceptron, so this is also important to understand. I just multiplied it or like duplicated 8 times just so that we can conceptually understand. But the important thing here is the same neural network. We're going to be feeding these into the one same neural network. So let's get started. So one epoch, as you'll hear Hadlan mentioning, one epoch is when we go through a whole data set and we train our neural network on all of these rows. So let's get started. So there's our first row, and there's y hat for the first row. There's the second row, there's y hat for the second row. So again, it's being fed into the same neural network every time. I've just copied them several times so we can visually see how this is happening. Then again, it's happening again. That's third row, fourth row. There's our y hat for the fourth row, and so on. Basically, then we get the same values for the remaining 4 rows as well. So every time we just feed in a row into our neural network, we get a value. Then we compare to the actual values. So there are the actual values. So for every single row, we have an actual value. And now, based on all of these differences between y hat and y, we can calculate the cost function, which is the sum of all of those squared differences between y hat and y, and all of that is halved. And there's our cost function. And basically now what we do after we have the full cost function, we go back and we update the weights. We update W1, W2, W3. And the important thing to remember here is that all of these perceptrons, all of these neural networks is actually one neural network. So there's not 8 of them, there's just one. And when we update the weights, we're going to update the weights in that one neural network. So basically the weights are going to be the same for all of the rows. So it's not the case that every row has its own weights. No, all of the rows share the weights. And so that's why we looked at the cost function, which is the sum of the square differences. And then we updated the weights. And now from here, that was just one iteration. Next, we're going to run this whole thing again. We're going to feed every single row into the neural network, find out our cost function, and do this whole process again. So just as we saw previously, where we had just one row and we were doing everything again and again and again, same thing here, but now we're going to be doing it for 8 rows or 800 rows or 8,000 rows, however many rows you have in your data set. You do this process and then you calculate the cost function. And the goal here is to minimize the cost function and to get, as soon as you've found the minimum of the cost function, that is your final neural network. That means your weights have been adjusted and you have found the optimal weights for this data set that you're training on, and you're ready to proceed to the testing phase or to the application phase. And this whole process is called backpropagation. So some additional reading that you might want to do for the cost function, and I know we just talked about one, and there are many different ones. A good article is located on Cross-Validated. It's called A List of Cost Functions Used in Neural Networks Alongside Applications. So the URL is there, but you can just Google for that exact search term or search phrase, and this one will be the first one that pops up. It's actually got some good examples and application or use cases for different cost functions. So if you're interested to learn more about cost functions, check out this article. And on that note, I hope you enjoyed today's tutorial. I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. In today's tutorial, we're talking about gradient descent. What we learned previously was that in order for a neural network to learn, what needs to happen is backpropagation. And that is when the error, the difference or the sum of square differences between y hat and y is backpropagated through the neural network and the weights are adjusted accordingly. So we saw that, and today we're going to learn exactly how these weights are adjusted. So let's have a look. This is our very simple version of a neural network, a perceptron or a single layer feed forward neural network. And what we can see here is this whole process in action where we've got some input value, then we've got a weight, then a activation function is applied, we get y hat, and then we compare it to the actual value, we calculate the cost function. So how can we minimize the cost function? What can we do about it? Well, one approach to do it is a brute force approach, where we just take lots of different possible weights and look at them and see which one works best. And what we'd do is, for instance, we'd try out, for let's say, for example, 1,000 weights, and we'd try them out. We'd get something like this for the cost function, and this is a chart of on the y-axis you have cost function, on the vertical axis, on the horizontal axis you have y hat, and because you can see the formula is y hat minus y squared, this is what the cost function would look, something like that. And basically you'd find the best one is over here. So very simple, very intuitive approach. Why not do this brute force method? Why not just try out 1,000 different 1,000 different parameters or inputs for weights and see which one works the best? You'll find the best one that way. Well, if you have just one weight to optimize, this might work. But as you increase the number of weights, increase the number of synapses in your network, you have to face the curse of dimensionality. And so what is the curse of dimensionality? The best way to describe this or explain it is to just look at a practical example. So remember this example we had when we were talking about how neural networks actually work, where we were building or running a neural network for proper evaluation. So this is what it looked like when it was trained up already. Well, when it's not trained, before it's trained, before we know what are the weights, the actual neural network looks like this, right? Because we have all these different possible synapses, and we still have to train up the weights. And here we have a total of 25 weights. So 4 times 5 at the start, plus 5 more from the hidden layer to the output layer, 25 weights total. And let's see how we could possibly brute force 25 weights. It's a very simple neural network right here. Very simple, just one hidden layer. And how could we brute force our way through a neural network of this size? Well, let's do some simple mathematical calculations. We have 25 weights, so that means if we have 1,000 combinations that we're going to test out for every weight, the total number of combinations is 1,000 to the power of 25 or 1,000 or 10 to the power of 75 different combinations. Now let's see how Sunway Taihu Lite, the world's fastest supercomputer as of June 2016, how would it approach this problem, right? So Sunway Taihu Lite, it looks like this. It's a whole huge building pretty much for this one supercomputer, and it got the Guinness World Record for being the fastest supercomputer. Right now, it is the fastest supercomputer in the world, and Sunway Taihu Lite can operate at a speed of 93 petaflops. Flop stands for floating operation per second. So it can do 93 to the power times 10 to the power of 15 floating operations per second. That's how quick it is. In comparison, average computers right now, they do like just over several gigaflops and so on. So like kind of those ranges, way less than Sunway Taihu Lite. So Sunway Taihu Lite is in the forefront of technology. And let's say hypothetically that it can do test one combination for our neural network in one flop, basically in one floating operation. That is not possible. That is not practical because you need multiple floating operations to test out a single weight in your neural network. But even let's give it a head start. Let's say that it can do that in a ideal world. It can do that in one floating operation. It can do one test per one floating operation. That means it will still require 10 to the power of 75 divided by 93 times 10 to the power of 15 seconds to run all of those tests, to brute force through that network. So that means approximately 10 to the power of 58 seconds. And that is the same as 10 to the power of 50 years. That is a huge number. That is longer than the universe has existed. And that is definitely not going to, this number is so huge, it's just definitely not going to work for us at all in our optimization. So there we go. This is a no-no even on the world's fastest supercomputer, Sunway Taihu Lite. So we have to come up with a different approach. How are we going to find the optimal weight? By the way, our neural network was very simple. What about if the neural network looks like something like this, right? Or even greater than that? Then, it's just not going to happen at all, ever. So the method we're going to be looking at is called gradient descent, and you may have heard of it already. If not, we will find out what it is right now. So there's our cost function, and now we're going to see how we can come up with a faster way to find the best option. So let's say we start somewhere. You got to start somewhere. So we start over there, and from that point in the top left, what we're going to do is we're going to look at the angle of our cost function at that point. So we're just going to that's why it's called gradient, because you have to differentiate. We're not going to look at the mathematical equations. We will provide some tips on additional reading at the end of the next lecture. But basically, you just need to differentiate, find out what the slope is in that specific point, and find out if the slope is positive or negative. If the slope is negative, like in this case, means that you're going downhill. So to the right is downhill, to the left is uphill. And from there, it means you need to go right. Basically, you need to go downhill. And that's what we're going to do. Vroom. Takes a step, right? The ball rolls down. Again, same thing. You calculate the slope. This time the slope is positive, meaning right is uphill, left is downhill, and you need to go left. And you roll the ball down. And again, you calculate the slope and you roll the ball right. There we go. So that's how you find, in simple terms, that's how you find the best weights, the best situation that minimizes your cost function. Of course, it's not going to be like a ball rolling is going to be a very zigzaggy type of approach, but it's easier to remember, or kind of it's more fun to look at it as a ball rolling. But in reality, yes, you just it is going to be like a step-by-step approach. So it's going to be a zigzaggy type of method. Yeah, and also there's lots of other elements to it. There's things like, for instance, why does it go down? Why does it not like go away over the line? So it could have jumped out of this, gone upwards instead of downwards, and things like that. So there are parameters that you can tweak, and again, we will mention where you can find out more on that. And plus, we'll have this in the practical application. But in the simplest intuitive approach, this is what is happening. We are getting to the bottom by just understanding which way we need to go. Instead of brute forcing through thousands and thousands and millions and billions and quadrillions of combinations, we can just simply every time have a look at which way is it sloping. So right, like you imagine you're standing on a hill, which way does it feel that it's going downwards? And whichever way it is going downwards, you just keep walking that way. You take 50 steps that way, and then you assess again. Okay, which way is it going downwards? This way. Okay, now take 50 steps or less, take 40 steps that way. So it gets less and less and less as you get closer. So here's an example of gradient descent applied in a two-dimensional space. So that was a one-dimensional example. Here we have a two-dimensional space for the gradient descent. As you can see, it's getting closer to the minimum. And it's also called gradient descent because you're descending into the minimum of the cost function. And finally, here's the gradient descent applied in 3 dimensions. This is what it looks like if you project it onto 2 dimensions. You can see it's zigzagging its way into the minimum. So there we go. That was gradient descent. In the next tutorial, we'll talk about stochastic gradient descent. It will be a continuation of this tutorial. And I look forward to seeing you there. Until next time, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about stochastic gradient descent. Previously, we learned about gradient descent and we found out that it is a very efficient method to solve our optimization problem where we're trying to minimize the cost function. It basically takes us from 10 to the power of 57 years to solving a problem within minutes or hours or within a day or so. And it really helps speed things up because we can see which way is downhill and we can just go in that direction and take steps and get to the minimum faster. But the thing with gradient descent is that this method requires for the cost function to be convex. And as you can see here, we've specifically chosen a convex cost function. Basically, convex means that the function looks similar to what we are seeing now, that it's just convexed into one direction and that it, in essence, has one global minimum, and that's the one that we're going to find. But what if our function is not convex? What if our cost function is not convex? What if it looks something like this? Well, first of all, how could that happen? Well, that could happen because if we, first of all, choose a cost function which is not the square difference between y hat and y, or if we do choose the cost function which is like that, but then in a multidimensional space it can actually turn into something that is not convex. And so what would happen in this case if we just try to apply our normal gradient descent method? Something like this could happen. We could find a local minimum of the cost function rather than the global one. So this one was the best one and we found the wrong one, and therefore we don't have the correct weights. We don't have an optimized neural network. We have a subpar neural network. And so what do we do in this case? Well, the answer here is stochastic gradient descent. And it turns out the stochastic gradient descent doesn't require for the cost function to be convex. So let's have a look at the two differences between the normal gradient descent that we talked about and the stochastic gradient descent. So normal gradient descent is when we take all of our rows, we plug them into our neural network. And once again, here we've got the neural network copied over several times, but the rows are being plugged into that same neural network every time. So there's only one neural network. This is just for visualization purposes. And then once we've plugged them in, we've calculated our cost function based on the formula on the right and looking at the chart at the bottom. And then we adjust the weights then. And this is called the gradient descent method, or it's also the proper term is the batch gradient descent method. So we take the whole batch of from our sample, we apply it, and then we run that. The stochastic gradient descent method is a bit different. Here we take the rows one by one. So we take this row, we run our neural network, and then we adjust the weights. Then we move on to the second row. We take the second row, we run our neural network, we look at the cost function, and then we adjust the weights again. And then we take another row, take row 3, we run our neural network, we look at the cost function, we adjust the weights. So basically, we're looking at we're adjusting the weights after every single row rather than doing everything together and then adjusting weights. Two different approaches, and now we're going to just compare the two side by side. So here they are. This is how to visually remember them. So you've got the batch gradient descent where you're adjusting the weights after you've run them, after you've run all of the rows in your neural network. And then basically you adjust the weights and you run the whole thing again, iteration, iteration, iteration. In the stochastic gradient descent method, you run one row at a time and you adjust the weights, you adjust the weights, you adjust the weights, and then you do everything again and again. And that is called the stochastic gradient descent method. The main two differences are that the stochastic gradient descent method helps you avoid the problem where you find those local extremos or local minimums rather than the overall global minimum. And the reason for that in simple terms is that the SGD, or the stochastic gradient descent method, has much higher fluctuations because it can afford them. It's doing one iteration or one row at a time, and therefore the fluctuations are much higher, and it is much more likely to find the global minimum rather than just the local minimum. And the other thing about the stochastic gradient descent method compared to the batch gradient is it's faster. Like the first impression that you might have is because it's doing every single row one at a time, it's slower, but actually, in fact, it is faster because it doesn't have to load up all the data into memory and run and wait until all of those rows are run all together. It can just run them one by one, so it's a much lighter algorithm. It's much faster in that sense. So though it has way more, in those senses, it has more advantages over the batch gradient descent method. The main advantage of, or the main kind of like pro for the batch gradient descent method is that it is a deterministic algorithm rather than stochastic gradient descent being a stochastic algorithm, meaning it's random. And with the batch gradient descent method, as long as you have the same starting weights for your neural network, every time you run the batch gradient descent method, you will get the same iterations, the same results for your for the way your weights are being updated. For the stochastic gradient descent method, you won't get that because it is a stochastic method. You're picking your rows possibly at random, and you are updating your neural network in a stochastic manner, and therefore you're just going to, every single time you run the stochastic gradient descent method, even if you have the same weights at the start, you're going to have a different process, different iterations to get there. So that's in a nutshell what stochastic gradient descent is. Also, there's a method in between the two called the mini batch gradient descent method, where you combine the two and you basically run, rather than running a whole batch or running one at a time, you run batches of rows, maybe 5, 10, 100, however many rows you decide to set. You run that number of rows at a time, then you update your weights, then you update your weights, and so on. And that's called the mini batch gradient descent method. If you'd like to learn more about gradient descent, there's a great article which you can have a look at. It's called A Neural Network in 13 Lines of Python, Part 2, Gradient Descent by Andrew Trask. And the link is below. It's on GitHub. 2015 article. Very well written, in very simple terms. It's got some interesting philosophical or just interesting thoughts on how to apply gradient descent, what are the advantages and disadvantages, and how to do things in certain situations. So it's got some very cool tips, tricks, and hacks. Very easy read, so definitely check that out. And another one, a bit more heavier read for those of you who are into mathematics, who want to get to the bottom of the mathematics, why gradient descent is that specific, what are the formulas that are driving gradient descent, how is it calculated, and so on. Check out the article, or actually the book. It's a free online book called Neural Networks and Deep Learning by Michael Nielsen, 2015 book. It's just basically, it's all online. You can go ahead and check it out there. And they're, again, very soft introduction to the mathematics, but the mathematics are pretty heavy as you go along, as you read through the article. But at the same time, it gets you into that mood. I think even it has like a warm-up chapter where you first warm up with the math and then you jump into them. So interested in math, then this is the article to go to. And there we go. So that's in a nutshell the difference between gradient descent and stochastic gradient descent, and how the two work. And on that note, we're going to wrap up today's tutorial. I look forward to seeing you on the next one, and until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're going to wrap up with backpropagation. All right, so we already know pretty much everything we need to know about what happens in the neural network. We know that there's a process called forward propagation, where information is entered into the input layer and then it's propagated forward to get our y-hats, our output values, and then we compare those to the actual values that we have in our training set, and then we calculate the errors. Then the errors are back propagated through the network in the opposite direction, and that allows us to train the network by adjusting the weights. So the one key important thing to remember here is that backpropagation is an advanced algorithm driven by very interesting and sophisticated mathematics, which allows us to adjust the weights, all of them at the same time. All of the weights are adjusted simultaneously. So if we were doing this manually, or if we were coming up with a different type of algorithm, then even if we calculated the error and then we were trying to understand what effect each of the weights has on the error, we'd have to somehow adjust each of the weights independently or individually. The huge advantage of backpropagation, and this is a key thing to remember, is that during the process of backpropagation, simply because of the way the algorithm is structured, you are able to adjust all of the weights at the same time. So you basically know which part of the error each of your weights in the neural network is responsible for. Now, that is the key fundamental underlying principle of backpropagation, and this was why it picked up so rapidly in the 1980s, and this was a major breakthrough. And if you'd like to learn more about that and how exactly the mathematics works in the background, then a good article, which we've already mentioned, is the Neural Networks and Deep Learning. It's actually a book by Michael Nielsen. There you'll find the mathematics written out, and it'll help you understand how exactly this is possible. But for now, for our purposes, if from an intuition point of view, the important part is to remember that that's what backpropagation does. It adjusts all of the weights at the same time. And now we're going to just wrap everything up with a step-by-step walkthrough of what happens in the training of a neural network. All right, so step one, we randomly initialize the weights to small numbers close to 0 but not 0. We didn't really focus on the initialization of weights during the intuition tutorials, but the weights have to start somewhere, and they are initialized with random values near 0, and from there, through the process of forward propagation, back propagation, these weights are adjusted until the error is minimized, until the cost function is minimized. Then step 2, input the first observation of your dataset, so the first row, into the input layer. Each feature is one input node. So basically take the columns and put them into the input nodes. Step 3, forward propagation. From left to right, the neurons are activated in a way that the impact of each neuron's activation is limited by the weights. So the weights basically determine how important each neuron's activation is. Then propagate the activations until getting the predicted result, y hat in this case. So basically you propagate from left to right, you go all the way until you get to the end and you get your y hat. Then compare the predicted result to the actual result, measure the generated error. And then you do the backpropagation. From right to left, the error is backpropagated. Update the weights according to how much they're responsible for the error. Again, you are able to calculate that because of the way the backpropagation algorithm is structured. The learning rate decides by how much we update the weights. The learning rate is a parameter you can control in your neural network. Step 6, repeat steps 1 to 5 and update the weights after each observation. That is called reinforcement learning, and in our case that was stochastic gradient descent. Or repeat steps 1 to 5 but update weights only after a batch of observations. So batch learning, it's either full gradient descent or batch gradient descent or mini batch gradient descent. And step 7, when the whole training set passed through the artificial neural network, that makes an epoch. Redo more epochs. So basically you just keep doing that and doing that and doing that until allowing your neural network to train better and better and better and constantly adjust itself as you minimize the cost function. So there we go. Those are the steps you need to take to build your artificial neural networks and train it. And these are the steps that you will be taking together with Hadelan in the practical tutorials. Wish you the best of luck, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome to the section on convolutional neural networks. Super excited that you're joining us for this section as well. And today we're going to cover off the plan of attack, how we're going to learn everything in this section. There's so much to learn. Let's see how we're going to approach this. All right, what we'll learn in this section. First of all, we'll talk about what convolutional networks actually are. Very important to understand the end goal that you're working towards before you actually start working towards it. So we'll talk about features, we'll have a look at a few little examples, we'll compare the human brain to artificial neural networks in terms of image recognition. So it'll be a fun, light tutorial to get us started for this whole section. Then we'll talk about step 1, diving straight into it, convolution operation. So this part of the course contains several steps that we need to go through in order to build a convolutional neural network, and that's how these tutorials are going to be broken up. So this one's going to be step 1, the convolution operation. We'll learn everything about feature detectors. We'll talk about which are also filters. We'll talk about feature maps and what are the different parameters there, what they mean, and we'll have a look at some visual examples as well. Then we'll talk about step 1, part B, the ReLU layer or ReLU layer, which is the rectified linear unit, and we'll talk about why linearity is not good and how we want more non-linearity in our network for image recognition. Then we'll talk about step 2, pooling, and we'll understand how pooling works. We'll talk specifically about max pooling, and we'll also mention a couple of things about mean pooling or sum pooling and other approaches that you can take to the process of pooling. Also in this lecture, we'll have a really cool example. So there'll be a very visual interactive tool that we're going to look at. So make sure to stick around to the end of that lecture because that's going to add a lot of value to your learning process, what we're going to discuss at the end there. Step 3, flattening. So here it's going to be a quick tutorial on how to proceed from your pooled layers to your flattened layer. And then we're going to talk about full connection. So this is the very meaty tutorial that puts everything together and puts everything into perspective and actually shows you how everything works at the end of the day and how those final neurons understand how to classify your image. Very, very important tutorial. And hopefully that will summarize or kind of put everything together for you. And finally, we'll have a summary which will summarize everything we've talked about. And as an extra little feature, I've included a tutorial on softmax and cross entropy. So you don't have to take this tutorial, but I thought it would be a great addition of knowledge, because these are terms that you will come across when dealing with convolutional neural networks. So maybe take it right away. Maybe when you come across these terms, you will always know you can come back to this course and take this tutorial to understand better what softmax and cross entropy are. And also, as always, throughout these tutorials, there will be lots of recommended reading for you to further upskill and get more knowledge. And on that note, I can't wait to see you on the first tutorial. This is going to be a very fun and exciting section. And until next time, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're kicking off convolutional neural networks. This is going to be exciting. Let's dive straight into it. We're going to start off with an image. What do you see when you look at this image? Do you see a person looking at you, or do you see a person looking to the right? You can see that your brain is struggling to adjust. If you look to the right side of the image, just look at the right border of the image, you'll see a person looking to the right. If you look at the left border of the image, you'll see a person looking at you. And this just proves that what our brain is looking for when we see things is features. Depending on the features that it sees, depending on the features that you process, you categorize things in certain ways. So when you look on the right side of the image, you see certain features of a person looking to the right because they're closer to your center of focus. And therefore, your brain classifies it as a person looking to the right. When you look to the left side of the image, you see more features of a person looking at you. And therefore, your brain classifies it as such. So let's have a look at another one. This is a very famous image. You probably have already seen it. But what do you see here? So some people will say that they see a young lady wearing a dress looking away. Some people will say they see an old lady wearing a scarf on her head looking down. So I'm going to point these features out and you'll see that it'll become very obvious. So this is the face of the young lady looking away. She's looking into the distance. That's her coat, that's her hair, that's her little feather in her hair. And on the other hand, this is the head of the old lady looking down. That's her nose, that's her mouth, that's her chin, that's the scarf on her head, and she's looking down. So as you can see, 2 in 1, and depending on which features your brain picks up, it will switch between classifying the image as one or the other. The oldest one of these illusions recorded in the printed work is this one. It's the duck or the rabbit. So is this a duck or is this a rabbit? Another example. And now I'm going to show you an image which will just, for a second, just look at it and see what emotions or what kind of experience, visual experience you go through. So what do you see? Do you feel like a bit, not dizzy, but a bit dazzled? Like your brain is trying to understand what it is. Like it's jumping between her eyes, the up and down eyes. And this is a classic example of when there are certain features where it could be this, it could be that, but your brain cannot decide. And because both seem plausible. And so basically all these examples illustrate to us how the brain works, that it processes certain features on an image or on whatever you see in real life, and it classifies that as such. And you've probably been in situations when you look over your shoulder quickly and you see something, you think it's, I don't know, if it's like a ball, but it turns out to be a cat, or you think it's a car, but it turns out to be a shadow, and things like that. That's because you don't have enough time to process those features, or you don't have enough features to classify things as such. And this is, for me, this is very interesting, because what we're going to be doing with neural networks, with convolutional neural networks, is very similar. And you'll find that the way that computers are going to be processing images is going to be extremely similar to the way we are processing images. So it's very valuable to understand and just kind of remember these things, that this is how we do it. And I'm going to take this lady off your screens because she's probably already freaking you out by now. So here's something different. Here's an experiment. An experiment done on computers, on convolutional neural networks. So we're slowly moving now from humans to computers. And this slide is from a talk by Geoffrey Hinton. And here you have, basically it describes an experiment that he had done on some convolutional neural networks that he had trained up. So here you see 3 images, and we're going to go through them left to right and see how you would classify them and then see how the computer classified them. So on the left, what do you think this is? You probably said cheetah, and you will be right, and this is what the computer said. So, and right away, right off the bat, we're going to learn how to read these images, because if you're going to go deep into convolutional neural networks, no pun intended, if you're going to start learning more and more about them and using them, you'll see a lot of these. So, and I've actually seen people read them incorrectly. So here at the top, cheetah is what it actually is. So that's the actual correct label of the image. That's what the label of the image is, regardless of any processing and computer vision. And then here are the guesses, the top 4 or 5 sometimes guesses of the algorithm, and they're given the probability. So the computer said, or the neural network said, cheetah, leopard, snow leopard, or Egyptian cat can be one of the 4, and cheetah has the highest vote. And throughout this part of the course, you will understand what these votes mean and how they are derived. But for now, it's pretty intuitive, right? So it's a cheetah in reality, and the neural network guessed right. It said with a high probability, about like 95, 99%, it's a cheetah. Then the second one, what do you think that is? That is a bullet train. And the neural network was able to distinguish between bullet train, passenger car, subway train, electric locomotive. Those are the top choices. Of course, it had many more options. These neural networks learn to distinguish from not just 4 categories, from dozens, thousands of categories at the same time. So those are the 4 options that it picked. And so that's bullet train, and it's bullet train. So what do you think the last one is? There are a couple of options, right? It's not very clear what it is. It could be a frying pan, it could be a magnifying glass, it could be even maybe a pair of scissors, some might say. Well, the neural network said it was a pair of scissors. But you can see how you can go wrong here. First of all, it's not a very clear image, and also you can see that the probabilities are not as clear here. So the neural network was a bit confused, a bit indecisive, just as we are. So it said scissors with the highest probability, but then it had hand glass, which it actually was, with not so far away on the second place, and frying pan, stethoscope. So basically, here you can see that scissors was its first guess, but the correct option was number 2, and that's why it's highlighted in red. So there we go. That's what neural networks are already capable of, and this is actually quite an old slide. This was several years ago. Now they're even better, and you will see that from the practical application that you will be coding together with Hadoop. But now let's try and understand a bit better what convnets, or convolutional neural networks, actually are, and why are they gaining so much popularity. And they actually are gaining popularity. So you can see here a Google Trends comparison I did just yesterday. Here you can see that convolutional neural networks are even taking over artificial neural networks. So a massive increase, and they're just going to keep going that way, because it is a very important field. That is where all the things happen, such as like self-driving cars. How do they recognize people on the road? How to recognize stop signs and things like that? How is Facebook able to tag images or people in images? And not only just like, remember previously, years ago, you had to tag people yourself, then it would recognize faces, you had to add the names, and now it just recognizes the faces and adds the names at the same time. Well, that is what convolutional neural networks are capable of. And speaking of Facebook, if Geoffrey Hinton is the godfather of artificial neural networks and deep learning, then Yann LeCun is the grandfather of convolutional neural networks. Yann LeCun is a student of Geoffrey Hinton's, and in fact, here you can see them together. And Geoffrey Hinton now is pioneering deep learning at Google. Yann LeCun is the director of Facebook Artificial Intelligence Research and also a professor at NYU. So slowly I love this part of the course. Slowly we're building up this these names, or this kind of picture of the profiles of the people who are driving this field. And in the next couple of parts, we'll get to know about a few more, and we'll have this whole mafia, as they call themselves, or Jan LeCun calls them, mafia or conspiracy of deep learning, and you'll learn a bit more about how this whole field developed. And these are just some great people. And so Jan LeCun, back in the 80s and the 90s, made significant contributions to the field of convolutional neural networks, and as we'll see throughout this course, has been able to develop or help the world develop something so extremely powerful. So moving on to how convolutional neural networks work. You have an input. It's very simple. It's very straightforward. So you have an input image, it goes through the convolutional neural network, and you have an output label, so it classifies that image as something like as a cheetah or a bullet train or something else. Now, kind of like going into a bit more detail, for instance, you can, after a neural network has been trained up on certain images, on certain classified images or categorized images that have been categorized prior, after that you can give it, let's say a neural network has been trained up to recognize facial expressions, emotions. You can give it a face of a smiling person. It's not just a face like a drawing of a face like this, but actual face of a person smiling, and it will tell you that that person is happy. And you can give it a face of a person that's frowning. It will tell you that that person is sad. It can recognize these emotions, and as you can see, that's already very powerful in terms of so many different applications just of this one example you can think of right away. And in both cases, it will give you a probability. So it won't say, with 100% the person's happy or sad. It'll be 99 or 98 or maybe 80% when it's unclear of what's going on. And just like we are, right? Sometimes we can mistake things for what they're not, or sometimes we can sometimes it's just not clear if the person is smiling or frowning, or if it's a dog or a cat, or if it's a train or a bullet train, right? Sometimes we haven't seen enough features, and it all goes down to features, because that's how we process visual information, as we saw from the start of this tutorial. So, but how is a neural network able to recognize these features? Well, it all starts at the very basic level. Let's say you have an image, you have two images. One is a black and white image of 2 by 2 pixels, and one is a colored image of 2 by 2 pixels. Well, neural networks leverage the fact that the black and white image is a two-dimensional array. So the way we see it right now on the left is just the visual representation, right? So it's some kind of picture, and for simplicity's sake, it's just a 2 by 2 picture. But in computer terms, it's actually a two-dimensional array with every single one of those pixels having a value between 0 and 255. So that's eight bits of information. 2 to the power of 8 is 256. So therefore, the values are from 0 to 255, and that's the intensity of the color. And in this case, the color white. So 0 will be a completely black pixel, 255 will be a completely white pixel, and between them you have the grayscale range of possible options for this pixel. And based on that information, computers are able to then work with the image. And that's kind of like the starting point, that any image has a digital representation, has a digital form, and those are just basically ones and zeros that form a number 0 to 255 for every single pixel. And that's what the computer works with. It doesn't actually work with colors or anything. It works with the ones and zeros at the end of the day. That's kind of like the foundation of it all. And in a colored image, it's actually a three-dimensional array. You've got blue pixel, you've got a blue layer, a green layer, and a red layer, and that stands for RGB, red, green, blue. And each one of those colors has its own intensity. So basically, a pixel has three values assigned to it. Each one of them is between 0 and 255. And therefore, you can find out what this image, what color exactly this pixel is by combining those three values. And again, computers are going to be working with that. So that's the foundation of it all. That's the red channel, the green channel, the blue channel. And finally, let's have a look at, for instance, an example, a very trivial example of a smiling face in computer terms. If we just really simplify things instead of having from 0 to 255. Instead of having those values, just so that we can understand things better and really grasp the concepts, we're going to say 0 is white, 1 is black, right? So we're just going to simplify things to the extreme, and you will see that that image can be represented like that. So the reason why we've brought this up is because we're going to, all of our intuition tutorials, we're going to structure on images like this, which are very simple, but at the same time, then all of those concepts can translate back to the 0 to 256 range of values, and everything applies the same way there. And the steps that we're going to be going through with these images are step number 1, convolution, step number 2, max pooling, step number 3, flattening, and step number 4, full connection. And I can imagine that probably none of these words mean much to you at the moment, but by the end of this section of the course, you will understand them in great detail and exactly what they're doing. So we'll get started in the next tutorial. For now, the additional reading that you might want to look into is Jan LeCun's original paper that gave the rise to convolutional neural networks. It's called Gradient-Based Learning Applied to Document Recognition. You may have seen this image before floating around the internet. It is from that paper. So if you want to go back to the very beginnings of how it all happened, where it all came from, this is the paper to look into. And I look forward to seeing you on the next tutorial. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. In the previous tutorial, we found out what convolutional neural networks are all about. And today we're going to dive into step 1, convolution. So this is the convolution function. I know we try to stay away from mathematics and keep things intuitive, but I couldn't help but share this formula with you because it is so simple. A convolution is basically a combined integration of two functions, and it shows you how one function modifies the other or modifies the shape of the other. And if you've done any signal processing or electrical engineering or a profession where signal processing is required, you would have inevitably come across the convolution function. It is quite popular. Now, once again, we're going to keep the mathematics light or keep them separate. And if you'd like to get into the math behind the convolutional neural networks, a great additional read is Introduction to Convolutional Neural Networks by Jianxin Wu, who is a professor at the Nanjing University in China. This paper was published literally days ago, like 5 or 6 days ago, and it is oriented specifically at people who are starting out, at beginners who are getting to know convolutional neural networks. So the mathematics there should be accessible. I actually emailed Professor Xianxin Wu, and he said his whole goal is to break the complex things down so that people who are new to this field can understand. And also he mentioned that he's got some materials available on his homepage. So if you, in the URL, if you just remove the last 2 parts and you just go to /WJX to that part, that's his homepage, and you'll be able to find more additional tutorials and materials which haven't been published as papers, but he uses them in his tutorials. So you might find those useful. So browse around there if you'd like to get an introduction into the mathematics behind convolutional neural networks and kind of build a solid base around that area. But we're going to move on, and we're going to talk about the convolution. So what is a convolution in intuitive terms? Here on the left, we've got an input image, as we discussed. That's how we're going to look at images, just ones and zeros to simplify things. And you can see the smiley face there. Then we've got a feature detector. So a feature detector is a 3x3 matrix. Does it have to be 3x3? No, it doesn't. AlexNet, I think, uses 7x7. And then some other, one of those other famous ones uses like 5x5 feature detectors. They can be different, but usually you'll see that they are 3x3, and they are reasons to make them 3x3. So we're going to stick to the convention of having a 3x3 feature detector. Also, the feature detector is called, these are important terms because you might come across them. There are many different terms for the feature detector, but the most common ones are feature detector, or you might hear it being called kernel, or you might hear it being called filter. So in this course, we're going to be using either filter or feature detector interchangeably, but just bear in mind that it has those names. And a convolution operation is signified by an X in a circle, just as you saw in the formulas before. And here what happens is, on an intuitive level, or just to think of it in terms of what is actually happening in the background rather than the mathematics, well, you take this feature detector or filter and you put it on your image like you see on the left. So you cover the, for instance, in this case, the top left corner, the 9 pixels in the top left corner, and you basically multiply each value by each value, so respective value. So the top 0 by the top left value by the top left value, then basically position number 1 1 by position number 1 1, position by number, or 0 1 by 0 1, 0 2 by 0 2, and so on. So just it's element wise multiplication of these matrices, and then you add up the results. So in this case, nothing matches up, so it's always either a 0 by 0 or 0 by 1, so the result is 0. Here you can see that one of them matched up. The one on the left matched up, and therefore we got a 1. Here nothing matched up, nothing matched up, nothing matched up. Then we move on to the next row. So and the step at which we're moving this whole filter is called the stride. So here we have a stride of 1 pixel. So here you can see again something matched up. The bottom right corner matched up. Again, stride, bottom one in the middle matched up. Here top right one matched up, then nothing matched up. The stride is 1. You can change the stride. You can make it 1, 2, you can make it 3, whatever you like. The conventionally the one that works well is usually a 2, so that's what people stick to, and we'll talk about what the stride is towards the end of this tutorial. So here we've got we're matching up, so we just keep going. Oh, here you can see we've got a 2 because 2 of them matched up, and so on and so on, so on. And there we go. There's another one that matched up. There we go. And there we're done. So what have we created, right? A couple of important things here. The image on the right is called a feature map. Also has several terms. It also can be called sometimes a convolved feature. So when you apply a convolution operator to something, it doesn't become convoluted, it becomes convolved. And yes, sometimes I think to myself in the wrong way, but it's the correct term is convolved. It's a convolved feature, or it can also be called the activation map, but we're going to be calling it a feature map in this course. So it can be called any one of those things. And what have we done here? Well, as you can see, we've reduced the size of the image. That's number one. And that's the important thing I wanted to mention about your input image and the feature detector and the stride, right? If you have a stride of 1, you can see the image reduced a bit. But if you have a stride of 2, the image is going to reduce more. So the feature map is going to be even smaller. And that's a very important function of the feature detector of this whole convolution step, is to make the image smaller because it'll be easier to process it, and it'll be just faster. It'll be just faster because imagine, like here we've got a 7 by 7 image, but imagine if you have a proper photo, right? Or you have like a 256 by 256 pixel image. It's a huge number of pixels, right? 256 squared, or like let's say you have a 300 by 300 pixels. So we don't get confused with the RGB 256. Let's just say like we have a 300 by 300 image in terms of size in pixels. Then you have 300 squared number of pixels. That's a huge number, and therefore feature detectors will reduce the size of the image, and therefore stride of 2 is actually beneficial. But then the question is, do we lose information? Are we losing information when we're applying the feature detector? Well, some information we are losing, of course, because we have less values in our resulting matrix. But at the same time, the purpose of the feature detector is to detect certain features, certain parts of the image that are integral. And so, for instance, if you think about it this way, like the feature detector has a certain pattern on it. The highest number in your feature map is when that pattern matches up. In fact, the highest number you can get is, in a now simplified example, is when the feature matches exactly. And you can see with that number 4 we have in our feature map, that's exactly, so if you look over here, that's exactly where this feature detector, because there's only 4 ones in it, matched perfectly. So you can see this part over here. So the feature was detected here. And as we discussed at the very start of this section, that is, features is how we see things, is how we recognize things. We don't look at every single pixel, so to speak, in what we see on an image or in real life. We don't look at every single pixel. We look at features. We look at the nose, the hat, the feather, the eyes under, or the little black marks under the cheetah's eyes, to distinguish it between a cheetah and a leopard, or the shape of the train. We don't to distinguish it between a bullet train and a normal train, and so on. So we don't look at everything. We look at features, and that's what we're preserving, and that's what the feature map helps us preserve. Actually, that's what it allows us to bring forward and get rid of all of the unnecessary things that even as humans we don't process. There's so much information going into your eyes at any given time, like gigabytes of information. If you look at every single dot, if not terabytes of information going into your eyes per second, and still we're able to process that because we get rid of what is unnecessary. We only focus on the important features that are important to us. And that is exactly what the feature map does. So now moving on, this is our input image, and we create a feature map. So the front one, let's say the front one is the one we just created. But then how come there's many of them? But we create multiple feature maps because we use different filters, right? And that's another way that we preserve lots of the information. So we don't just have one feature map. We look for certain features, and then or basically the network decides through its training, and this is something we'll discuss towards the end of this section, through its training, it decides which features are important for certain types or certain categories, and it looks for them, and therefore it'll have different filters, and we'll talk about filters just now, but basically it'll apply these filters. So to get this feature map, it applied a filter like the one we saw, but then to get this feature map, it applied a different filter. To get this feature map, it applied a different filter, and so on. And so basically it just creates these feature maps. And actually that's why personally I think the term feature detector is better than filter. So remember over here we have this filter, which we also can call a feature detector. Well, actually the word feature detector I think is better suited. And the reason for that is that's what the purpose is, right? We don't want to just filter out our image, but even though that's the same, just a question of terminology. But basically, we want to detect features. All right, in this layer, we're going to, or in this feature map, we've detected where certain features are in the image. In this feature map, we've detected where certain other features are, where a certain specific feature is located. In this feature map, we've detected where a certain other feature is located on the image. So that's what we're doing, and let's have a look at a couple of examples. So here we're using, and this is from gimp.org, their documentation. It's a free like a kind of tool like Paint, and you can use it to adjust your images or work with your images. But basically, they have some valuable examples in their documentation, and here they have a picture of the Taj Mahal, and you can choose which filter you want to apply. So if you download this program and you upload a photo into it, and then you can actually start a convolution matrix and apply filters, and you will see that these convolution matrices are actually applied in image processing and design and so on. So let's have a look at what we get. So if we apply this filter, 5 in the middle, -1, -1, -1, -1, you can see that it sharpens the image. And yeah, so it's quite intuitive if you think of it. So 5 is the pixel, the main pixel, like in the middle of the filter or the feature detector, and then -1, -1, -1 just kind of like reduces the pixels around it in an intuitive sense. Then blur. So basically, it takes gives equal significance to all of the pixels around the one in the center, and therefore it combines them together and you get a blur. Edge enhance. So here you can see that -1 and 1, and then you get zeros, right? So you remove the pixels around the main one in the middle, and you only keep this one at a -1, and it gives you an edge enhance. This one's a bit harder to understand how it works. Like probably harder just to think of it intuitively. Edge detect, right? So this one probably makes more sense, right? You take the middle one, you reduce the middle one, probably like the strength of the middle pixel, and then you look for the ones, you look for these ones, you increase the strength of the ones around them, so you have the ones there. Yeah, so that gives you like an edge detection, and you can see what you get there. Emboss, another one. So the key here is that it's asymmetrical, and you can see the image becomes asymmetrical as well. So you got like that kind of feeling that it's standing out towards you, and that's what you get when you have like minuses here and pluses here. Again, this is getting a bit technical now, but at least we can get some kind of intuitive understanding. Let's just go quickly through them again. So there's sharpen, there's blur, there's edge enhance, there's edge detect, there's emboss. And so as you can see, these are great examples of the same image, but we're getting feature maps. So we use different feature detectors to get different feature maps of the same image. And therefore now we have lots of this versions of this image, where in each one we've tried to detect certain things. These terms, they're not applicable to us. Except like emboss is probably not applicable to us in terms of convolutional neural networks, but edge detect, that's important. We want to detect the edges. Edge enhance, probably not. Blur, sharpen. So certain things like edge detect is probably the most important one for our type of work. And in terms of understanding, like computers, they will decide for themselves. Their neural network will decide for itself what's important, what's not, and it probably won't be even recognizable to the human eye. You won't be able to understand what those features mean, but the computer will decide. And that's the beauty that of neural networks, that they can process so many different things and understand without even having that intuition, without having that explanation why. They will understand which features are important to them, whether we have a name for them or not. That's an irrelevant question for the artificial neural network. And my favorite one, here's a image of Geoffrey Hinton, a photo of Geoffrey Hinton passed through one of these filters. All right, so that brings us to the end of today's tutorial. I hope you enjoyed learning about convolution. The key takeaway is that convolution, the primary purpose of a convolution is to find features in your image using the feature detector, put them into a feature map, and by having them in a feature map, it still preserves the spatial relationships between pixels, which is very important for us to, because if they're completely jumbled up, then we've lost the pattern. And at the same time, it's important to understand that most of the time, the features a neural network will detect and use to recognize certain images and classes will mean nothing to humans, but nevertheless, they work. And that's what convolution is, and I look forward to seeing you on the next tutorial. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about ReLU, which is rectified linear units, and this is an additional step on top of our convolution step. So it's not a separate big step, it's a small step, it's step 1b basically. And what is going on here? Well, we have our input image, we have our convolution layer, which we've discussed, and then on top of that, we're going to apply, wait for it, our favorite rectifier function. And you're already familiar with the rectifier function from the previous section on artificial neural networks. And so sometimes authors or instructors separate the convolution and the rectifier as two separate steps. In our examples, we're just going to consider them just one big step. First the convolution, then the rectifier. And the reason why we're applying the rectifier is because we want to increase non-linearity in our image, or in our network, in our convolutional neural network. And rectifier acts as that filter, or acts as that function which breaks up linearity. And the reason why we want to increase non-linearity in our network is because images themselves are highly nonlinear, especially if you're recognizing different objects next to each other, or just on backgrounds and stuff like that. Like the image is going to have lots of non-linear elements, and the transition between pixels, adjacent pixels, is often going to be non-linear. That's because there's borders, there's different colors, there's different elements in your images. But at the same time, when we're applying a mathematical operation such as convolution, running this feature detection to create our feature maps, we risk that we might create something linear, and therefore we need to break up the linearity. So let's have a look at an example. Here is an original image. Now, when we apply a feature detector to this image, we get something like this. So you can see here that black is negative, white is positive values. Well, when you apply a feature detector to a proper image, which has not just zeros and ones, but has lots of different values, and you apply, as we saw previously, feature detectors can have negative values in themselves. Sometimes you'll get negative values. And here, their black ones are negative, white ones are positive. And what a rectified linear unit function does is it removes all the black, right? Anything below 0 turns into 0. And so from this, it turns into this, right? And so it's pretty hard to see what exactly is the benefit in terms of breaking up linearity. I'll try to show an example on this image, but at the end of the day, this is a very mathematical concept, and we would have to go into a lot of math to really explain what is going on. But let's have a look. So, for instance, let's look at this building here, right? So this is a building on its own. Then you can see this shadow, this black part, this shadow over here. Well, you can see that it's white, the reflection of the light, and then it's a gray, and then it gets darker, and then it gets darker again, right? So, and when we take it out, we take out that black part. So think of it in terms of linearity, right? So it looks like when you go from white to gray, the next step would be black, right? The next step would be black. It's a linear progression from bright to dark, and therefore this is kind of like a linear situation. When you take out the black, you break up the linearity. Let's try another one. Let's have a look here. And at the same time, it's still that same building, right? It's not like it's not like you're blending two buildings into each other. But that is secondary. The main point is breaking up the linearity. So let's have a look here. Same thing. So you see white, gray, black, gray, white. And when you break it up, you don't have that anymore, right? You don't have that progression, the gradual progression, that you just have like an abrupt change, and that helps introduce non-linearity into your image. It's a very rough explanation, very kind of like on the fingers explanation, rather than technical, but hopefully it kind of helps you understand a bit better what we're talking about here. So here again, you can see white, gray is a better example even. You see bright, darker, 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 darker. So this part looks like it's linear, then you break it up like that. Again, so this is a very rough explanation. It's not absolutely perfect, but at least it gives you some idea of what's going on. But if you'd like to learn more, there's a good paper. As always, there's always a paper. This one is by CCJ Kuo from the University of California, and it's called Understanding Convolutional Neural Networks with a Mathematical Model. And basically there he answers two questions, and you need to just look at the first one, and the question is why a nonlinear activation function is essential at the filter output of all intermediate layers. So that kind of explains it in a bit more detail, both in terms of intuition and mostly in terms of mathematics. So that's an interesting paper where you can get some more additional information on this topic. And if you really want to dig in and explore some cool stuff here, then there's another paper that you might be interested in. It's called Delving Deep into Rectifiers, Surpassing Human Level Performance on Image and Net Classification. And here the authors, Kai-Ming He and others from Microsoft Research, they propose a different type of rectified linear unit function. They propose the parametric rectified linear unit function, which you see here on the right, and they argue that it delivers better results without sacrificing performance. So interesting read if you'd like to get a bit more into this topic. And that's all for today. The ReLU layer is pretty simple, pretty straightforward, just applying the rectifier function. And I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about max pooling, and we've got some very exciting slides coming up ahead and even a special surprise at the very end of the tutorial. So let's get started. The first question is, what is pooling and why do we need it? Well, to answer that question, let's have a look at these images. On these three images, we've got a cheetah. In fact, it is the same exact cheetah. On the first image, the image is positioned properly and the cheetah is looking straight at you. On the second image, it's a bit rotated, and the third image is a bit squashed. And the thing here is that we want the neural network to be able to recognize the cheetah in every single one of these images. In fact, this is just one cheetah. What if we have lots of different cheetahs? Here's a cheetah, here's a cheetah, here's another cheetah, here's a cheetah, here's a cheetah, and here's a cheetah. And we want the neural network to recognize all of these cheetahs as cheetahs. And how can it do that if they're all looking in different directions? They're all in different parts of the image. They're like, their faces are positioned in different parts of the image. Somebody's on the right hand side, somebody's in the left corner, somebody's in the middle. They're all a bit different. The texture is a little bit different. The lighting is a bit different. There's lots of little differences. And so if the neural network looks for exactly a certain feature, for instance, a distinctive feature of the cheetah is the tears that are on its face going from the eyes, or the shadows that look like tears, the texture, the pattern that is going from its eyes down its on the sides of its nose that looks like tears, that's a distinctive feature of the cheetah. But if it's looking for that feature which it learned from certain cheetahs in an exact location or an exact shape or form or texture, it will never find these other cheetahs. So we have to make sure that our neural network has a property called spatial invariance, meaning that it doesn't care where the features are located. Not so much as in which part of the image, because we've kind of taken that into consideration with our map, with our convolution layer, but it doesn't have to care if the features are a bit tilted, if the features are a bit different in texture, if the features are a bit closer or if features are a bit further apart relative to each other. So if the feature itself is a bit distorted, our neural network has to have some level of flexibility to be able to still find that feature. And that is what pooling is all about. So let's have a look at how pooling works. Here's our feature map. So we've already done our convolution, and we've completed that part, and now we're working with the convolution layer. Now we're going to apply pooling. So how does it work? We're going to be applying max pooling. There's several different types of pooling you can apply. There's mean pooling, max pooling, sum pooling, and we'll comment on those towards the end of this tutorial. But for now, we're just applying max pooling. So we take a box of 2 by 2 pixels like that. And again, it doesn't have to be 2 by 2. You can choose any size of box. And again, we'll comment on that towards the end of the tutorial. And you place it in the top left-hand corner. And you find the maximum value in that box. And then you record only that value. And you disregard the other 3. So in your box, you have 4 values. You just disregard 3. You only keep 1, the maximum, which is 1 in this case. Then you move your box to the right by a stride. You select the stride once again. So here we've selected a stride of 2. And that's what you normally select. You can select a stride of 1, you can select, so there are overlapping boxes, you can select any kind of stride that you like, even 3 if you want, but we're selecting a stride of 2 here, and that's what is commonly used. And then you repeat the process, you record the maximum. Here, if you cross over, it doesn't matter, you just continue doing what you're doing, so you still record the maximum here, 0. Here the maximum is 4, here the maximum is 2, here the maximum is 1, 0, 1, 0, 2, and then 1. So as you can see, a few things happened. First of all, we still were able to preserve the features, right? The maximum numbers, they represent, because we know how the convolution layer works, we know that the maximum or the large numbers in your feature map, they represent where you actually found the closest similarity to a feature. But by then pooling these features, we are, first of all, getting rid of 75% of the information that is not the feature, which is not the important things that we're looking out for. because we're disregarding 3 pixels out of 4. So we're only keeping 25%. And then also, because we are taking the maximum of the pixels that we, or the values that we have, we are therefore accounting for any distortion. So for instance, 2 images in which, for the example, the cheetah's tears on the eyes are, in one image they're a bit to the left or a bit rotated to the left, and in the other one they're a bit, and they're how they're supposed to be, or how we like if we take one as the basis and then the other one they're a bit rotated to the left, the pooled feature will be exactly the same. So you can see here, if we are talking about the cheetah's tears, then let's say this is the 4 and this is where it was here. Then if it was a bit rotated, so for instance the 4 ended up over here, then when we're doing the pooling, we're still going to get the same pooled feature map. And that's kind of the principle behind it. It's a very rough explanation, again, intuitive explanation, but that's the point of pooling, that we're still being able to preserve the features and moreover account for their possible spatial or textural or other kind of distortions. And in addition to all of that, we're reducing the size. So there's another benefit. So we're preserving the features, we're introducing spatial invariance, we're reducing the size by 75%, which is huge, which is really going to help us in terms of processing. And moreover, another benefit of pooling is we're reducing the number of parameters. So we're reducing, again, by 75%, we're reducing the number of parameters that are going to go into our final layers of the neural network. And therefore, we're preventing overfitting. It is a very important benefit of pooling that we're removing information, and that is a good thing. That is a good thing because that way, our model won't be able to overfit onto that information, especially because that information is not relevant. Remember, like at the very start, we were talking about, even for us as humans, it's important to see exactly the features rather than all this other noise that is coming into our eyes. Well, same thing for neural networks. By disregarding the unnecessary, non-important information, we're helping with preventing of overfitting. So there we go. That is what pooling is about. And the question here is, of course, why max pooling, right? There's lots of different types of pooling, and why a stride of 2, why a size of 2 by 2 pixels, lots of all these things. And on that note, I'd like to introduce you to this lovely research paper called Evaluation of Pooling Operations in Convolutional Architectures for Object Recognition by Dominik Scherer from University of Bonn. There's the link. And the beauty about this paper is that it's very, very simple, very straightforward. So if you've never read a research paper before, but you'd like to give it a go, this is a great place to start. It's very short, only 10 pages, very easy to read. And plus, the extra benefit is that now that we've discussed convolution and pooling, you will be totally comfortable with everything that they're talking about in this paper. And this is a great way to actually reinforce your knowledge. So I highly recommend checking this paper out. It'll take 20 minutes to read it. And you can even skip part 2, which is called related work. If it feels a bit far-fetched or alienating, just don't read that part. Just go straight from part 1 to part 3. And one thing that you do need to know about this paper, they talk about a concept called subsampling. Well, subsampling is basically average pooling. So remember how here we were taking the maximum. So in our square, we were taking the maximum value. There's a concept called mean pooling or sum pooling. Sum pooling is you just sum these values up. Average pooling or mean pooling, you take the average value out of all of these. And subsampling is kind of like a generalization of mean pooling. It's a more kind of generalized approach to taking the average of these values. And you can read a bit more about it in the paper, but otherwise just think of it as average pooling when you're reading that paper. And so that's where you can get some additional information on this topic. And now kind of let's recap. Where have we gotten to? So there's our input image. Then we applied the convolution operation and we got the convolution layer. And now to each of those feature maps that we get, we've applied the pooling layer. So we've done these 2 steps, convolution and pooling. And now we're going to do something very fun, something exciting. We're going to experiment with this. So this is a screenshot I took from a tool created by Adam Harley from back when he was at Ryerson University of Computer Science, and now he's at Carnegie Mellon, I think, doing his PhD. And a great tool. So let's open up, let's have a look. So you can find it. You can't actually find it through Google. You have to know the URL. It's just hard to find it through Google because there's no text here. Just this URL, scs.ryerson.ca, and then this stuff on the end. And basically, this is exactly what we're doing, but visualized. So here, you need to draw a number. So let's say I draw a number 4. And this tool will put the number 4 here. That's your image in our first step. Then this is the convolution step, right? And this is the pooling step. And also pooling, by the way, is also called downsampling. So pooling and downsampling are the same things. So you can see it's applied convolution, then it's applied pooling, and you can see how it exactly works. So you can see what kind of convolutions it has applied, or what kind of filters it applied, what they look like. You can see what features it's looking out for. And then it's applying pooling, so it's reducing the size. And you can see here that this is important, right? So you can see that this is the convolved image, and this is the pooled image, and you can still see the same features. It's just less information, but same features, right? The features are preserved. That's the important part. And moreover, if our 4 was a bit to the kind of like rotated a bit to the side, it would still be able to pick up very similar pooled layers. And then after that, it's got more layers. We haven't talked about that yet. So then it's got another convolution layer here, which we actually won't have. And then it has another pooled layer, but it's basically just repeating that same process. And then after that, this is what we're going to be talking further down in the course. It's got the fully connected layers and so on. But you can definitely play around with that. So if I delete that, if I draw a 7, you'll see that it actually tells you the guesses. It guesses that this is a 7, and the second guess, the second likelihood is a 3. So you can draw it some challenging things and see if it can pick them up. So let's say if I draw something that looks like a 0, but it's not a finished 0, will it pick it up? No, this time didn't pick it up. It looks like a 9 to the image. What if I kind of like finish it like that? See, now it thinks it's a 0 or a 9. And you can see over there what's lighting up, the 0 or the 9. But we'll talk about that part further down. Let's do one more. Let's say like 8. I think 8s are pretty hard for this. No, picked up an 8. So you can see that goes into an 8. And then after that, it stops being recognizable. It stops making sense to us humans, right? These features that it's working with. But at the same time, it is correctly recognizing that it's an 8. Yeah, so definitely play around with that. You can draw a smiley face, see what happens then. Looks like a 3 to this tool, because the tool is obviously trained up only on digits from 0 to 9. So it has to recognize something there out of those, and it recognizes a 3. It's like in life when you see something like a type of fruit that you've never seen before, like a custard apple or something, and you think that it's a pear, because you've never actually seen one before. You don't know what to classify it as. Same thing here. So it hasn't actually trained on smiley faces, and that's why it thinks it's a tree. It's a 3. So there you go. It's a very powerful tool. It will be helpful for you to play around with it. Actually, when you put your mouse over a pixel, it shows you where the feature detector was to pick up that pixel. So you can see where this pixel is coming from, and also, so you can see how the filter was kind of like going through the image, exactly how we talked about in the course. And here you can see the pooling. You can see that the pooling is done with a little square size of 2 by 2, and you can see that it's a stride of 2 as well, just as we discussed in today's tutorial. So there you go. Have a play around with that, and I hope you enjoyed today's session. I look forward to seeing you next time, and until then, enjoy deep learning. Hello and welcome back to the course on deep learning. I hope you're tracking along with these intuition tutorials just fine, and that you had a chance to play around with everything we've learned so far. And today we're talking about flattening, and the good news is that this is a very simple step, and this tutorial is going to be very quick, and then we'll be able to move on to the next interesting things. All right, so far we've got the pooled layer, pooled feature map, and that is after we apply the convolution operation to our image, and then we apply pooling to the result of the convolution or to the convolved image. And so what are we going to do with this pooled feature map? Well, we're going to take it and we're going to flatten it into a column. So basically just take the numbers row by row and put them into this one long column. And the reason for that is because we want to later input this into an artificial neural network for further processing. So this is what it looks like when you have many pooling layers, or you have the pooling layers with many pooled feature maps, and then you flatten them, so you put them into this one long column sequentially, one after the other, and you get one huge vector of inputs for an artificial neural network. And so to sum all of this up, we've got an input image, we apply a convolution layer, and let's not forget the ReLU, or rectified linear units function that we apply after the convolution layer as well. And then we apply pooling, and then we flatten everything into a long vector, which will be our input layer for an artificial neural network. And exactly how that works, we'll find out in the next tutorial. Hope you enjoyed today's session, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're finally at step number 4, full connection. So what is this step all about? Well, in this step, we're adding a whole artificial neural network to our convolutional neural network. So to all of the things that we've done so far, which are convolution, pooling, and flattening, now we're adding a whole new ANN on the back of that. How intense is that? That is something. That is definitely something. And so here we've got the input layer, we've got a fully connected layer and output layer. And by the way, the fully connected layer, in the artificial neural networks, we used to call them hidden layers. And here we're calling them fully connected layers because they are hidden layers, but at the same time, they're a more specific type of hidden layers. They're a fully connected layer. In artificial neural networks, hidden layers don't have to be fully connected, whereas in convolutional neural networks, we're going to be using fully connected layers, and that's why they're generally called fully connected layers. And so basically that whole column or vector of outputs that we have after the flattening, we're passing it into the input layer. And here we've got a very simplified example just for illustration purposes. And what the main purpose of the artificial neural network is to combine our features into more attributes that predict the classes even better. So we already, in our vector of outputs in the flattened result from what we've already done, we have some features encoded in the numbers in that vector. And they can already do probably a pretty good job at predicting what class we're looking at, whether it's a dog or a cat, or whether it's a tumor or not a tumor, and so on. But at the same time, we know that we have this structure called the artificial neural network, which is designed, which has a purpose of dealing with attributes and coming up, or dealing with features and coming up with new attributes and combining attributes together to even better predict things that we're trying to predict. And we know that from the previous part, so why not leverage that? And that's exactly what the plan here is. So how about we pass on those values into an artificial neural network and let it even further optimize everything that we're doing. And so that's what we're going to be doing, but let's look at a more realistic example, because this one is a bit too simple. So here we've got a better looking artificial neural network where we have 5 attributes on the inputs. Then we have, in the first hidden layer, we have 6 neurons. In the second, fully connected layer, we have 8 neurons, and then we have 2 outputs, one for dog and one for cat. And so an important thing to for us to talk about here is that why do we have 2 outputs? We are kind of used to having only one output in our artificial neural networks. Well, one output is for kind of when you're predicting a numerical value, when you're running a regression type of problem. But when you're doing classification, you need an output per class, except for the exception is when you have just 2 classes. Like we have 2 classes here, dog and cat, and we could have just done one output and made it a binary output and said 1 is a dog and 0 is a cat. And that would have worked totally fine. And actually, in fact, you'll see Hadoop do that in the practical tutorials, and that's how they'll be structured. But at the same time, if you have more than two categories, for instance, dogs, cats, and birds, then you have to have a neuron per every category. And that's why we're going to practice with two categories in this example so that we know what to expect if we ever have more than two categories. And so what's going to be happening here? So we've already done all the groundwork. We've done the convolution, we've done the pooling and the flattening, and now the information is going to go through the artificial neural network. So let's have a look at how all that all happens. There's the information going through from the very start, from the moment when the image is processed, then convolved, then pooled, flattened, and then through the artificial neural network, all 4 steps. And then a prediction is made. And we'll see how this happens in a moment. It'll be very, very interesting. But for now, let's just say a prediction is made, and for instance, 80% that it's a dog. But it turns out to be a cat. And then an error is calculated, what we used to call a cost function in a artificial neural network, and we use the mean squared error there, or in convolutional neural networks, it's called a loss function, and we use a cross entropy function for that. And we'll talk about cross entropy and mean squared errors in a separate tutorial and how all that happens. But for now, let's just say we have a loss type of function which tells us how well our network is performing, and we're trying to optimize it or minimize that function to optimize our network. So the error is calculated, and then it's back propagated through the network, just like we had in the artificial neural networks. It's back propagated, and some things are adjusted in the network to help optimize the performance. And the things that are adjusted are, as usual, the weights in the artificial neural network part, so the blue lines that you see here, the synapses. Then also another thing that is adjusted is the feature detectors. So we know that we're looking for features, but what if we're looking for the wrong features? What if this didn't work out because the features are incorrect? And so the feature detectors, remember those little matrices that we had, the 3x3 matrices, they are adjusted so that maybe next time it'll be better, and let's see what happens, type of thing. But of course, it's all done with a lot of science in the background, with a lot of math, and it's all done through a gradient descent with back propagation. So it's all not just random perturbations. It's actually very thought through how it's done. But nevertheless, the feature detectors are adjusted, the weights are adjusted, and this whole process happens again. And then again, the error is back propagated. And this keeps going on and on and on. And that's how our network is optimized. That's how our network trains on the data. So the important thing here is that the data goes through the whole network from the very start to the very end. Then the error is compared. So the error is calculated and then is back propagated. So same story as with artificial neural networks, just a bit longer because of that for the first 3 steps that we already had. And now let's have a look at the interesting part, the really interesting part. How do these 2 classes work? Or how do these 2 output neurons work? Because before we've always kind of had 1 output neuron. What happens when we have 2? How does this situation of classification of images play out? Well, let's start with the top neuron first. We're going to start with the dog. The main purpose, what we need to do first is we need to understand what weights to assign to all of these synapses that connect to the dog, so that we know which of the previous neurons are actually important for the dog. And let's see how that is done. So let's say, hypothetically, we've got these numbers in our previous layer, previous fully connected, or in the final fully connected layer. And again, these numbers can be absolutely anything. They don't have to be that. They can be any numbers. But just for argument's sake, we're going to agree that we are looking specifically at numbers between 0 and 1. So it's easier for us to argue these things and understand. And 1 means that neuron was very confident that it found a certain feature. And 0 is going to mean that that neuron didn't find a feature it's looking for. So because at the end of the day, these neurons, like anything else on this left side, is just looking at features at an image. This is already very, very processed, but still, it's detecting a certain feature or combination of features on the image, right? Before in the convolve step, we had kind of recognizable features. In the pool step, they're less recognizable. Then they become even less recognizable in the flattened image, and then they get combined and so on. But nevertheless, this we're talking about here certain features that are present in the image or their combination. So a 1, which is being passed, and this is important, is being passed to both the dog and the cat at the same time, to both the output neurons. So a 1 means that for us, for our argument, it means that this neuron is firing up. It's really rapidly detecting that feature that might be an eyebrow. It might be detecting this eyebrow for simplicity's sake, is detecting this eyebrow, and it's communicating that to the dog neuron, to the cat neuron, saying, I can see my eyebrow, I can see my eyebrow. And then it's up to the dog and the cat neuron to understand what that means for them, right? And so in this case, which neurons are firing up? These 3 neurons are firing up. The eyebrow, and let's say the nose, is saying, I can see a big nose, and I can see floppy ears. So it's saying that to the dog and to the cat. And then what happens is we know that this is a dog. So the dog neuron knows that the answer is it is actually a dog. Because at the end we're comparing to the picture or to the label on the picture, and it knows a dog. So basically the dog neuron is going to say, aha, so I should be triggered in this case. So these are my neurons. They're telling this signal that they're sending to me, to the dog, and to the cat is actually a indication for me that it is a dog. And throughout these lots and lots and lots of iterations, if this happens many times, the dog will learn that these neurons do indeed fire up when the feature belongs to a dog. On the other hand, the cat neuron will know that it's not a cat, and it will know that this feature is firing up, and this neuron is telling me it can see floppy ears, floppy ears, floppy ears, but at the same time, it's not a cat. So basically, to me, that's a signal that I should ignore this neuron. And the more that happens, the more the cat neuron is going to ignore this neuron about the floppy ears. And so basically, that's how, through lots and lots of iterations, if this happens often, so this is just one example, but if this happens often, maybe a 1, maybe a 0.8, 0.9, maybe sometimes it won't fire, but overall, on average, this neuron is lighting up very often. When it is indeed a dog, the dog neuron will start attributing higher importance to this neuron. And so there we go. That's how we're going to signify it. We're going to say that these 3 neurons, through this iterative process with many samples and many epochs. Remember, so a sample is a row in your data set, and epoch is when you go through your whole data set again and again and again. Through lots and lots of iterations, this dog neuron learned that this eyebrow neuron and this big nose neuron and this floppy ear neuron, they all seem to really contribute very well to the classification of what it's looking for, and which is a dog. So that's how it works. And again, these ears and nose and eyebrows, those are very, very approximate or like very far-fetched examples, because by this stage in this whole convolutional neural network, it is completely unrecognizable what they're looking for. But at the same time, it is something in the features of dogs or cats or whatever you're classifying. And then, so let's move on to the next one. Now we're going to look at the cat neuron. But these, we're going to remember that these weights are, we've sorted out the dog. So the dog is kind of like pretty much ignoring all these other neurons, 1, 2, 3, 4, 5, but it's really paying attention to what these 3 neurons are saying. Now, what is the cat listening to? Well, whenever it is actually a cat, right? This is an example of a situation when it's actually a cat. So you'll see that these 3 neurons, 0.9, 0.9, and 1, they're saying something to both the dog and the cat. And this is, again, important to remember. So this output signal goes both ways. It's the same, right? It's saying 1 to the dog, it's saying 1 to the cat. But then it's up to the dog and to the cat to decide whether to take into account that signal and learn from it or not. And both the dog and the cat can see that this is a photo. I should have put a photo of a cat here, but basically imagine a photo of a cat. Both the dog and the cat can see that this is actually a cat. So basically the dog is like, oh, okay, so these whiskers and these pointy triangle ears and this small size, I guess, or I don't know, oh, maybe this type, you know how cats have these things in their eyes are like little, they're not circles, they're lines or something like that, like cat eyes. Basically, these cat eyes, they're definitely not working for me. They're not helping me out predict, because every time these neurons light up, the prediction is not what I'm looking for. On the other hand, the cat is like, that's interesting. Every time this one lights up, or most of the time it lights up, it matches my expectation. It matches what I'm looking for. Okay, I'm going to listen to this guy more. Then this one, same thing. Every time it lights up, or most of the times it lights up, I happen to be rewarded for my prediction because I get it right. It's a cat. Okay, so I'm going to listen to him more. This one, useless to me because he's not actually, he's not even lighting up. It's a cat, but he's not lighting up. So the opposite is happening. And this one as well, it's a cat, but he's not lighting up. So I'm not going to listen to him. But this one, what was this? The cat eyes light up. I can see that it's a cat. It matches most of the time. So I'm going to learn from that. And I'm going to listen to these three guys more often than not. And so basically the cat is listening to these three and it's ignoring the other five. And that is how these final neurons learn which neurons in the final fully connected layer to listen to. So the output neurons learn which of the final fully connected layer neurons to listen to. And that's how they understand. Basically, that's how the features are propagated through the network and conveyed to the output. And so even though these features, of course, don't have that much meaning to them, like floppy ears or whiskers, at the same time, they do have some they are a distinctive feature of that specific class. And that's how the network is trained, because we also, during the backpropagation process, we also adjust the feature detectors. So if a feature is useless to the output, it's going to probably be disregarded, because this doesn't happen over one or two iterations. This happens through thousands and thousands of iterations. So with time, a feature that is useless to the network is going to be disregarded and replaced with a feature that is useful. And so at the end of the day, in this final layer of neurons, you're likely to have lots of features or combinations of features from the image that are indeed representative or descriptive of dogs and cats. And so then once your network is trained up, this is how it's applied. So this is the next step. Like, we've already trained up our network. Well, let's see what happens when this network is applied. So let's say we pass on an image of a dog. The values are propagated through a network. We get certain values. And so this time, the dog and the cat neurons don't know. They don't have the image of the dog here. They don't know that it's a dog or a cat. They have no idea what it is. But they have learned to listen to what is being shown here, right? They have learned to listen to, the dog neuron listens to these three neurons, the cat neuron listens to these three. And so the dog neuron looks at 1, 2, 3 and says, aha, these are pretty high, so my probability is going to be high that it's a dog. The cat neuron looks at these three and says, okay, this one is pretty high, but these are pretty low. Interesting, so my probability is going to be 0.05. And that's where you get your prediction. So then your first choice for this neural network is dog, second choice is cat, and that's pretty much it. So the answer is dog. And same thing happens when you pass an image of a cat. You get new values, and you can see that even though this one's high, these ones are low, and for the cat, this one's high, and this one's a bit low. So the probability here might not be as great as previously, but still you can see that it's a cat with 79%. And so therefore, the neural network is going to vote that it's a cat. And so basically, the neural network is going to conclude that it's a cat. Voting is a term that is used for these guys. So these neurons in the final fully connected layer, they get to vote. And these are their votes. And again, we are just, for argument's sake, putting values between 0 and 1 here. These could be any values, but they get to vote. And then these weights are the importance of their vote. So this is these purple weights are how the dog neuron views their votes, how much importance it assigns to these neurons and to those votes, and this is how much importance the cat neuron assigns to these to the votes of these neurons. And so these neurons vote. The dog and the cat, based on their learned weights, they decide who to listen to, and then they make their predictions, and the whole neural network concludes that this is, in this case, a cat. And then that's your conclusion. And that's how you get images like this, where you have a cheetah, and then you have a cheetah class with like a high probability. So this is the probability that the network has predicted, and these are lows. But these still exist because there's still kind of like a small chance the other neurons are also listening to their voters, and they're saying, oh, maybe it's actually a leopard. And the bullet train, very, very probable. Here, scissors, this one won, but hand glass was very close second, and then frying pan stethoscope, because you could see like these guys, this neuron, the scissors neuron, the output scissors neuron, listened to its voters, and it had the predominant vote overall, but then the hand glass had a good outcome as well. So there we go. That's how the full connection works and how this all plays out together. I hope you enjoyed today's tutorial. We're going to summarize all of this in the summary as well, and I'll see you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. So we've learned quite a lot in this section of the course. Let's summarize what we've talked about. All right, so here we go. We started with an input image, to which we applied multiple different feature detectors, or also called filters, to create these feature maps. And this comprises our convolutional layer. Then on top of that convolutional layer, we applied the ReLU, or rectified linear unit, to remove any linearity or increase nonlinearity in our images. Then we applied a pooling layer to our convolutional layer. So from every single feature map, we created a pooled feature map. And basically, the pooling layer has lots of advantages. The main purpose of the pooling layer is to make sure that we have spatial invariance in our images. So basically, if something tilts or twists or is a bit different to the ideal scenario, then we can still pick up that feature. Plus, pooling significantly reduces the size of our images, and also pooling helps with avoiding any kind of overfitting of our data or of our model to the data, because it just simply gets rid of a lot of that data. But at the same time, pooling preserves the main features that we're after, just because the way it's structured, and the pooling we used was max pooling. Then we flattened all of the pooled images into one long vector or column of all of these values, and we input that into an artificial neural network, and that was step 3, flattening, and step 4 is the fully connected artificial neural network, where all of these features are processed through the network, and then we have this final layer, final fully connected layer, which performs the voting towards the classes that we're after. And then all of this is trained through a forward propagation and back propagation process, and lots of iterations and epochs. And in the end, we have a very well defined neural network. And another important thing is not only the weights are trained in the artificial neural network part, but also the feature detectors are trained and adjusted in that same gradient descent process. And that allows us to come up with the best feature maps. And in the end, we get a fully trained convolutional neural network, which can recognize images and classify them. So there we go. That's how convolutional neural networks work. And now you should be totally comfortable with this concept and ready to proceed to the practical applications. If you'd like to do some additional reading, then there's a great blog by Edith Deshpande from 2016. You can see the link over there at the bottom. So the blog is called The 9 Deep Learning Papers You Need to Know About Understanding CNNs Part 3. And this blog actually gives you a short overview of 9 different CNNs that have been created by people like Jan LeCun and others, which you can then go ahead and study further. So there will be a lot of new things that will be totally new to you and that you will have to get your head around. But just keep this blog in mind, or these 9 papers in mind. And even if you're not ready to go through them right now, maybe after the practical tutorials, maybe after you do some additional training in the space of deep learning, slowly you can then reference these works. And ideally, I think you will get a lot of value through looking through other people's neural networks and how they structured their convolutional nets. And that will help you understand what are the best practices and why people did certain things in a certain way. And that will help you with your architecture of neural networks, because neural networks and convolutional neural networks are not an exception. They are like an architecture challenge. You have to come up with a idea and then structure it and then adjust it and tweak it to get the best possible design and the best possible and optimal performance. So there we go. That's us for today. I hope you enjoyed today's tutorial and this whole section, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. This is an additional tutorial to talk about the softmax and cross entropy functions. It is not 100% necessary in order for you to go through all of the parts that we've been through in the main part of this section where we're talking about the convolutional neural networks. But at the same time, I thought it would be a good addition to your bag of knowledge and skill set. So let's go ahead and dig into these functions. So to start off with, what we have here is the convolutional neural network that we built in the main part of the section, and then at the end it pops out some probabilities for 0.95 for a dog and 0.05 or 5% for a cat, given that photo in the left as an input. This is after the training has been conducted. This is actually it's running and it's classifying a certain image. And so the question here is, how come these two values add up to 1? Because as far as we know from everything that we've learned about artificial neural networks, there is nothing to say that these two final neurons are connected between each other. So how would they know what the value of how would each one of them know what the value of the other one is, and how would they know to add their values up to 1? Well, the answer is they wouldn't in the classic version of an artificial neural network. And the only way that they do is because we introduce a special function called the softmax function in order to help us out with the situation. So normally what would happen is the dog and the cat neurons would have any kind of real values. They don't have to they don't have to add up to 1. But then we would apply the softmax function, which is written up over there at the top, and that would bring these values to be between 0 and 1, and it would make them add up to 1. And to quote Wikipedia, the softmax function, or the normalized exponential function, is a generalization of the logistic function that quote unquote squashes a k-dimensional vector of arbitrary real values to a k-dimensional vector of real values in the range of 0 to 1 that add up to 1. So basically, it does exactly what we want. It brings these values to be between 0 and 1 and makes sure that they add up to 1. And the way it works is that this is possible is that because at the bottom over here you can see that there's a summation. So it takes the exponent and puts it in the power of z and adds it up. So z1, z2 across all of your classes, all of these values. And so that's your normalization happening right there. So that's how the softmax function works, and it makes sense to introduce the softmax function into convolutional neural networks, because how strange would it be if you had a possible classes of a dog and a cat, and for the dog class you had probability of 80%, and for the cat class you had a probability of 45%, right? It just doesn't make sense like that. And therefore, it's much better when you introduce the softmax function, and that's what you will find happening most of the time in convolutional neural networks. Now, the other thing is that the softmax function comes hand in hand with something called the cross-entropy function, and it's a very handy thing for us. So let's first look at the formula. This is what the cross-entropy function looks like. We're actually going to be using a different calculation. We're going to be using this representation of the cross entropy, but the result is basically the same. This is just easier to calculate. And what I know this might sound very unrelated to anything right now, just formulas on your screen, but there will be some additional recommended reading at the end of this section. So don't worry if you're not picking up on the math, like if we haven't explained the math right now. But the point here is that what is the cross entropy? Well, a cross entropy function, remember how we previously in artificial neural networks, we had a function called the mean squared error function, which we used as the cost function for assessing our network performance. And our goal was to minimize the MSE in order to optimize our network performance. Well, that was our cost function then, and in convolutional neural networks, we can still use MSE, but a better option in convolutional neural networks, after you apply the softmax function, turns out to be the cross-entropy function. And in convolutional neural networks, when you apply the cross-entropy function, it's not called the cost function anymore, it's called the loss function. And they're very similar. They're just little terminological differences and a bit different in what they mean. But for our purposes, it's pretty much the same thing. And what happens is the loss function is, again, something that we want to minimize in order to maximize the performance of our network. So let's have a look at a quick example on how this function can be applied. So let's say we've put an image of a dog into our network. The predicted value for dog is 0.9, and this is during the training, so we know the label that it is a dog. So the predicted value is 0.9, the predicted value for cat is 0.1. Then here we have the label, so we know it's a dog because this is training, and 1 for dog, 0 for cat. And so in this case, you need to plug these numbers into your formula for the cross entropy. So how you would do it is the values on the left go into the variable q, the one that is under the logarithm on the right side, and the values from the right would go into p. And so it's important to remember which one goes where, because if you get them wrong, you don't want to be taking a logarithm from a 0 value or a logarithm from a 1. So you just want to plug them in, make sure you plug them into the correct places, and then you basically add that up. So that's how the cross entropy works. And we'll look at actually right now we're just going to look at a specific step-by-step example of applying this function in real life. And it'll kind of make more sense what cross entropy is. And it'll be less, my goal in this tutorial is to make you more comfortable with cross entropy, because it can sound very convoluted and no pun intended. It can, like convolutional neural networks, it can sound very complex, right? Scary, but it's not. That's the point. So let's go ahead and apply it just so we know that it's not scary. So here's neural net, and also this will explain why we're doing this, why we're looking at different cost functions. So neural network 1, neural network 2. Let's say we have 2 neural networks, and then we pass an image of a dog. And we know that this is a dog and not a cat. And then we have another image of a cat, this time an animal, and it's a cat, not a dog. And here we have a weird looking animal, which is in fact a dog, not a cat, if you look very closely. So we want to see what our neural networks will predict. In the first case, neural network 1, 90% dog, 10% cat, correct. Neural network number 2, 60% dog, 40% cat, still correct. Worse, but correct. Second option, first neural network, 10% dog, 90% cat, correct. Neural network number 2, 30% dog, 70% cat, worse, but still correct. And then finally, neural network 1 in image 3, neural network 1, 40% dog, 60% cat, incorrect. Neural network number 2, 10% dog, 90% cat, incorrect, and worse. So the key here is that even though both networks got it wrong in the last one, throughout all 3 images, neural network 1 was outperforming neural network 2. So even in the last case, it was very it gave dog like a 40% chance, as opposed to neural network 2 only gave dog a 10% chance. So neural network 1 is outperforming across the board when compared to neural network 2. And so now we're going to look at the functions that they can measure performance that we've kind of talked about already. So let's put these into a table. So there's neural network 1. You have the row number, so that's the image number. And then for image 1, you have what it predicted, 90% dog, 10% cat. So those are the hat variables. And then you have the actual values. So dog correct, cat incorrect. Same thing for image number 2, and same thing for image number 3. And same for neural network number 2. So dog 60%, cat 40% in the first image. That's what it predicted. The correct answer was dog, not a cat, and so on. And so now let's see what errors we can actually get. So what errors we can calculate to estimate the performance and monitor the performance of our networks. So one type of error is called the classification error. And that is basically just asking, did you get it right or not? Regardless of the probabilities, it's just, did you get it right or did you not get it right? So in both cases, for both neural networks, each of them, they got one, or so this is how many they got wrong. So they got 1 out of 3 wrong. So 33% error rate for neural network 1 and 33% error rate for neural network 2. And so basically from this standpoint, both neural networks perform at the same level. But we know that's not true. We know that neural network 1 is outperforming neural network 2. That's why classification error is not a good measure, especially for the purposes of backpropagation. Mean squared error, different. And by the way, I did these calculations in Excel. I just didn't want to bore you with them, but you can totally just sit down and do them on a paper or in Excel. These are very straightforward calculations. Just basically take the sum of squared errors and then just take the average across your observations, and that's pretty much it. So for neural network 1, you get 25%. For neural network 2, you get 71% error rate. So as you can see, this one is more accurate. It's telling us that neural network 1 has a much lower error rate than neural network 2. And then cross entropy, again, we've seen the formula. You can also calculate this. This is actually even easier to calculate than the mean squared error. Cross entropy gives you 38% for neural network 1 and 1.06 for neural network 2. So you can see the results are a bit different when you look at them like that, when you look at the mean squared error and cross entropy. The question of why would you use cross entropy over mean squared error isn't just about the kind of like the numbers that they spit out. These calculations were just to show you that this is all, it's all doable. You can just do it on a paper. It's not, these are not very intense mathematics. These are pretty simple, straightforward things. But the question of why would you use cross entropy over mean squared error, it's a very, very good question to ask. I'm glad you asked it. The answer to that is, like, there's several advantages of cross entropy over mean squared error, which are not obvious. And so I'll mention a couple, but then I'll let you know where you can find out more. So one of them is that if for instance, you're at the very start of your backpropagation, your output value is very, 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 very tiny, very tiny. So it's much smaller than the actual value that you want. Then at the very start, the gradient in your gradient descent will be very, very low, and it won't be enough. It'll be very hard for the neural network to actually start doing something and start moving around and start adjusting those weights and start actually moving in the right direction. Whereas when you use something like the cross entropy, because it's got that logarithm in it, it actually helps the network assess even a small error like that and just do something about it. Here's how to think about it. So let's say, again, this is very intuitive approach. There's going to be a link to the mathematics, and you can derive these things through the mathematics in more detail, but a very intuitive approach. Let's say your outcome that you want is 1, and right now you are at 1 millionth of 1, right? 0.000001, and then you improve next time. You improve your outcome from 1 millionth to 1,000th, and in terms of if you calculate the squared error, you're just subtracting one from the other, or basically in each case, you're calculating the square error, and you'll see that the squared errors, when you compare one case versus the other, it didn't change that much. You didn't improve your network that much when you're looking at the mean squared error. But if you're looking at the cross entropy, because you're taking a logarithm, and then you're comparing the two, dividing one by the other, you will see that you have actually improved your network significantly. So that jump from 1 millionth to 1,000th in mean squared error terms will be very low. It will be insignificant, and it won't guide your gradient boosting process or your backpropagation in the right direction. It will guide it in the right direction, but it'll be like a very slow guidance. It won't have enough power. Whereas if you do it through cross entropy will understand that, oh, even though these are very small adjustments that are just making a tiny change, in absolute terms, in relative terms, it's a huge improvement. And we are definitely going in the right direction. Let's keep going that way. So cross entropy will help your neural network get to the optimal state. It's a better way for the neural network to get to an optimal state. But bear in mind that this only works when cross entropy is only the preferred method only for classification. So if you're talking about things like regression, like which we had in artificial neural networks, then you would rather go with mean squared error, whereas cross entropy is better for classification. And again, it has to do with the fact that we're using softmax functions. So that's a kind of intuitive explanation of that. A good place to learn a bit more about that, if you're really interested in, why are we using cross entropy versus mean squared error, Google a video by Jeffrey Hinton called the softmax output function. And he explains it very well. And, being the godfather of deep learning, who can explain it better anyway? And by the way, any video by Jeffrey Hinton is golden. He's just got a huge talent for explaining things. Anyway, so that's softmax versus cross entropy. I hope that gives you kind of like an intuitive understanding of what's going on here, but more importantly, that you're not put off by the term cross entropy, because Hadelin will mention it in the practical tutorials, and I wanted to make sure that you're prepared for that. And it's just another way of calculating your loss function and another way of optimizing your network, which is specifically tailored to classification problems and therefore convolutional neural networks, and comes in hand in hand with the softmax function. So, additional reading. If you'd like a light introduction into cross entropy, if you're interested in cross entropy a bit more, of course, a good article to check out is called A Friendly Introduction to Cross Entropy Loss by Rob DiPietro, 2016. Here's the link below. Very, very nice, very soft, no super complex math, good analogies, good examples. He uses analogies of cars, and you look at cars and talks about information and bits and restrictions, and how would you encode this, how would you encode that. It's a good article to have a look at, and will give you a good overview of cross entropy, like from an introductory standpoint. If you want to dig into the heavy math, like what you see here, then check out an article or a blog by How to Implement a Neural Network Intermezzo 2. So intermezzo is like an intermediary thing, like a intermittence in, like when you go to a theater and you have like a break between the first part and the second part. So that, because he's like going through all these steps, and then he says, oh, I got to explain this first. And yeah, so that's why it's called intermezzo. No other reason, as far as I understand. The article is by Peter Rowlands, 2016 as well. So both are quite recent. And check out this if you would like to dig into the mathematics behind cross entropy, behind the softmax and cross entropy in this article, actually. So there we go. That's all there is to these two. Hopefully I was able to add some additional clarity, and good luck with that. It's going to be fun, and enjoy the practical tutorials. I'll see you next time. Until then, enjoy deep learning.
Hi everyone, and welcome to this bonus lecture. We wanted to provide you some additional practical material to help really continue more hands-on experience in AI. And for this, we're going to be using Q-learning and the knowledge that you've acquired in this course to solve something similar to the postman problem. And that may sound familiar to some of you. Basically, it's a modified version where our main goal is to find the shortest path between locations. And this is a really popular concept within computer science, and we want to use AI and our Q-learning options to solve it. This can be expanded to solve a range of business problems and can really help demonstrate Q-learning concepts. So, with that being said, let's dive in and get started solving this challenge in the next lecture. But for those of you that may want to try and solve it on your own, and I highly recommend it, it's a great way to practice. You can build different solutions. There's always multiple options to solving it. In the next lecture, I will do my best to provide the environment setup and overview so that you can then write some of your own code and approach, and then compare it to the method that we use to solve it. Awesome. Let's get started, and I'll see you in the next lecture. Hi everyone and welcome back. In this lecture, we're going to get our environment set up, and I want to introduce this more high-level overview for those of you that want to try and solve it on your own. And this may look familiar. In the last lecture, you saw this, so if you read through it, my apologies, we're just going to go through it really quickly. First things first, in this project, we're really aiming to keep it as simple as possible in the sense we don't need to import too many libraries. We're basically just going to be using NumPy. For that, we just need to import NumPy as NP. Usually the common reference for NumPy. And we also want to set up our environment. As you'll see here, and we're just going to go through this again really quickly as an overview, the first step for our Q learning is we want to define an environment that the postman has to navigate. We need that environment set up so we can actually iterate and go through it. In this lecture, the environment is going to consist of states, actions, and rewards. States and actions are inputs for the Q learning AI agent, while the possible actions are the AI agent's outputs. Our states, we can think about and look at this image as our representation. The states in our environment are all the possible locations within the city. We can call this example city. Some of these locations are the city boundaries, which will be our black squares, while other locations are aisles that the postman can use to travel through the city. Those are going to be the white squares. The green square indicates the item, packaging, and shipping area. The black and green squares are what we're going to call terminal states. So overall, our goal, or our AI agent's goal, we want to use the shortest path. We want our agent to learn the shortest path between the item packaging area, which are green, and all the other locations in the city where the postman is allowed to travel. In the above image, we have 121 possible states or locations within the city. These states are arranged in a grid, 11 by 11. Each location can hence be identified by its row and column index. So what would be our first step? And this is really, I want you guys to start thinking about how you can define it. We need to define our environment. This is a good example of our image and how we're going to approach it. So how would you model that? Remember, we're using NumPy. So we need to define these boundaries, and we can define a 3D NumPy array to hold our current Q values for each state and action pair. As we see, our representation, and for those of you who are not familiar with it, or maybe this is new, or you want to just have a refresher, the AI A through Z handbook from this course is extremely helpful. Highly recommended. So what do we have to do here? We can actually, let me just expand this really quickly for us so we can view it a little easier. Let me just add some code cells. We're going to define our 3D NumPy array. How would you go about this? So we have some options, but the most really straightforward and simple option, let's call it environment rows, and let's set it to 11. It's an 11 by 11. And then we can also do environment underscore columns, and we can also set this to 11. Lastly, we can set our Q values since we need to add our NumPy with the environment rows, environment columns. And we can set this as Q values equal to NumPy.zeros. And we need to use our environment rows, environment columns, and we have our 3D NumPy array, our 3D environment representation set with our environment. Awesome. Now, and we're going to leave it off here, but I want you guys to start thinking about how to solve this since you already have your environment set up. The next thing that you're going to want to do as a hint is set up your actions. Your agent needs to be able to move through the environment. So how would you represent that? How would you write that in for this problem? Let's leave it off here. In the next video, we're going to revisit those actions. Awesome. I'll see you guys in the next video. Hi, everyone, and welcome back. In the last lecture, we ended up starting to build our environment. We have essentially an 11 by 11 grid here that we want our postman to iterate through to solve our challenge. We want to now start to think about, once we have the grid, we also need to have actions for our agent. And I'm going to delete these really quickly. We don't need these cells. I just wanted to have it in for some spacing. Just makes it easier to view. Give me 1 second. Let me delete these, and we can leave this one here. So I left the text in that we have, and we want to set our actions as in up, right, down, and left. With Python, it's pretty straightforward. We can build a list and set our actions. Our actions are going to be equal to as we have up, right, down, left. So let's set it up, right, down, and left. We need to give our agent, some ability to maneuver with these actions through the maze. In addition to that, we also have to start setting rewards. Now, this is where it's going to start becoming a little more tricky because we have to set different states of our environment. Different states in the sense of we want to be able to assign these -100 and -1, these steps or these state values to each square within the grid. So we see to help our AI agent learn each state or location in our city, we want to have a reward value. That's how our agent's going to learn. So the agent may begin at any white square, but its goal is always the same. We want to maximize its total rewards within Q-learning. Negative rewards, we know that they're referred to as punishments. These are used for all states except the goal. That's how we're going to establish that optimal policy, which encourages the AI to identify the shortest path to the goal by minimizing its punishments. All right. Also, to maximize the cumulative rewards, the AI agent will need to find the shortest path between the item packaging area, our green square, remember, and the other locations of the city where the postman can travel, the white squares. Agent's going to learn to avoid crashing into any of the city boundaries. Those are the black squares as we see with the -100. We want to stay away from them. They have more of a punishment. So in order to do this, we have our grid, the environment that we created above with our rows, but we also want to assign these values to it. So in order to do that, let's try to think about how we can establish that. We can use NumPy, and we can also start setting it to -100 for environment rows and environment columns. So we have our environment rows and environment columns. So let's call this rewards equal to numpy.full. And let's pass in our environment rows, environment columns. And to set our values, we can start with -100. In addition to that, we also want to set our rewards window to use the indexes of 0 and 5 equal to 100. And this is going to make sense in a second. So we're taking a look at our green square. We have our 0 and 5. We have our green square set as 100, taking these or this location to set the value. Now I'm going to paste in the next snippet of code so we can go through it, so you don't have to watch me write each step out because it's a little repetitive. And now we have our white spaces. Let's set our note for our reward points. And in this snippet of code, we're using a dictionary and setting each of our values within our dictionary. So we have our aisles. We're thinking about that as each individual row. And we can set with our slicing, with our index 1 through 9, and we want to use an iteration with our for loop to set these values. In doing so, you'll see if we look at 1 through 10, 1, 7, and 9, and by using this, we can actually set the row index in our range of 1 through 10, which we're working through in our environment. We can set the column index in our aisles of our row index with our dictionary. Our rewards row index and column index, we can set it to -1. So what this is doing is essentially, if we look at each specific, if we take a range here, for example, aisle 9 for I in our range, we have -1 set throughout the entire environment or each state within our environment. For 8, we have 3 and 7. So if we can scroll up, we can see that in 3 and 7, we're setting a -1 since they would all be -100 or set to a -100. And with this iteration, we can set those rewards or set each state that we're defining within our aisles to -1. It makes it very easy instead of having to write further logic or maybe more detailed functions or statements. We can iterate through and set these values. I highly recommend that you take a minute to explore, experiment if you want to change the environment later after we run this solution. It's a great way to help learn and reinforce these policies. But this is starting to take shape. And a cool thing we can do is we can actually visualize it. So let's do for row in rewards, print row. And let's print this, and we can see, I might have to actually rerun the cells, my apologies. I wasn't connected to the notebook working through here. Give it 1 second, it's gonna throw an error. I need to go back through and rerun the cells. So let me just run this really quickly. I want to import NumPy. I can actually just, my apologies. Let me go through this here. And I'm going to come down. We want to run our environment. We want to run our actions. The other ones are just text, so we don't need them, but I like to have that in so you guys can have a reference to it. We want our reward points, and we finally want to visualize this. We can see the visualization, the actual numerical representation in NumPy of our environment. Really cool. So we have our environment set up. Amazing work. Hope you guys are finding this useful. Now we're going to cap it off here because in the next lecture, we're going to start training the model. So this was to set our agent's actions, to set our environment, to set our rewards, our punishment. This is going to help the agent establish the optimal policy within Q-learning. Overall, we have this visual representation or this image built, and we can see it here if we print out our row. Amazing. All right. I won't keep rambling on. Let's cap it off here. In the next lecture, let's start training the model. I'll see you guys in the next lecture. Hi, everyone, and welcome back. In the last lecture, we ended up finishing or finalizing the actual definition of our environment, the representation of our values, our punishment and rewards, and our actions in the environment. In this lecture, what I want to do is to introduce the training, the idea behind how to train the model, and to help get you started. And then in the next lecture, provide the solution and more of a breakdown for the steps involved. So we need to train the model. What would be required of training? This is an approach that we can use for the following steps for training the model. We want to choose a random non-terminal state, which would be the white square of our agent, and that's how we want to begin in our episode for the training. We then, of course, want to choose an action for the current state. We need to have our agent being able to move around the environment. So actions for us and our agent in this challenge are going to be chosen using epsilon greedy. This algorithm will usually choose the most promising action for the AI agent, but occasionally choose a less promising option in order to encourage the agent to explore the environment. We really want to find that optimal policy. Then we want to perform the chosen action and transition to the next state, move to the next location. And why I'm saying this is I want you guys to think about how you can break this down into functions to solve this problem. Next, we need to receive a reward for going to a new state and then calculate the temporal difference. We have to update the Q value for the previous state and action pair. And if the new or current state is a terminal state, we would then go to 1. Otherwise, we'd go to step number 2. So the entire process, we're going to aim to run for 1,000 episodes to train. This is going to give us enough opportunity, or our AI agent sufficient opportunity, to calculate that shortest path between the item packaging area and other locations in our example city. Awesome. So please think about how you would approach this. And I want to help give you an idea to try and solve this. So we'd be looking at, in our solution, we're going to be using the following functions. I can actually comment this out since it's a code cell. My apologies. We don't want a $sign. We want to comment these out. And I'll help get you started on the first one. Overall, we're going to have these functions defining our steps for training the model. And to help get you started, let's take a look at how we would approach is terminal state in creating a function within Python for this. First things first, we would, of course, want to define our function as is terminal state. And these are the names of the functions that you will see to give you an idea that might help you break it down. What we want to do is take the current row index and the current column index. This is going to help give us the position of our agent. And we can add here for our rewards a true or false. So we need an if statement. So let's set our rewards of our current row index and current column index equal to -1 if they're in that state. We would return false. Otherwise, or else, we would return true. Pretty straightforward enough. And this is how we're going to get an idea of our is terminal state. After we have, if it's existing in the terminal state, we then want to get the starting location. As a hint, you can take a look at using the current row index and the current column index and setting NumPy with a random, we want to initialize that randomly, to the environment rows, environment columns. But in the next lecture, you'll see a breakdown. You'll see the rest of the functions with some notes to help give you an idea. I really hope that you guys take the chance to experiment with this because it is just an awesome way to learn and help give you an idea. And this is to get you started. So don't worry, you'll get the solution in the next lecture. And then we're going to wrap things up by actually assigning an epsilon, discount factor, learning rate, those type of things for training, running the training, and viewing the results. Awesome. Let's stop here. Again, try to solve this, but if not, if you want to just advance, go to the next lecture and you'll get the solution for the training for defining of these functions. All right, I'll see you guys in the next lecture. Hi, everyone, and welcome back. In the last lecture, we ended up finishing or finalizing the actual definition of our environment, the representation of our values, our punishment and rewards, and our actions in the environment. In this lecture, what I want to do is to introduce the training, the idea behind how to train the model, and to help get you started. And then in the next lecture, provide the solution and more of a breakdown for the steps involved. So we need to train the model. What would be required of training? This is an approach that we can use for the following steps for training the model. We want to choose a random non-terminal state, which would be the white square of our agent, and that's how we want to begin in our episode for the training. We then, of course, want to choose an action for the current state. We need to have our agent being able to move around the environment. So actions for us and our agent in this challenge are going to be chosen using epsilon greedy. This algorithm will usually choose the most promising action for the AI agent, but occasionally choose a less promising option in order to encourage the agent to explore the environment. We really want to find that optimal policy. Then we want to perform the chosen action and transition to the next state, move to the next location. And why I'm saying this is I want you guys to think about how you can break this down into functions to solve this problem. Next, we need to receive a reward for going to a new state and then calculate the temporal difference. We have to update the Q value for the previous state and action pair. And if the new or current state is a terminal state, we would then go to 1. Otherwise, we'd go to step number 2. So the entire process, we're going to aim to run for 1,000 episodes to train. This is going to give us enough opportunity, or our AI agent sufficient opportunity, to calculate that shortest path between the item packaging area and other locations in our example city. Awesome. So please think about how you would approach this. And I want to help give you an idea to try and solve this. So we'd be looking at, in our solution, we're going to be using the following functions. I can actually comment this out since it's a code cell. My apologies. We don't want a $sign. We want to comment these out. And I'll help get you started on the first one. Overall, we're going to have these functions defining our steps for training the model. And to help get you started, let's take a look at how we would approach is terminal state in creating a function within Python for this. First things first, we would, of course, want to define our function as is terminal state. And these are the names of the functions that you will see to give you an idea that might help you break it down. What we want to do is take the current row index and the current column index. This is going to help give us the position of our agent. And we can add here for our rewards a true or false. So we need an if statement. So let's set our rewards of our current row index and current column index equal to -1 if they're in that state. We would return false. Otherwise, or else, we would return true. Pretty straightforward enough. And this is how we're going to get an idea of our is terminal state. After we have, if it's existing in the terminal state, we then want to get the starting location. As a hint, you can take a look at using the current row index and the current column index and setting NumPy with a random, we want to initialize that randomly, to the environment rows, environment columns. But in the next lecture, you'll see a breakdown. You'll see the rest of the functions with some notes to help give you an idea. I really hope that you guys take the chance to experiment with this because it is just an awesome way to learn and help give you an idea. And this is to get you started. So don't worry, you'll get the solution in the next lecture. And then we're going to wrap things up by actually assigning an epsilon, discount factor, learning rate, those type of things for training, running the training, and viewing the results. Awesome. Let's stop here. Again, try to solve this, but if not, if you want to just advance, go to the next lecture and you'll get the solution for the training for defining of these functions. All right, I'll see you guys in the next lecture. Hi, everyone, and welcome back. In the last lecture, you saw how we used our helper functions to really set up the core of our functionality to train our model. So we had our terminal state, our starting location, our next action, next location, and shortest path. Really defines the majority of how our agent or how our environment is going to work. The last thing we have to do is use our training. In order to use our training, it's pretty straightforward in the sense of what we need to include, but how we go about it is a different story. That being said, also, if you guys use a different approach or you want to customize this and experiment with it, it's highly recommended. In addition to that, if you use a different approach and you want to discuss it, please feel free to share it in the Q&A. More than happy to discuss it with you. It's such a great idea because there's so many ways to solve this, and you might find a way that's way better, more advantageous. We could look at pros and cons. Again, more than happy to discuss it. All right, so what do we have to do? We have to launch our training. For our training, we want to use the epsilon. So basically the percentage that we're going to take for the best action for our, instead of a random action. So let's set our epsilon and let's set it to 0.9. And we're going to do something similar with our values for our discount factor and our learning rate. So let's do discount factor equal to 0.9. Let's also take our learning rate and set it to equal 0.9. That's going to be the rate which our agent is going to or should learn. And we also want to take the number of training episodes. Let's call it N training episodes. So we have a number of training episodes. Let's set it to 1,000. How many times this is going to train or how many episodes this is going to train on. Awesome. Now, essentially what we want to do is iterate through each episode. We want to take the range of our number of training episodes and set our, basically our epsilon. We want to find out our temporal difference to set that. We need to look at some previous Q values. We need to calculate our starting position and our action index. So let's get started. Let's take a big for loop. So we have our for episode in the range of our number of training episodes. There we go. Barring any syntax error on my part there. We want to take the row index and the column index for our grid, for our maze column index, and set it to our get starting location. We need a starting location, so let's have that for our each episode. Now we can set our terminal state while not is terminal state. We want to look at the row index and the column index. Okay. Next, let's set our action index for our next action. So we do need our next action as this agent iterates through the maze. For our action index, we can use our get next action, and we can use our row index, column index, and let's call our epsilon. So we want to have this instead of our random action. Let's use column index, and we need epsilon. Awesome. If I could spell correctly here, we want epsilon. All right, let me just delete this. Okay. Let me grab the rest of the code and we'll walk through it so we don't have to watch me typing out each line. But just keep that in mind how we want to approach this of setting the old row. We would need an old row index. We would also want to have the rewards for our columns and our rows. We need to take a look at Q values and old Q values. And we need to calculate our temporal difference. Okay. So you see the change in code or the update to the code. We are taking our old row index and our old column index to look at our row index and column index. our row index, column index equal to our next location. And our next location would need the row index, column index, and action. Lastly, we're looking at our rewards. Our old Q values would be Q values with the old row index, the old column index, and again, referencing our action index, and the calculation of our temporal difference, which is our reward plus the discount factor times the Q values with the row index and column index minus the old Q value from the previous Q value. Almost done, where we need our new Q value, which is our old Q value plus the learning rate times temporal difference, and our Q values with the old row index and our old column index equal to the new Q value. If you guys want to discuss this any further, again, I highly recommend the Q&A. Please feel free to print. Try to experiment with all the variables used in here. If you want to see the shapes, see how they can be used, what it's referencing, I highly recommend it, and I'm more than happy to discuss it further. One last thing we can do, so we have a little bit of a notification. Let's add a print statement so we know when the training is complete for our 1,000 rows. All right. If there's no syntax errors on my part, we should be good to go. The collab notebook is initialized. I reran everything. Let me run this. It should be very quick since we're only using NumPy. It's a very optimized model in a sense. Let me click this and we will then look for the shortest path. All right, we have our training complete. Let's also print the shortest path for some starting options. So we're starting at row 3, column 9 with the shortest path option with our get shortest path. We want to look at row 5 and 0 and starting at row 9 and column number 5. Let's print these out. Awesome, we have the shortest path, but we're not done. We're almost there. We can see our postman automatically get the shortest path from a legal, we can consider, location from our city to the item packaging area. But what about the reverse, so the opposite scenario? Basically referring to, can our postman deliver an item from anywhere in the city to the packaging area? But after the item, it would need to go then from that area, from the packaging area, to another location in the city because it would have to pick up the next item. So what can we do to solve this? And it's actually pretty simple. You could revise the order of the shortest path. Try to think about that for a second, and then this would be the solution. We can use the get shortest path. So let's take row 5 and column 2. And then all you would need to do is use the reverse option. With Python, we use path.reverse and we can print out the path. So we're looking at 5 and 2. And there we go. We have the shortest path. And it's really helpful if you want to grab the image in the cell and bring it down to compare and look at those paths. But you can actually see the paths if you take the printed out the statement, look at the column and the order and see how the salesman is traveling. So awesome work. You are using Q learning, what we learned from this course, as a little bit of a bonus and fun scenario and section to solve this essentially traveling salesman kind of problem. We're looking at the postman to deliver packages and items in the city to find those shortest options and shortest paths. Highly recommend that you customize, test out other options, change the hyperparameters, and if you discover anything better, if you discover any optimized or best parameters to use, please feel free to share them in the Q&A. Amazing. Hope you guys really enjoyed this. Please customize, experiment, and keep learning. It's so much fun to work with Q Learning and enjoy AI.